So we've learned a little bit about waves, right? We've learned that waves originate from vibrations, which are oscillating motions over a fixed position. A vibration can cause a disturbance to travel through a medium, transporting energy without transporting matter. This is what a wave is, but how do we properly talk about waves? How do we compare them to one another? Can we measure the size and speed of a wave? How do we know how much energy it carries? To find out, we'll need to look at the major wave parameters, the ways in which we measure waves. We'll learn how to characterize a wave by its period, frequency, amplitude, speed, and wavelength. Once we get to know the right way to use these parameters, we'll be able to learn more about how the different waves work. Let's start off by remembering what a wave looks like. We've seen this picture before. It's a wave drawn over a set of x and y axes. We plotted the wave as a function of time and said that the portion of a wave between two crests or troughs is called a wave cycle. From this image, we can see that waves travel by crests and troughs in a periodic fashion. That is, a full wave cycle always takes the same amount of time. In this case, that amount of time is exactly 2 seconds. 2 seconds is called the period of the wave. The period is the time it takes a wave to complete one cycle. We measure the period in seconds and we symbolize it with the capital letter T. You can think of the period as the time it takes for one particle in the medium to move back and forth. If this were a water wave, all the particles in the water would be moving up and down as the wave travels through. The time it takes for one water molecule to move up, move back down, and then return to its original position is called the period. Knowing the period of a wave is fine, but we often need to talk about waves in terms of how often the wave cycles are coming. In other words, we want to know the frequency of a wave. A wave's frequency is the number of cycles that are completed in a certain amount of time. The symbol for frequency is the lowercase f, and we measure it in cycles per second, which is the same as the unit hertz. A wave with a frequency of 20 hertz completes 20 wave cycles every second. Be careful that you don't confuse frequency with period. This is a common mistake. Frequency and period are actually opposites. While period is measured in seconds per cycle, frequency is measured in cycles per second. Consider a wave with a period of 2 seconds. Since the wave completes one cycle every 2 seconds, then its frequency is 1/2 or 0.5 hertz. So you see, period and frequency are reciprocals of each other. We can represent their relationship with a simple equation. The greater the period is for a wave, the less wave cycles can fit within a second, and so the lower the frequency gets. Likewise, a wave with a larger frequency would have to fit more wave cycles into every second, meaning the period of each cycle would have to be smaller. No matter what kind of wave you're looking at, the period and frequency will always be inversely proportional to each other. So now we know how to measure a wave based on cycles and time. But what about the height of a wave? Can we measure how high a wave's crest reaches, or how low the trough dips down? We already mentioned the amplitude in our previous lesson. It's the distance between the midline of a wave and its crest or trough. Amplitude measures how much energy is being transported by the wave. The larger the amplitude, the more energy a wave has. The symbol for amplitude is a capital letter A. Be careful not to make the mistake of thinking amplitude is the distance from crest to trough. It's only the distance from the resting point. Let's take the example of a giant water wave. We can see that the crests reach 1/2 meter above the resting point, and the troughs reach 1/2 meter below the resting point. It doesn't matter whether we look at the crest or the trough. The amplitude for this wave is 0.5 meters. If waves carry energy, and the energy of a wave is illustrated by its amplitude, then does that mean high amplitude waves move faster than waves of low amplitude? You might be tempted to think so, but the speed of a wave has nothing to do with the amplitude of its crests and troughs. Speed is measured by the distance the wave travels in a certain amount of time. Specifically, it's measured in meters per second. We already have the per second part down. Remember, the frequency tells us how many cycles are completed per second. But how do we know what the distance is for each complete cycle? The distance per cycle of a wave is called the wavelength. It's easiest to find the wavelength by measuring the spatial distance between two wave crests. Earlier, we were measuring the time it took to complete one cycle, but now we're measuring the length of one complete wave cycle. Wavelengths for long waves can be measured in meters, but we use nanometers to measure the length of shorter waves. The character that symbolizes wavelength is the Greek letter lambda. So now can we find out the speed of a wave? Sure. We've got a measure of distance from the wavelength of the wave, and we've got a measure of time from the frequency. Wavelength is meters per cycle, frequency is cycles per second. So multiplying the two gives us meters per second. In science, we use a lowercase v to symbolize speed because it's also called velocity. So we can sum up our findings now with the equation speed equals wavelength times frequency. Well, that wasn't so bad, was it? You've learned 5 ways of describing a wave using your wave parameters. The period, frequency, amplitude, speed, and wavelength are used to distinguish and categorize waves into groups. Later on, we'll learn about the many different types of waves that are out there and how to use these parameters to understand them all. A wave is a disturbance that travels through a medium in a periodic fashion, carrying energy without transporting matter. Waves are described and measured by 5 wave parameters: the period, the frequency, the amplitude, the wavelength, and the speed. The period of a wave is the time it takes to complete one cycle. The frequency is just the opposite. It's the number of wave cycles that are completed in 1 second. Amplitude and wavelength are both measures of distance. The amplitude measures the height of the crest of the wave from the midline. The wavelength measures the horizontal distance between cycles. Wave speed is found by multiplying the wavelength and the frequency. By learning the 5 major wave parameters, we can learn about waves more easily and categorize them based on their traits.
Have you ever wondered what happens to wood as it burns? It seems as if the wood may disappear into thin air. While burning wood appears to create energy and destroy the wood, they're not created or destroyed. Rather, energy and matter are changing from one form to another. You see, wood contains what we call chemical potential energy. Energy stored in the bonds that hold the chemicals together. This stored energy is released in the form of heat and light when the wood is burned. Wood also contains matter, where matter is anything that has mass and takes up space. The matter within the wood is transformed into different matter, including ash and soot, as it burns. The total amount of energy and matter in the wood before burning is equal to the energy and matter of the ash, soot, heat, and light after burning. In other words, energy and matter are conserved, both during and after the wood is burned. This phenomenon of conservation is explained by what we call the first law of thermodynamics, sometimes referred to as the law of energy conservation. The law states energy cannot be created or destroyed. Energy can be described as the ability to do work, where work is the movement of matter when a force is applied to it. With the example of burning wood, the energy we see in the form of fire is not created out of nothing, but rather comes from the energy that is stored in the wood. Likewise, the wood is not destroyed, but rather converted into ash and soot. In order to better understand the law of energy conservation, we need to consider the fact that it applies to systems. A system is simply a collection of component parts that make up a whole. Burning wood is a system that includes the wood, heat, ash, and soot. The universe is the largest system that we know of, and it includes all matter and all energy, including the burning wood that we're talking about. There's other examples of small systems. For example, you can consider your body as a system. When you're cooking, you could consider a pot of water on the stove as a system as well. Now that we have a good understanding of systems, let's consider the difference between an open and a closed system and discuss the law of energy conservation as it applies to each. A closed system is a system in which no matter or energy is allowed to enter or leave. The first law of thermodynamics tells us that the amount of energy within any closed system is constant. It doesn't change. An open system, on the other hand, allows stuff to come in and go out, like burning wood in a fireplace. Here, you can add wood to the fireplace and light it with a match from, say, your pocket. Heat, ashes, and soot can leave the fireplace as the fire burns. In other words, energy and mass can enter and leave a system as long as it comes from a system or leaves to go to another system. It's important to note, however, that the total mass and energy in our universe remains constant. Since most systems are not closed, The law of energy conservation can be rephrased to say that the change in the internal energy of the system is equal to the difference between the amount of energy coming in minus the amount of energy going out. In other words, the amount of energy in a system can change, but only if it comes from another system or goes to another system. At any rate, systems, whether they're open or closed, do not create or destroy energy. Rather, energy can enter from one system and leave to another. Energy that enters a system must either be stored there or leave. A system cannot expend more energy than it contains without receiving additional energy from an external source. Now that we understand that energy is conserved within a system, let's consider some practical applications of the law. In other words, what does it do for me? How does understanding the law of conservation help us out? Have you ever heard of a perpetual motion machine? Such a machine would continue to work without any input of energy. No such machine has ever been built, and according to the energy conservation law, such a machine never will be. Every machine requires the continual input of energy in order to keep working. The type of energy providing the input can vary, including the sun for solar energy, wind to move a windmill, water flowing over the dam, the breakdown of chemicals like gasoline to run our automobiles, or the breakdown of chemicals in the food we eat to pedal a bike. A really good bike can coast on level ground for a long time, but it's eventually going to come to a stop unless someone pedals the bike. So how does the law of energy conservation help us explain why machines will stop working if no energy is put into the system? Well, at first, the law of energy conservation may seem to not apply to machines because we're having to constantly add energy. So it seems as if energy is not being conserved. But on the contrary, the law absolutely applies. And in fact, it applies to all machines and all systems. Anytime a machine works, some energy is lost to what we call friction. Friction is heat generated by moving objects in contact with each other. No matter how well lubricated the wheels of a bike, for example, every bike will lose energy to friction as it moves. This energy lost to friction has got to come from somewhere according to the law of energy conservation. And indeed it does. It comes from the energy of the system. In this case, the system is the coasting bike. Eventually, all the energy of the coasting bike is going to be lost to friction and the bike will come to a stop. So you'll see, the law applies. The law of energy conservation applies to all matter and energy in every system, no matter what the conditions. And as it is a law, we assume it to be true in all cases, even if our observations don't seem to match up with the law. And if they don't, we assume that we're not accounting for some form of energy. And this assumption has helped us to discover new forms of energy. The amount of energy and mass in the universe is constant. It's been the same since the beginning of time. Energy can be changed from one form to another, but it cannot be created or destroyed. Energy can be moved from one system to another, but it cannot be created out of nothing. Likewise, a system cannot destroy energy. Rather, energy can be transferred to another system. All machines, whether they're man-made or natural, require a source of energy in order to continue working. As long as this energy is supplied, the machine can continue working. When the source of energy is removed, however, the machine will eventually stop. And the machine stops due to friction. Friction, again, is the heat generated due to moving objects in contact with each other. This principle is referred to as the first law of thermodynamics, or the law of energy conservation. And the law applies to all systems, both large and small. And again, it states that energy cannot be created or destroyed.
Johnny is riding his bicycle and enjoying his vacation here on Ideal Island, where all gases behave ideally, meaning they move rapidly and randomly, and the gas particles have no volume and no intermolecular forces. Keep in mind, real gases, like the ones you and I are familiar with, behave like ideal gases at normal temperatures and normal pressures. So, often when we are describing real gases, we will use the ideal gas characteristics to make approximations of our real gases. Now back to Johnny on Ideal Island. One thing Johnny really loves about this place is that all gases here are predictable and follow one law. Just like different states and countries have different laws, Ideal Island has its law of the land, the ideal gas law. All gas particles follow this law all of the time. The ideal gas law relates the temperature, pressure, number of moles, and volume of any gas. So let's take the air in the tires in Johnny's bicycle as an example. The air particles are all flying around inside of the tires, hitting the inner walls of the tires and applying pressure to the inside of the tire with each collision between the particle and the wall of the tire. These particles all have a certain velocity based upon the temperature of the gas. The hotter they are, the faster they will move. Also, these tires have a certain number of particles, and as a group, they have a certain volume, meaning they take up a defined amount of space. These four variables are all related, meaning that if one increases or decreases, one or more of the others will change. They can be related mathematically by the ideal gas equation, or PV equals nRT. In this equation, P stands for the pressure inside the container, the bicycle tires. V stands for the volume of the container. N represents the quantity of particles in the container. R is the ideal gas constant, equal to 0.0821 liter atmospheres per mole K, which we'll go into later, and T is the temperature of the gas in the container. Now any number of units can be used for pressure, volume, number of particles, and temperature, but the most commonly used ones are atmospheres, liters, moles, and kelvins, and we must use these units if we want to use 0.0821 as our R constant. So what does this equation mean? Well, let's start by comparing the pressure and temperature. Remember that pressure is caused by the collision between a gas particle and the walls of its container. Say we have two containers, each is holding particles. If they are both at the same temperature, the pressure inside each container will be the same. Now, if we increase the temperature of one container, the velocity of particles will increase and there will be more collisions with the inside walls of the container. According to Gay-Lussac's law, this will result in a higher pressure. So pressure and temperature are directly related to each other. We can represent this as P is proportional to T. And we can see this relationship in our car tires. As we drive, the temperature in our tires increases, which causes an increase in tire pressure. We also know that if two containers have the same volume and the same temperature, the more particles that are in that container, the more collisions there will be with the inside walls of that container, and the higher the pressure will be. This means that the pressure and the number of particles, or the number of moles of particles, is directly related. We see this every time we fill our tires with air. The more air we put in, the higher the tire pressure. We can represent this as P is proportional to N, or combine the two relationships to make P is proportional to N times T. Next, we will examine the relationship between the number of particles and the volume. According to Avogadro's law, if we increase the number of particles in a balloon, or a container that can expand, the volume of that container will also increase. So the volume and the number of particles are also directly related, giving us V is proportional to N. Now if we combine this with our previous statements, we get PV is proportional to NT. So this P times V is proportional to N times T also shows Boyle's law, which states that the pressure and the volume are inversely proportional to each other. And it also shows Charles' law, which states that volume and temperature are directly related to each other. All of these separate combinations of gas laws fuse together to form the ideal gas law. So where does this R come from? I'm going to start by taking the ideal gas law and rearranging it for R. So if we do that, we need to divide both sides by N times T, giving us R is equal to P times V divided by N times T. Now, we can find the R for any gas situation, each time getting the same number, of course. So let's solve it for a gas situation we have previously been introduced to, Avogadro's law, which states that 1 mole of an ideal gas at standard temperature and pressure, or 1 atmosphere and 273 kelvins, takes up 22.4 liters of space. So if we fill in the values we know, pressure equals 1 atmosphere, volume equals 22.4 liters, N equals 1 mole, and T equals 273 kelvins, we multiply across the top and bottom and then divide, round to 3 significant figures, we will get 0.0821 liter atmosphere per mole K. So you never really have to memorize R if you know Avogadro's law. One thing that's really tricky about this number is all the units attached to it. When we solved for R, none of these units canceled out. So whenever you use this R, you need to make sure you keep all 4 of those units on it. Also, if you do this when using the ideal gas law, you will always end up with the correct unit you are solving for. Another thing to mention about this constant is the number, 0.0821, is different depending on which units of pressure and volume you use. So if you always use liters, atmospheres, moles, and kelvins, the 0.0821 will always work. This means that there may be many situations you need to convert units like Celsius to kelvins, or torr to atmospheres, and so on. If we combine everything we already know about gases into one central governing principle, it would be the ideal gas law, which shows the relationship between pressure, volume, temperature, and the number of moles of an ideal gas. It is represented using the ideal gas equation, or PV equals nRT, where P is the pressure in atmospheres, V is the volume in liters, N represents the quantity of particles in the container, T represents the temperature in kelvins, and R is the ideal gas constant, equal to 0.0821 liter atmosphere per mole kelvins. Johnny uses this equation in his gas experiments to calculate any one of these variables as long as the other 3 are known.
Everyone is hot. Or rather, everyone has heat. Every atom and molecule in your body undergoes constant random motions that are impossible to predict. These random motions are what we call heat energy. Thermodynamics is the study of the movement of heat. If you touch a block of ice, it isn't always pleasant unless it's a really hot day. If you touch a hot pan out of the oven, you'll burn yourself. Both of these things happen because of how fast heat is moving. The heat from the hot pan moves into your hand rapidly, and when touching an ice cube, you lose your own body heat fast. Heat transfers from hot places to cold places, or in other words, heat spreads out. Extreme heat or cold can damage our tissues, so it's a pretty important thing to understand. It's also how we've been able to build refrigerators and large insulated coolers to take to the beach. These are examples of the many things we can do with heat if we understand how it moves within or between systems. A system is just a particular object or area we're looking at. Our system could be the inside of a thermos flask, or it could be the whole human body, or just our skin, or the gas inside a piston. We choose the system we want to look at for convenience. Then we can look at how heat moves in, out, and within that system. We can look at how the system changes. A thermodynamic process is any process that involves heat energy moving within a system or between systems. In this lesson, we're going to look at the 4 types of thermodynamic processes. The 4 types of thermodynamic process are isobaric, isochoric, isothermal, and adiabatic. Those terms are pretty hard to understand just from the names, so let's break them down one at a time. An isobaric process is one where the pressure of the system, often a gas, stays constant. Iso means the same, and baric means pressure. Pressure is related to the amount of force that the molecules apply to the walls of the container. Imagine that you have a gas inside a movable piston and you heat that gas up. By heating the gas up, you make the molecules move faster, which would normally increase the pressure. But at the same time, the piston expands, increasing the volume and giving the molecules more room to move. Since the walls of the container are now bigger, the pressure can stay the same, even though the molecules are moving faster. That makes it an isobaric process. An isochoric process is one where the volume of the system stays constant. Again, iso means the same and choric means volume. Volume is the amount of space the material takes up. So this would be like heating a gas in a solid, non-expandable container. The molecules would move faster and the pressure would increase, but the size of the container stays the same. An isothermal process is one where the temperature of the system stays constant. Thermal relates to heat, which in turn is related to temperature. Temperature is the average heat or movement energy of the molecules in a substance. An example of an isothermal process would be if we took a gas held behind a movable piston and compressed that piston. The volume has decreased and the pressure behind the piston has increased, since the molecules have less space in which to move. When you compress a piston, you're using energy. You're doing work on the gas, so normally the molecules would gain energy and move faster, and the temperature would increase. So the only way for an isothermal process to happen is if all that energy you put into compressing the gas comes out again. For example, by putting a cold reservoir in contact with the piston. In an isothermal process, whatever energy we put into the system immediately leaves the system again. In the real world, you would have to move the piston infinitely slowly to make this happen, but you can still do something that gets close to this by moving super slowly. An adiabatic process is one where no heat flows in or out of the system. We can't heat up the system by putting a hot reservoir next to it, and we can't cool down the system by putting a cold reservoir next to it. The system is perfectly insulated. In an adiabatic process, you take the gas behind the piston and move it up or down to change the volume, and both the pressure and the temperature change as a result. If you compress the piston, both the temperature and pressure increase because you've added energy to the system by doing work, pushing the piston down. If you let the piston expand, both the temperature and pressure decrease. For this to happen in real life, you would either need a perfect insulating material or you would need to push the piston infinitely fast. Thermodynamics is the study of movement of heat, which is the motion of molecules. A thermodynamic process is when heat moves, either within systems or between systems. There are 4 types of idealized thermodynamic processes. An isobaric process is one where the pressure stays constant and the temperature and volume change relative to each other. An isochoric process is one where the volume stays constant and the temperature and pressure change relative to each other. An isothermal process is one where the temperature stays constant and the pressure and volume change relative to each other. An adiabatic process is one where no heat flows in or out of the system. Pressure, volume, and temperature all change relative to each other. Together, these 4 processes help us understand how heat moves. Although many of them are not possible in real life, by understanding these idealized situations, we can better understand the more messy and complex situations in the world around us.
Do you ever wonder how the universe came into existence? Well, the Big Bang Theory tells us that the universe began as an infinite amount of energy exploded and began to spread into the universe as we know it today. All right, that's great, but what's energy? Well, energy is simply the ability to do work. And work is the movement of something by some force. So at the beginning of time, all the energy in the universe was contained in a single, relatively small location. This intense concentration of energy represented a massive amount of what we call potential energy, where potential energy is stored energy due to its location or position, and it is now equal to the total amount of energy in the universe today. As time goes on, the energy has spread over the vast expanse of our universe. On a much smaller scale, a reservoir of water held back by a dam contains potential energy as its location gives it the potential to flow over the dam. In each case, the stored energy, once released, spreads out and does so without any applied effort or force. In other words, the release of potential energy is a spontaneous process. A spontaneous process is simply a process that occurs without the need for additional energy. Another way of putting that is, it happens automatically once you give it a little bit of a kick. As the energy spreads out, some of it is converted into usable energy and gets the work done that we need. The rest of the energy is converted into unusable energy, simply referred to as heat. As our universe continues to spread out, it contains less and less useful energy. As less useful energy is available, well, less work can get done. As water flows over a dam, it contains less useful energy as well. This decrease in useful energy over time is referred to as entropy, where entropy is the amount of unusable energy in a system. And a system is simply a collection of objects that make up a whole. Now, entropy can also be referred to as the amount of randomness or chaos in a system, less organization. As usable energy decreases over time, disorganization and chaos increase. Thus, as stored potential energy is released, not all of it is converted into usable energy. All systems experience this increase in entropy over time. This is very important to understand, and this phenomenon is referred to as the second law of thermodynamics. As you may have guessed, the second law of thermodynamics follows the first law of thermodynamics, which is commonly referred to as the law of energy conservation. And it states that energy can't be created and it can't be destroyed. In other words, the amount of energy in the universe or any system is constant. The second law of thermodynamics is commonly referred to as the law of entropy, and it holds that energy becomes less usable over time. Therefore, while the quantity, based on the first law, the quantity of energy remains the same, the quality of energy decreases over time, based on the second law. How does understanding the second law of thermodynamics help us? The implications of the second law of thermodynamics are as extensive as the boundaries of our universe. The universe is constantly losing usable energy and becoming more chaotic, less organized. This would suggest that the universe is not eternal, but rather has an end, both in space and time. At a much smaller level, the springs of an old clock must be wound in order for the clock to tick and to tock. The wound springs contain a lot of stored potential energy, and that energy is used over time to make the clock work. That's what moves the hands of the clock. However, not all the potential energy is converted into usable energy. Some of that energy is lost in the form of heat. Heat is unusable energy. If no one's available to wind up the clock, it won't be able to do any work again. Let's now consider a biological example. Our bodies are systems. As long as we can consume energy, our bodies can do the work that's needed to survive and reproduce. Eventually, however, our bodies become less organized and more chaotic. Structure and function eventually give way to entropy. Nobody lives forever, and just like the universe, our lives have an end. However, scientists are constantly researching for ways to slow down entropy, both in man-made and natural systems. A good example of that is the internal combustion engine that makes our automobiles move. They're far more efficient now than they were when they were first invented. The first law of thermodynamics reminds us that the amount of energy in a system is constant. It has been the same since the beginning of time. Now, energy can be changed from one form to another, but it cannot be created or destroyed. That's the first law. The second law of thermodynamics tells us that entropy increases in a system as the potential energy is converted into usable energy for work. In other words, all systems, both natural and man-made, will eventually fall apart.
Johnny Dalton and his family are vacationing on Ideal Island, where all gas particles behave ideally. They move randomly and rapidly, and they don't interact with each other. They have elastic collisions, and they are point particles, meaning the individual particles don't have any volume. Just like when you travel to a foreign country and have to use a different currency or different units to measure things, Johnny must use different units on Ideal Island. Today we are going to discuss temperature and the temperature units that are used here on the island. When you have a fever and you take your temperature, did you know that you are really just measuring how fast the particles in your body are traveling? You can think of a thermometer like a little particle speedometer. The faster the particles are moving, the greater the temperature. Temperature is defined as the measurement of the average kinetic energy of the particles in a substance. The hotter something is, the faster its particles are moving. A normal bulb thermometer usually contains a red liquid in a reservoir at the bottom. When this bulb is touching something warm, the fast particles in the warm substance hit the particles in the glass, or whatever your thermometer is made out of, and that causes them to speed up. And then they hit the particles in the red liquid, causing them to speed up. When the particles in the red liquid speed up, they space themselves apart more, causing the liquid to expand. This liquid needs a place to go, and in a thermometer there is no place to go but up. You may measure your temperature using the Fahrenheit scale, but the rest of the world uses the Celsius scale. If you know a temperature in Fahrenheit, you can convert it to Celsius using this equation. This equation is rarely used in chemistry because chemists use the Celsius scale for measuring temperature. The Celsius scale was created using the freezing and boiling temperatures of water at sea level as a standard. 0 degrees Celsius, or 32 Fahrenheit, is the freezing point of water, and 100 degrees Celsius, or 212 degrees Fahrenheit, is the boiling point of water at sea level. There are 100 divisions, or degrees, in between these 2 points, and each division represents a degree Celsius. Now, because you may not use the Celsius scale on a daily basis, you can use the following poem to remember the relative temperatures and their corresponding degrees. 30 is hot, 20 is nice, 10 is cold, and 0 is ice. Normally in science, the Celsius scale is used, but on Ideal Island a different scale is used, the Kelvin scale. The Kelvin scale is an absolute scale, meaning that 0 is the lowest temperature possible. If the temperature is a measure of the average kinetic energy of the particles in a substance, then the temperature where there is no molecular movement would be 0 kelvins, or absolute 0. Currently, this temperature only exists in theory. It has never been reached, but scientists have come extremely close. The degree Celsius and the Kelvin are both equal in size, which makes converting between the Celsius and Kelvin scale a simple matter of just adding or subtracting. At 0 kelvins, the temperature in Celsius is negative 273 degrees. So to calculate one of the temperatures, if you are given the other, you would use the following equation. Kelvins equals degrees Celsius plus 273. It's important to note that the degree symbol isn't used when expressing the temperature in kelvins. Let's practice converting between these two units of temperature. Say you keep the temperature of your home at 22 degrees Celsius, so about 72 degrees Fahrenheit. What would this be in kelvins? To solve this, you would replace the given temperature with the degrees Celsius in the equation, then add 273, which gives you 295 kelvins. The average January temperature in my hometown is 262 kelvins. What would this be in degrees Celsius? To solve this, you would replace the given temperature with the kelvins in the equation, and then you would solve for degrees Celsius by subtracting 273 from both sides. This would give you an answer of negative 11 degrees Celsius. Temperature is a measure of the average kinetic energy of the particles, so it is directly related to the speed of the particles. It is measured using a thermometer and expressed in either degrees Celsius or kelvins. On Ideal Island, the temperature unit that is used is the Kelvin. The lowest temperature on the Kelvin scale is 0 kelvins, or absolute 0. It is the theoretical temperature at which all particles stop moving. To convert between degrees Celsius and kelvins, the following equation is used. Kelvins equals degrees Celsius plus 273.
A heat engine is a device that produces motion from heat and includes gasoline engines and steam engines. These devices vary in efficiency. The Carnot cycle describes the most efficient possible heat engine, involving 2 isothermal processes and 2 adiabatic processes. It is the most efficient heat engine that is possible within the laws of physics. The second law of thermodynamics states that it is impossible to extract heat from a hot reservoir and use it all to do work. Some heat must be exhausted into a cold reservoir. Or in other words, no process can be 100% efficient, because energy is always lost somewhere. The Carnot cycle sets the upper limit for what is possible, for what the maximally efficient engine would look like. Before we go through the details of the Carnot cycle, we should first define 2 important terms, isothermic and adiabatic. An isothermic process is a process where the temperature remains constant and the volume and pressure vary relative to each other. An adiabatic process is a process where no heat enters or leaves a system to or from a reservoir, and the temperature, pressure and volume are all free to change relative to each other. The Carnot cycle can be described by this pressure-volume graph. Stage 1 is an isothermal expansion, where the volume increases and the pressure decreases at a constant temperature. This is where heat enters the system from the hot reservoir, i.e. from your power source, to keep the temperature constant. The gas inside the engine is allowed to naturally expand and push a piston. Stage 2 is an adiabatic expansion, where the hot reservoir is now taken away. The gas continues to expand, causing the pressure and temperature to decrease. Stages 1 and 2 are where the engine actually does useful work. Stage 3 is an isothermal compression, where the volume decreases and the pressure increases at a constant temperature. The pressure is kept constant by putting it in contact with the cold reservoir. Here you actually have to do work by physically pushing the piston to compress the gas. Lastly, stage 4 is an adiabatic compression, where you remove the cold reservoir. The volume continues to decrease, but without the cold reservoir, this leads to both the pressure and temperature increasing. Stages 3 and 4 both involve you doing work on the system. You are expending energy to make this happen by pushing down on the piston. The useful work that comes out of the Carnot cycle is the difference between the work done by the engine in stages 1 and 2 and the work done or the energy wasted by you in stages 3 and 4. The Carnot cycle, with its 2 isothermal processes and 2 adiabatic processes, is the most favourable case. In other words, the cycle that produces the largest difference between these values allowed by the laws of physics. Unfortunately, the Carnot cycle is not practical in real life. If you build a Carnot engine in your car, it would indeed be super efficient, but the process would operate so ridiculously slowly that you would be overtaken by pedestrians. The efficiency of a Carnot engine is entirely a function of the temperatures of the hot and cold reservoirs you use. It can be calculated using this equation, where TH is the temperature of the hot reservoir in Kelvin, and TC is the temperature of the cold reservoir in Kelvin. So all you have to do is take the difference in temperature between these reservoirs, divide it by the temperature of the hot reservoir, and then multiply it by 100 to turn it into a percentage. It's important to note that the temperatures must be in Kelvin for it to work. So if you have a temperature in degrees Celsius, for example, you need to add 273 to that value to convert into Kelvin. Maybe this will be clearer if we went through an example. Let's say you're operating a Carnot engine with a hot reservoir at a temperature of 100 degrees Celsius and a cold reservoir at a temperature of 0 degrees Celsius. What is the efficiency of the Carnot engine? Well, first of all we should write down what we know. But we can't do that until we convert our temperatures into Kelvin. 100 degrees Celsius in Kelvin is 100 plus 273, which comes out as 373 Kelvin. 0 degrees Celsius in Kelvin is 0 plus 273, which is 273 Kelvin. So TH is 373 and TC is 273. Plug these numbers into the efficiency equation. 373 minus 273 divided by 373 multiplied by 100 gives us an efficiency of approximately 27%. So with the reservoirs at these admittedly similar temperatures, that is the most efficient that an engine could ever be. As you may have noticed from the equation, the larger the difference in temperature between the two reservoirs, the greater the efficiency. A heat engine is a device that produces motion from heat and includes gasoline engines and steam engines. These devices vary in efficiency. The Carnot cycle describes the most efficient possible heat engine, involving 2 isothermal processes and 2 adiabatic processes. It is the most efficient heat engine that's possible within the laws of physics. Unfortunately, the Carnot cycle is not practical in real life. If you build a Carnot cycle in your car, it would indeed be super efficient, but the engine would run too slowly to be useful. The Carnot cycle can be described by this pressure-volume graph. Stage 1 is an isothermal expansion, where the volume increases and the pressure decreases at constant temperature due to contact with a hot reservoir. Stage 2 is an adiabatic expansion, where the hot reservoir is now taken away. The gas continues to expand, causing the pressure and temperature to decrease. Stages 1 and 2 are where the engine actually does useful work. Stage 3 is an isothermal compression, where the volume decreases and the pressure increases at a constant temperature again. The temperature is kept constant by putting it in contact with a cold reservoir. Lastly, stage 4 is an adiabatic compression, where you remove the cold reservoir. The volume continues to decrease, but without the cold reservoir, this leads to both the pressure and temperature increasing. Stages 3 and 4 both involve you doing work on the system. You are expending energy to make this happen by pushing down on the piston. The useful work that comes out of a Carnot cycle is the difference between the work done by the engine in stages 1 and 2 and the work done or energy wasted by you in stages 3 and 4. The efficiency of a Carnot engine is entirely a function of the temperatures of the two reservoirs you use. It can be calculated using this equation, where TH is the temperature of the hot reservoir in Kelvin, and Tc is the temperature of the cold reservoir, also in Kelvin. When I was a kid, I hated getting up in the night to use the bathroom. Not only did it make it hard to get back to sleep, but the bathroom floor was tiled and super cold. I would run across the tile to the rug feeling like my feet were burning. Perhaps you've noticed how your feet feel when you step from a carpeted room into a tiled room. Which floor surface is colder? The floor of a tiled room pretty much always feels colder, but they're actually exactly the same temperature. Whenever you're in a room that has been sealed off for a while, with no windows and doors open, it won't take long for everything in the room to reach thermal equilibrium, or equal temperature. So why do tile floors feel colder? It's all because of thermal conductivity. Conduction is the passing of heat energy between two objects that are in direct physical contact. It's one of the 3 types of heat transfer, the other 2 being convection and radiation. Whenever 2 objects of different temperatures are in contact with each other, heat energy will pass between them. To understand this, we have to realize that temperature is the average kinetic energy of the molecules in a substance. Hotter materials have molecules that are moving faster. So when a cold object and a hot object are touching, the fast-moving hot molecules will hit the colder molecules, spreading the heat from the hot object to the cold object. This will keep happening until they reach the same temperature. But that says nothing about how fast it will happen. Some materials are better conductors than others. Your feet are pretty much always warmer than the floor, but a tile floor conducts heat faster. What your skin feels as cold is just the heat transferring from your feet to the floor, and it happens much faster with a tile floor than with a carpet. There are all kinds of examples of conduction in our everyday lives. The key is to think about whether objects are physically touching. So a saucepan of boiling water being heated by an electric stove is receiving heat energy from the stove by conduction. And when you touch a metal cookie sheet in the oven and burn yourself, that also happened due to conduction. In physics, everything must have an equation. It's kind of an unwritten rule. Conduction is no exception. How fast conduction happens depends on several factors. What material the objects are made from, the conductivity, the surface area of the 2 objects in contact, the difference in temperature between the 2 objects, and the thicknesses of the 2 objects. In equation form, it looks like this. Q over T is the rate of heat transfer, the amount of heat transfer per second, measured in joules per second, or watts. K is the thermal conductivity of the material. For example, copper has a thermal conductivity of 390, but wool has a thermal conductivity of just 0.04. T1 is the temperature of one object and T2 is the temperature of the other. Since it's a temperature difference, you can actually use Celsius or Kelvin, whichever is the most convenient. And D is the thickness of the material we're interested in. So, the rate of heat transfer to an object is equal to the thermal conductivity of the material the object is made from, multiplied by the surface area in contact, multiplied by the difference in temperature between the two objects, divided by the thickness of the material. Okay, let's go through an example. Let's say you're going to a water park, and you're going to take a styrofoam cooler with you. The cooler has a total surface area of 1.2 meters squared, and the walls are 0.03 meters thick. The temperature inside the cooler is 0 Celsius, and at the hottest part of the day it's 38 degrees Celsius. During this time of day, how much heat energy per second is lost by the cooler? And how much heat energy is lost in 3 hours at the water park, assuming the temperature stays at 38 degrees? Note the thermal conductivity of styrofoam is 0.01. So all we have to do to solve this problem is plug numbers into the equation. The heat energy per second, Q over T, is equal to the thermal conductivity of styrofoam, K, multiplied by the surface area of the cooler, A, multiplied by the difference in temperature between the cooler and the outside, that's T2 minus T1, divided by the thickness of the styrofoam. So that's just 0.01 multiplied by 1.2 multiplied by 38 divided by 0.03. Type all that into a calculator and you get 15.2 joules per second, or in other words 15.2 watts. For the second part of the question, we need to figure out how much energy is lost in 3 hours. Well, we have the energy lost per second, 15.2 joules, so we just need to know how many seconds there are in 3 hours. 3 hours times 60 minutes times 60 seconds gives us a total of 10,800 seconds. 15.2 joules a second for 10,800 seconds, well, you just multiply the two together. 15.2 joules a second multiplied by 10,800 seconds gives you a total of 164,160 joules over the 3 hours. And that's it, we're done. Conduction is the passing of heat energy between two objects that are in direct physical contact. It's one of the 3 types of heat transfer, the other 2 being convection and radiation. Whenever 2 objects of different temperatures are in contact with each other, heat energy will pass between them. To understand this, we have to realize that temperature is the average kinetic energy of the molecules in a substance. Hotter materials have molecules that are moving faster, so when a cold object and a hot object are touching, the fast-moving hot molecules will hit the colder molecules, spreading the heat from the hot object into the cold object. This will keep happening until they reach the same temperature. Some materials are better conductors than others. This is why tile floors feel so cold. Your feet are pretty much always warmer than the floor, but a tile floor conducts heat better. What your skin feels as cold is just the heat transferring from your feet into the floor. And it happens much faster with a tile floor than with a carpet, even though they're usually the same temperature. The equation for conduction tells us that the rate of heat transfer Q over T in joules per second, or watts, is equal to the thermal conductivity of the material, K, multiplied by the surface area of the objects in contact, A, multiplied by the difference in temperature between the two materials, T2 minus T1, divided by the thickness of the material we're interested in, D. You can use this to find the rate of heat transfer, but if you're given a particular period of time, you can also calculate the total heat transferred. Conduction is taking place all around us. When you burn yourself on a hot cookie sheet, when you heat up a saucepan on an electric stovetop, when you have cavity wall insulation installed, whenever heat is transferring between 2 things that are touching directly, it's because of conduction.
Have you ever been to a party where the music is so loud you can feel it? I don't mean just the beat in your mind. Sometimes you can literally feel the vibrations of the music in the floor or other objects. People often like to blast their music from their cars on the highway, causing unpleasant buzzing in the vehicles nearby. But how do we get sensations like these from music playing so far away? How can music travel from somebody's speakers and cause such powerful vibrations in other objects? To answer this question, let's explore what we mean when we say the word vibration. What are vibrations? Where do we find them? In a guitar string? On a trampoline? What about a cymbal in a drum set? The ground in an earthquake? These are all examples of things that experience vibrations. In each case, there's an object beginning at a resting position, such as the cymbal on its stand or the string on the guitar. The motion made by the object is in a back-and-forth nature over the resting position. Vibrations are oscillating motions around a fixed position. When an object vibrates, it exhibits a motion that repeats itself over the same path in a periodic fashion. That is, the time it takes to complete one cycle of the vibration is always the same. Take a look at this system here. We have a mass being suspended from a spring. When the system is at rest, the mass just sits there in the air, stretching the spring to a certain extent because of its weight. But if someone pulls the mass down a little and lets go, the mass springs upward, past its resting position, and then oscillates up and down at a certain frequency. If we plot its position over the course of time, we see that there is a very regular, periodic nature to its movement. This nature is best represented in the form of a wave. The wave is a disturbance that travels through a medium from one place to another. Waves are formed by the vibration of the object or substance that carries the wave. You can make your own waves in a jump rope by creating a vibration at one end. Begin with the jump rope in its resting position, then move one end quickly up and down. You'll create a wave that travels through the rope from one end to the other. If you do it right, the wave might even bounce off the other end and travel back to your hand. All waves are caused by some type of vibration. Vibrations cause a disturbance in the medium that becomes the source of the wave. Think about water waves formed when you throw a rock into a pond. The rock hitting the surface causes the water to vibrate. This vibration disturbs the surrounding water, creating waves that move outward from the point of the rock's impact. If we look more closely at a typical wave, we can see the periodic nature in the shape of the wave itself. Let's plot the wave as a function of time. We'll put seconds along the horizontal axis, and the vertical axis will measure the wave's vertical displacement. Just so we can talk about the wave more clearly, we'll label it with letters at different points. The letters A and E show the low points of the wave, which we call troughs. The letters C and G show the crests of the wave. A full wavelength is defined as that portion of the wave between two successive crests, or between two troughs. By looking at how the crests and troughs line up with our horizontal axis, we can see that a full wavelength always takes the same amount of time. That's why we say that waves have a periodic nature. But what about how high and low the wave oscillates? Can we learn anything from the height of a wave's crest or the depth of its trough? The distance between the midline of a wave and its crest or trough is called the amplitude. If this was a wave traveling through water, the amplitude would measure the maximum displacement of the particles from their resting point. We may not always see a wave's amplitude, especially if it's a sound wave or a light wave, but amplitude tells us something very important. It's a measure of how much energy the wave is carrying. As the particles in the medium move up and down with the wave, they transfer energy in the direction that the wave is moving. Let's go back to that rock you threw into the pond. The waves moving outward from the rock's point of impact will eventually reach the shore. They're transferring energy from the place where you impacted the water and carrying the energy onto the shore. So, waves transport energy. But do they also transport matter? Imagine that a duck was sitting on the pond at the time you threw in the rock. Your water waves would flow outward toward the shore. But would they carry the duck in to shore as well? Of course not. Ducks bob up and down on the surface of waves. The same thing happens with the molecules of water in the waves. The water itself just bobs up and down, transferring energy between particles as the wave moves along. Waves don't actually transport any matter, even though they do transport energy. The waves on your jump rope transport energy, but the particles in the jump rope itself stay put. Sound waves carry energy through the air, but the air itself doesn't go anywhere. So, waves transport energy without transporting matter. The best way to experience this concept is through sound. When that driver blasts his music right next to you at a stoplight, the energy of the sound rattles your car without transferring any material your way. The same is true for the music at that party. We now know that sound waves carry energy from the music source, the vibrating speakers, toward the people and objects around them. They transfer this energy to the floor, the walls, and the ears of all the partygoers. Like all waves, sound waves carry energy without carrying matter. So, even though they transfer energy to other objects, they don't transfer any amount of mass or particles. Vibrations in objects and substances are oscillating motions that occur repeatedly over a fixed position. Vibrations are the origins of waves. When vibrations disturb a medium, the disturbance travels through the medium from one location to another in the form of a wave. Waves travel by crests and troughs in a periodic fashion. The portion of a wave between two crests or troughs is called a wavelength. A wave's amplitude indicates how much energy is being transferred by the wave. While waves do transport energy from one place to another, keep in mind that they do so without transporting matter.
Do you know what our planet looks like on the inside? You've probably seen pictures like this one showing the layers inside the Earth. You've got the crust on the outside, the mantle underneath, and then the outer and inner core. Scientists tell us that the mantle is made of solid rock, while the outer core is liquid. The inner core, they say, is solid again. But how do scientists know all that? Nobody's ever dug down into the Earth's inner layers. How can we possibly claim to know what's down there, or if the layers are in solid or liquid form? Well, believe it or not, we do have legitimate evidence for the state of the Earth's inner layers. To understand it all, we'll have to learn a bit more about waves. When you picture a wave in your mind, you probably envision a transverse wave. It kind of looks like a squiggly line with peaks and valleys, which we call crests and troughs. In a transverse wave, the particles of the medium move perpendicular to the wave's direction of travel. Imagine a line of people all holding hands. If the first person on the left jumped up and down, they would pull on the hand of the next person in line, causing them to jump up and down too. This would continue on down the line to the right until everyone had jumped up and down. The people are like the particles in a medium. They move up and down while the wave moves from left to right. This type of wave gets its name from the fact that the particles move in a direction transverse to the direction of the wave. Transverse waves can be mechanical or electromagnetic in nature. A mechanical wave is a disturbance that travels through a medium, such as a vibrating string. In contrast, electromagnetic waves, such as light or radio waves, don't need a medium and can travel through empty space. While all electromagnetic waves are transverse, mechanical waves can be transverse or longitudinal, which brings us to our next type of wave. In a longitudinal wave, the particles of the medium move parallel to the wave's direction of travel. Let's go back to our line of people to see what this would look like. In this scenario, instead of the person on the left jumping up and down, they bump into the person next to them. Now this next person, being knocked off balance, will bump into the person beside them, and so on down the line. As each person regains their balance, they return back to the place where they were standing before being so rudely disturbed. As we can see, the wave traveled from left to right again, but this time the motion of the people was also left and right. To help us remember this relationship, we can think about how the motion of the particles is along the longitudinal wave. While transverse waves have crests and troughs, longitudinal waves have compressions and rarefactions. A compression is where the density of the wave medium is highest. In our line of people, this was where folks were actually bumping into each other. A rarefaction is where the density of the wave medium is lowest. In our line, this occurred just after the compression where the people were spread out, trying to regain their balance. Just like the wavelength of a transverse wave is the distance from crest to crest, or trough to trough, the wavelength of a longitudinal wave is the distance between compressions or between rarefactions. When it comes to mechanical waves, transverse and longitudinal waves are not equal. While a longitudinal wave can travel through solids, liquids, and gases, transverse waves can only travel through solids. To understand why this is, let's go back to our line of people who were jumping up and down. When we saw them before, everyone was holding hands, which allowed one person to pull on the next. This bond between people is like a solid object, where the particles are strongly connected to each other. Now imagine that the people stopped holding hands and the first person jumped. Nothing happens. Without a strong connection, one person can't get the others to jump. This is like a liquid or gas where the particles are not strongly connected to each other. On the other hand, a longitudinal wave can be transmitted whether the people or particles are strongly joined or not. All they have to do is bump into each other to move the wave along. Now you may be wondering about all those water waves you've seen at the beach. Those sure do look like transverse waves, and in some respect they are. But the waves you're seeing are actually a special combination of transverse and longitudinal waves, called surface waves. A purely transverse wave cannot travel through liquid. The inability of transverse waves to travel through liquids played an important role in discovering the layered composition of the Earth. Any time an earthquake occurs, It sends out seismic waves in the form of longitudinal P waves and transverse S waves. As instruments became more sensitive, geologists learned that the seismic waves from a single earthquake could be measured at locations all over the world. However, they also learned that only the longitudinal P waves were arriving at the opposite side of the Earth. Something was blocking the transverse S waves. Knowing that transverse waves could only travel through solid material, scientists were led to the conclusion that the outer core of the Earth was actually a liquid. Waves can be divided into two major groups, transverse waves and longitudinal waves. In a transverse wave, the particles of the medium move perpendicular to the wave's direction of travel. Transverse waves are characterized by peaks and valleys, called crests and troughs. In a longitudinal wave, the particles of the medium move parallel to the wave's direction of travel. This type of wave is characterized by areas of high and low densities in the medium, called compressions and rarefactions. While a longitudinal wave can travel through solids, liquids, and gases, transverse waves can only travel through solids.
Are you one of those people who likes to shout "echo" whenever you're inside a cavernous building? I think it's fun to experiment with echoes. Lots of people like to shout when they're standing under a bridge, or inside a parking garage, or at the bottom of a canyon. We know that echoes are simply the reflection of sound from the rigid walls of buildings and natural formations. But what can echoes tell us about sound waves? Can we learn how sound travels from one place to another by studying the echo phenomenon? Before we get into that, let's review what a sound wave is. We've learned already that sound waves are longitudinal waves. That is, the particles in the medium vibrate in a direction parallel to the movement of the wave. Longitudinal waves are tougher to visualize than transverse waves, so let's use the sound of a guitar string as an example. When you pluck a guitar string, it begins to vibrate from side to side. This is what it would look like in slow motion. Let's pretend these are the air particles that are evenly distributed around the guitar and everywhere else. When the string moves to the right, like this, it pushes on the air particles and makes them press together. This is called a compression. When the string moves to the left, like this, it creates a gap in the air particles and they get further apart. This is called a rarefaction. You probably remember that compressions and rarefactions are the equivalent of crests and troughs for a longitudinal wave. These areas of higher and lower air pressure travel outward, away from the string. In other words, the sound wave travels outward from the guitar. However, the air particles themselves do not travel. They simply oscillate back and forth in a direction parallel to the motion of the sound wave. In this example, the air surrounding the guitar is called the medium because it's the material that carries the sound. When talking about waves, a medium is the substance that transports a wave from one place to another. The medium for sound waves is often air. But sound can also travel through liquids and solids. If you're talking about sound waves traveling between two whales singing in the ocean, then the medium is seawater. If you're talking about your neighbor's music traveling through the walls of his house, then the medium is the wood and drywall. No matter what the medium is, sound waves are able to travel through it because of the particles interacting with each other. The compressions and rarefactions occur within the particles of seawater, or wood, or drywall, just as they did in the air outside our guitar string. Once the first particles are pushed by the vibrations of the sound source, then they pass this push on to the next particles, which pass it on to the next, and so on. Thus the wave travels through the medium as a result of the particles bumping back and forth on each other. The interactions between particles in the medium cause the sound wave to travel through the medium. So if sound waves travel because of the particles in the medium, then what happens to sound if there is no medium? Well, you guessed it, without a medium there's no sound. Sound waves require a medium in which to travel from one place to another. Think about a place where there's absolutely no air, like the surface of the moon. If you were standing on the moon and your friend was standing 10 feet away from you, you could shout and scream and clap your hands and your friend wouldn't hear a thing. The moon has no atmosphere. It's in the great vacuum of outer space, so it doesn't matter how much noise you make. Your sound will not carry anywhere because there's no medium to carry it. Let's go back to the different mediums that sound can travel through. We said that sound waves travel through solids, liquids, and gases. They can travel through all states of matter. But do the waves travel the same way through each of these different substances? We know that a solid has its particles packed very tightly together. Liquid particles are more loosely packed, and particles in a gas are pretty far apart. The distance between the particles affects how strong the interactions are between them. This in turn affects how quickly they transfer the energy of the wave. The stronger the particle interactions are, the more quickly the wave is transferred. So in general, sound travels faster in solids than in liquids, and faster in liquids than in gas. Temperature actually increases the speed of sound because warmer particles generally move at a faster rate. Scientists have derived a special formula for finding the speed of sound in dry air. It works for most of the temperatures found on Earth. The formula is V equals 331 plus 0.61 T, where V is the speed of sound and T is the temperature. For this formula, speed must be measured in meters per second and temperature in degrees Celsius. You can see by this formula that an increase in temperature, or T, would cause an increase in speed, or V. If the temperature was 20 degrees Celsius, then the speed of sound in dry air would be about 343 meters per second. If the temperature rose to 30 degrees Celsius, then the speed would increase to 349 meters per second. Don't forget that the speed of sound has everything to do with what's happening with the sound wave. A wave is a disturbance traveling through a medium. When we measure the speed of sound, what we're really finding is how fast a disturbance is passed between particles, or the distance a disturbance travels per unit of time. We just saw one formula for finding the speed of sound, but most formulas for sound speed are much more complicated. There are so many factors out there that can change the speed of sound, there's no one formula that accounts for them all. But when it comes down to wave speed, all you're really looking for is distance per unit time, right? So I wonder if we can find the speed of a sound wave based on the other wave parameters. Do you remember this formula? It's actually called the wave equation. It states that you can find the speed of a wave by multiplying the wavelength by the frequency. You can also rearrange this to find speed by dividing wavelength by the period, because period is the reciprocal of frequency. Let's say the wavelength for a sound wave was 34 meters and it took exactly 1/10 of a second to pass by. The wavelength would be 34 and the period would be 0.1. So the speed of this wave would be 340 meters per second. Let's try it using frequency. Let's say the frequency of a sound wave is 500 Hertz, that is 500 wave cycles per second, and the wavelength is 0.7 meters. To find the speed, you'd multiply these two and get 350 meters per second. So, do you think this wave equation can help us learn anything about echoes? If you have ever been inside a very steep-walled canyon, you know that sound can bounce around between the stone walls. If you shout, you'll hear your own call return to you in a matter of seconds. If you could time exactly how many seconds your echo took, could you find the speed of sound inside the canyon? Let's try it. You're standing in a canyon facing a vertical wall 519 meters away. You let out a shout and it returns to you in exactly 3 seconds. What's the speed of sound in this case? Well, you know the time it took, so the period is 3 seconds. The distance the wave traveled was 1,038 meters. You have to double the distance because the wave traveled to the canyon wall and returned back to you. So if speed is meters per second, then 1,038 meters divided by 3 seconds is 346 meters per second. And that sounds like a reasonable speed for a sound wave. Sound waves are longitudinal waves that travel by compressions and rarefactions in the air, water, or other mediums. Sound requires a medium in order to travel, therefore it cannot travel in a vacuum. Sound waves travel faster through solids than liquids, and faster through liquids than gas. The speed of sound waves increases with higher temperatures, but decreases with higher densities. A simple way to find the speed of sound wave is to use the wave equation, where speed is derived from the wavelength and frequency or period. Sound speed can also be found by timing an echo from a known distance. While many factors affect how fast a sound wave travels, sound speed really comes down to how the particles interact inside of the medium. Are you a musical person? Do you have perfect pitch? If I play this sound here, and then I play this sound, can you tell what the difference is? You probably noticed that the first sound was lower and the second sound was higher. If you have musical training, you may have recognized that the interval between the two notes was a major sixth. And if you have perfect pitch, you may have recognized the notes as a C and an A. But what does pitch mean when it comes to sound? We know that sound travels in waves and that those waves are characterized by their wavelengths, amplitudes, and other parameters. If the two tones I just played come from different sound waves, then what exactly about the waves is different between the two? In this lesson, we're going to explore the more familiar characteristics of sound, like pitch and volume. We'll talk about what these mean in terms of the sound waves we've learned about so far in this chapter. By the end, you'll have a deeper understanding of how sound works and maybe appreciate music a little bit more. Let's start by recalling a few things about sound waves. While sound can travel through all types of substances, we're going to use air as the medium in our examples here. A great way to visualize longitudinal waves in air is to think of the sound coming from a guitar string. When you pluck the string, it vibrates from side to side, pushing the surrounding air molecules in a periodic fashion. The compressions and rarefactions in the air comprise a longitudinal wave, which we detect as sound. If we could look at just one air particle, we would see it oscillating back and forth. Sometimes the particles move back and forth over a very large distance. Other times the particles oscillate just a little ways. The amount of oscillation in the particles of the medium is related to the amount of energy carried by the wave. Can you remember which of the 5 wave parameters describes a wave's energy? And by wave parameters, I mean the frequency, wavelength, period, speed, and amplitude. The one that describes a wave's energy is the amplitude. In a transverse wave, the amplitude can be seen as the height of the crests, but in a longitudinal wave like sound, amplitude is a measure of how far the particles oscillate back and forth. In a high-energy wave, the amplitude is large because the particles oscillate over a large distance. A low-energy wave has low amplitude because the oscillations are small in size. So now we get the relationship between energy and amplitude, but how does that translate into what we hear as a sound wave? The energy in a sound wave has to travel over a certain area in a certain amount of time. We detect sounds as being louder when we're standing closer to the source and quieter when we're standing further away. The amount of energy we detect is known as the intensity. Intensity is measured in units of energy over the area and time. In other words, it's the amount of energy that is carried over a certain area in a certain amount of time. We describe different levels of intensity using the decibel scale, a logarithmic scale for measuring the intensity of sound waves. Normal conversation generally falls around 60 decibels. A whisper is more like 20 decibels, while a vacuum cleaner runs as loud as 80 decibels. You may be more familiar with decibels as a measure of volume. When talking about sound waves, the volume is the perception of loudness from the intensity of a sound wave. The higher the intensity of a sound, the louder it is perceived in our ears, and the higher the volume it has. Since intensity is a function of energy, and energy is related to amplitude, then we can make the conclusion that the volume of a sound is proportional to the amplitude of the sound wave. It was a little tough trying to visualize the amplitude of sound waves. Because sound is a longitudinal wave, we don't get the nice up and down wave shape that makes it so easy to see the parameters. We figured out a way to see the amplitude of sound, but what about the period and frequency? Is there a way to see the parameters that are related to time? Let's say a sound wave is traveling toward a microphone. The microphone picks up compressions and rarefactions as the wave passes by. When a compression hits the microphone, it receives a high amount of air pressure from the particles in that space. During a rarefaction, the air pressure is very low. Over time, the microphone experiences ups and downs in pressure, which we can illustrate as an up and down wave like this. It looks like a transverse wave, doesn't it? But it's really a plot of pressure over time, showing us the periods between successive compressions of the wave. If we take the reciprocal of the period, we can find the frequency. This sound wave has a frequency of 262 Hertz. So what does it mean when we describe waves as having a certain hertz? Sure, we know it refers to the frequency of a wave. A wave of 262 Hertz has 262 wave cycles passing by every second. A wave of 440 Hertz has 440 cycles a second. But what does that mean for a sound wave? Can we hear the difference in frequencies between two sounds? Let's go back to those two sounds we heard in the beginning. The tone played here has a frequency of 262 Hz, and this tone here has a frequency of 440 Hz. The first one was middle C, and the second was the A above middle C, or concert A. In music, the pitch of a certain note is defined as the perception of frequency. Hearing musical pitch helps us to put different sounds in order from high to low frequency. High-pitched notes have a high frequency, while low-pitched notes have a low frequency. The difference in pitch between middle C and concert A is a difference of 178 Hz. Humans can typically hear sounds as low as 20 Hz and as high as 20,000 Hz. This range is known as the acoustic range of sound. Sounds above 20,000 Hz are considered ultrasound. Dogs, dolphins, and bats can hear sounds in the ultrasonic range. At the other end of the spectrum is the range of infrasound. These are sounds that are too low for us to hear, like the communication calls between whales and elephants. Obviously, we humans only play our music within the acoustic range of sound, between 20 and 20,000 Hz. When you're able to discern a difference between musical pitches, just know that what you really perceive is a difference in the sound wave's frequencies. Sound waves are longitudinal waves that require a medium in which to travel. The medium consists of particles that oscillate within a certain amplitude. The amplitude of a sound wave is a reflection of how much energy is carried, which contributes to the intensity of the sound. Intensity is measured in decibels and is perceived as sound volume. Thus, the volume is proportional to the amplitude of the sound wave. The frequency of a sound wave is perceived as pitch. Humans can detect pitches within the acoustic range of 20 to 20,000 Hz, but we can't detect ultrasound or infrasound. We can hear changes in frequencies of musical notes, which we describe as being changes in pitch. When we hear sounds, we describe them based on the pitches and volumes that we perceive. These entities are simply our perceptions of the frequencies and amplitudes of sound waves. We previously learned a lot about the structure and nature of waves. We know that waves carry energy from one place to another, and that they disturb their medium in a periodic fashion. Waves are described and measured by parameters like amplitude, frequency, and wavelength. We can see waves in water and hear waves as sound, but we haven't yet discussed the waves that we perceive as light. Visible light is only a small part of a group of waves we call electromagnetic waves. To learn more about light, we'll first have to understand the electromagnetic spectrum. The electromagnetic spectrum describes a wide range of different electromagnetic waves. Also called EM waves, these are a special type of wave that can travel without a medium. Unlike sound waves and water waves, electromagnetic waves don't need a fluid or a solid or even air to help them travel from one place to another. EM waves can travel across the great vacuum of space, which is why we see light from distant stars and planets. Electromagnetic waves are named for the fact that they have both an electric and a magnetic component. They begin when charged particles, like electrons, vibrate due to the various forces acting on them. The vibration of charged particles results in an emission of energy known as electromagnetic radiation. EM waves propagate outward from the source. Just like regular transverse waves, the oscillations of EM waves are perpendicular to the direction of the wave's travel. But EM waves are more complicated. The electric component oscillates in one plane, while the magnetic component oscillates in a different plane. In a vacuum, EM waves always travel at the same speed, the speed of light, which is roughly 300 million meters per second. We call this value the speed of light, but really it counts as the normal speed for all of the EM waves. So what are the other EM waves besides light? Electromagnetic waves include infrared, ultraviolet, radio waves, and microwaves. They also include X-rays and gamma rays. You've probably heard of all these waves before, but you may not have seen how they relate to visible light. Let's take a look at how these 7 groups of waves fit together on the electromagnetic spectrum. The EM spectrum is the range of all possible frequencies of electromagnetic waves. At one end of the spectrum are the waves with the lowest frequencies. At the other end are the highest frequency waves. The spectrum is broken up into regions that define each of the different wave types. At the lowest frequencies, we have radio waves. Then, as we increase frequency, we encounter the microwaves, infrared radiation, and visible light waves. Moving further up the spectrum, we have ultraviolet radiation, X-rays, and gamma rays. Gamma rays have the highest frequencies of all the EM waves. Electromagnetic waves can also be distinguished by their wavelength. Wavelengths for EM waves can be found by dividing the speed of light by the wave's frequency. This is a modification of the wave equation. Since all EM waves travel at the speed of light, then the spectrum of wavelengths is exactly opposite the spectrum of frequencies. In other words, wavelength and frequency are inversely proportional to each other. We can view our electromagnetic spectrum not only in terms of increasing frequencies, but also in terms of decreasing wavelengths. As frequencies increase on the EM spectrum, wavelengths decrease. So that means radio waves have the largest wavelengths and gamma rays have the smallest. To help you associate these relationships across the spectrum, try to imagine a continuous wave with gradual changes throughout. The wave begins with very wide arcs, indicating the large wavelengths and low frequencies of radio waves. As the wave moves along the spectrum, the crests and troughs get closer together. By the end, the arcs are so close together you can barely see between them. This represents the high frequencies and small wavelengths of our gamma rays at the end of the spectrum. Electromagnetic waves are tough things to imagine. I mean, it's not like we can actually see or feel them as we can water and sound waves. Where does electromagnetic radiation come from? We already said it originates from the vibration of charged particles, but what does that really mean? What are the sources of those charged particles? Radiation in the visible light range comes mostly from the sun. Light bulbs, burning flames, and certain animals can also be sources of visible light. Infrared radiates from the sun and other warm things like people, electrical appliances, and distant galaxies. Most microwaves that we know about come from devices that we have invented to generate them, but there are microwaves coming from the sun and from the universe in general. Stars and lightning are natural sources of radio waves, but these are also produced by the antenna on a radio transmitter. On the other side of the spectrum, we have ultraviolet radiation, which is emitted by black lights and fluorescent lamps. Of course, the main source of UV rays is the sun, which is also a major source of X-rays. Both X-rays and gamma rays can be made by machines used in diagnostic imaging, but gamma rays come naturally from the decay of radioisotopes. You can see that in general, all of the electromagnetic waves are emitted from objects in space, and all of them can be produced by our technology. At the end of the day, though, the narrow band of visible light remains the only region of the spectrum that we can actually see. EM waves originate from the vibration of charged particles, and unlike other waves, they can travel without a medium. The vast range of frequencies for EM waves is described by the electromagnetic spectrum. The spectrum stretches from the lowest frequency radio waves to the highest frequency gamma rays. We can also describe the EM spectrum in terms of relative wavelengths. The size of the wavelength decreases continuously from radio waves to gamma rays. Different wave types originate from different sources, but most of them are emitted from objects found in outer space. Humans have developed a wide range of technology to produce electromagnetic waves. These machines are used in medicine, communication, and general convenience. In previous lessons, we've learned about waves and their basic properties, including the very intriguing electromagnetic waves. EM waves originate from the vibration of charged particles, and they can travel without a medium. The electromagnetic spectrum describes the vast range of frequencies from the lowest frequency radio waves to the highest frequency gamma rays. Now that we have a feel for how the EM spectrum works, we need to take a closer look at each separate region. Let's start with the radio waves and work our way up the spectrum. The lowest frequency waves on our EM spectrum are the radio waves. These are the waves that television and radio stations use to transmit data. By exciting the electrons on a conducting antenna, these stations create radio waves that can be received by other devices. The data is created by modulating the parameters of the oscillations, for instance by changing the amplitude and the wavelength. Radio waves have the longest wavelengths, ranging from about 1 millimeter to hundreds of meters. After radio waves come the microwaves. These, of course, are the waves used to heat your food in a microwave oven. They do this by rotating the molecules inside your food, which increases its thermal energy. Unlike regular ovens, microwave ovens do not actually transfer heat to your food. They heat the food directly by exciting the molecules. Microwaves are also used in Wi-Fi technology, but only at low intensities. Infrared radiation is the next region on the electromagnetic spectrum. We call it infrared because it's just below the red part of the visible spectrum. It spans from frequencies of about 300 gigahertz to about 400 terahertz. This is the same as a range of wavelengths from 1 millimeter to 750 nanometers. Infrared radiation is emitted by things that are warm or hot, including animals and people. We can see radiation in the infrared range only by using special technology. We often use infrared photography to capture thermal images in the dark. Some animals can see in the infrared range, which allows them to accurately locate their prey. For example, a snake can use infrared vision to locate a warm mouse hiding in a grassy field. Mosquitoes can literally see the warm parts of your skin. This helps them pick out the best places to suck your blood. The region of visible light waves is pretty small compared to most other regions. This part of the spectrum is defined as the range of light frequencies to which the human eye is most sensitive. Visible light spans from about 760 to 380 nanometers. At the low frequency end, we perceive the light as red. The full spectrum of visible color spans through this range until we get to the other end, which we see as violet. We're going to talk more about colors in light in another lesson, so we won't worry about the exact parameters right now. This is probably a good time to point out that the EM spectrum regions do overlap a little. For example, some of the low-frequency infrared waves can also be considered microwaves, while some of the higher infrared waves overlap with the visible light range. Just like the colors green and blue blend into one another on the visible light spectrum, the ranges for each type of wave blend into one another on the electromagnetic spectrum. Scientists have generally classified waves based on how their radiation affects matter. For example, microwaves make molecules rotate, while infrared radiation makes molecules vibrate. In the overlap between microwaves and infrared, you might see properties of both. But let's not worry about the molecular effects of EM waves right now. We first need to make sure we know the rest of the EM spectrum. After the visible light range comes the ultraviolet light. Ultraviolet is also called UV radiation. You're probably most familiar with UV rays as the source of sunburn and other skin damage that results from exposure to the sun. Most of the sun's harmful UV rays are absorbed by the gases in the Earth's atmosphere. But the UV radiation that does get through can get into our skin cells and break the chemical bonds in DNA. Damage to DNA often results in mutations, which can lead to serious problems like skin cancer. X-rays come after UV radiation. X-rays are really interesting because they can pass through substances in a way that allows us to use them for diagnostic imaging. If you've ever had an X-ray done at the doctor's office, then you know what this looks like. The X-ray films that doctors look at are actually called radiographs. We can't see X-rays with our eyes, but we can use them to create images of the insides of structures. X-rays pass through soft tissue quite easily, but not so well through bone. By looking at how the X-rays pass through the different tissues in your body, your doctor can get an idea of what's going on inside and hopefully let you know if you have a broken bone. The last region on the electromagnetic spectrum is the gamma rays. The waves that live in the gamma ray section have the highest frequencies and the smallest wavelengths of all the EM waves. In fact, there is no lower limit to the wavelength of a gamma ray. Some have wavelengths that are smaller than an atom. Gamma rays are emitted naturally from things undergoing radioactive decay. Because gamma rays cause damage to cells and DNA, scientists have to be very careful about producing them. But we do use gamma rays to sterilize food and medical equipment using a process called irradiation. We also use gamma rays to take PET scans for diagnostic imaging and for radiation therapy in cancer treatment. Gamma rays, visible light, and radio waves are all forms of electromagnetic waves. The electromagnetic spectrum begins with the lowest frequency radio waves, then moves up in frequency and down in wavelength. After radio waves come microwaves, followed by infrared radiation and visible light. The visible light range is right in the middle of the EM spectrum. Moving toward the opposite end, we have ultraviolet waves and X-rays, and we end with the highest frequency gamma rays. While scientists do break up the spectrum into the groups that we've described, keep in mind that the groups overlap, so that all regions of the spectrum blend together at their boundaries.
Have you ever wondered if other people see colors the same way you do? If you say that your shirt is blue, and your friends say that your shirt is blue, are they really seeing the same blue that you are? And what about different varieties of blue? Some blues have more of a greenish tinge, while others look more violet. One of your friends might call your shirt teal, while another might call it aquamarine. How do we perceive different colors and distinguish between them? To answer these questions, we'll have to learn more about the visible light spectrum. The visible light spectrum is a very small part of our giant electromagnetic spectrum. The EM spectrum consists of 7 different regions, including X-rays, infrared, and ultraviolet light. The electromagnetic waves that we can see are confined to this small area called the visible light region. This part of the spectrum is the range of light frequencies to which the human eye is most sensitive. Visible light shares many characteristics with the other EM waves because it too is a type of electromagnetic radiation. All electromagnetic waves originate from the vibration of charged particles. These charged particles come from a variety of sources, like the sun, other stars, and warm objects like light bulbs and animals. Any source of EM radiation that we can see, like the light from the sun, is considered visible light. So other sources of visible light would be flames, red-hot metal, and the glowing screen on your cell phone. Our ability to see everyday objects is due to the reflection of light from the surfaces of those objects. For example, the reason you can see your car in your driveway is because the sunlight is reflecting off of it. Your car may be getting very warm in the sun, and it may be giving off infrared radiation because of that warmth, but that's not a form of radiation you can see. You can only see the waves in the visible light region. Recall that regions in the EM spectrum are distinguished by their ranges in wavelength as well as frequency. EM waves with a large wavelength have a low frequency, and waves with a small wavelength have a high frequency. Visible light spans from about 760 to 380 nanometers in wavelength, which is the same as about 430 terahertz to about 750 terahertz. The low frequency end corresponds to light that we perceive as the color red. The high frequency end is related to light that we see as violet. EM waves that are just below the red spectrum are called infrared. These are the waves that have a frequency of less than 300 terahertz or more than 1000 nanometers. We can't see these waves, but we can detect them as heat. At the other end, above the limit for violet light, is the ultraviolet spectrum. Ultraviolet waves have a frequency of more than 1000 terahertz or a wavelength of less than 300 nanometers. We can't see ultraviolet light either, but we can certainly tell when our skin has been burned by UV exposure. So, we know the lower frequency limit for red, we know the upper frequency limit for violet, but what happens in between those limits? Where do red and violet transition to the other colors in our visible light spectrum? Red light spans up to about 480 terahertz or 635 nanometers, at which point it transitions into orange. Orange light spans up to 510 terahertz or 590 nanometers, and yellow light spans up to 540 terahertz or 560 nanometers. Do you see how the wavelengths are dropping lower as we increase in value for frequency? That's because for EM waves, wavelength is inversely proportional to frequency. You've seen this on the larger scale of the entire EM spectrum, but it holds true for the tinier bands of colored light on the visible light spectrum. Green light comes after yellow, and it spans up to 610 terahertz or 490 nanometers. Then it transitions to blue until 670 terahertz or 450 nanometers. Violet comes last, ending around 750 terahertz or 400 nanometers, after which it switches to the ultraviolet light range. It's important to note that the colors we're describing here would be produced by a single frequency of light. For example, light with a frequency of 650 terahertz would look blue. We would call this blue a pure spectral color because it is only produced by a single frequency or a single wavelength of visible light. Each different frequency on the blue color range would produce a slightly different shade of blue, so that at some point the color of light would look green or violet. The point of transition is something that scientists approximate based on how people perceive the frequencies. So you know those frequency ranges that I gave you? Well, they're not exactly definite rules. The pure spectral colors form a continuous spectrum, just like the regions of EM waves form a continuous EM spectrum. There's no official cutoff mark for any of the colors, so while blue is typically classified as lying between 610 and 670 terahertz, you'll find some people that identify blue at higher frequencies. Now, what happens if you detected more than one frequency of light at a time? What if you saw a mixture of many different visible light frequencies? Well, the frequencies would mix together to produce white light. In fact, this is the kind of light we most commonly see, like the visible light from the sun and our household light bulbs. White light is a mixture of all light frequencies in the visible light spectrum. We'll talk more about white light in a later lesson, but for now, just remember that white is not a pure spectral color. And that makes sense, right? Because you've never seen a band of white color inside the layout for the visible light spectrum. Because the visible colors exist on a continuous spectrum, we find a lot of variation in how people identify colors. You may see a shirt and call it greenish blue, while your friend sees the same shirt and calls it bluish green. But keep in mind that people do perceive colors the same way. The frequency of light coming to your eyes from the shirt is the same as the frequency going to your friend's eyes. Unless one of you is color deficient or colorblind, both of you will perceive the same color of light. But naming the color is a different story. We rely on a lot of cultural trends that teach us to identify certain colors certain ways. We also change our minds about how to name colors over the course of history. So we'll never be able to agree completely on how to name our colors, but at the end of the day, we're all seeing the same colors with our eyes. All of the color frequencies together make up the visible light spectrum. Visible light is one form of electromagnetic radiation, and it makes up a small part of the electromagnetic spectrum. Like all EM waves, visible light originates from the vibration of charged particles, such as those from the sun and other radiation sources. A specific range of frequencies makes up the visible light spectrum. Each frequency produces a different pure spectral color. We can divide the full range of spectral colors into 6 main groups: red, orange, yellow, green, blue, and violet. White light is a mixture of all the color frequencies. The way that people classify the colors can vary across cultures and the course of history. So while everyone perceives the spectral colors the same, not everyone divides the ranges of colors the same way.
When I was little, I liked to look at reflections of myself. I would make goofy faces in the mirror or dance around in front of a car window. I thought it was really fun to see how surfaces could reflect my childish antics. But the first time I saw my reflection in a spoon, I was amazed. Looking at the spoon's inner surface, I saw my image reflected both upside down and backwards. Back then, I didn't understand why the reflection of my face appeared that way, but now I know that the image I saw was the result of basic principles that govern the reflection of waves. Wave reflection always works the same way, whether the wave is a light wave, a sound wave, or a water wave. It describes a change in the direction of a wave when it strikes a surface. In talking about reflection and some other wave properties, it's helpful to think of a wave as a ray, a straight line through space that indicates the path of a wave. For example, we know that a light wave from the sun travels in a straight line toward the Earth. Because it's an electromagnetic wave, we could think of it as having the typical wave-like up and down shape, but we can also think of it like a straight line ray. A ray of sunlight is an appropriate concept for how we should think of waves in reflection. So from now on, in this lesson, we'll refer to all our waves as rays. Think about a single ray of sunlight. The ray that initially comes down from the sun is called the incident ray. This is really the term we use for any ray that approaches a reflective surface. The Earth isn't the best example for reflection, so let's say that we've got a mirror here instead. The incident ray comes in and strikes the mirror at a certain angle. Then it bounces off the mirror and proceeds in another direction. The ray that travels away from the reflective surface is called the reflected ray. Incident and reflected rays are related to one another in that the angle of the reflected ray matches that of the incident ray. To visualize this, think about a typical pool table. Say you're playing a game of pool and you're trying to get the 5 ball into this side pocket. You'd have to hit the ball at an angle so that it would bounce off the opposite rail and roll into the pocket. If the ball hits the rail at too shallow an angle, it will end up too far to the left. If the ball hits the rail at too wide an angle, it will end up too far to the right. The ball will always bounce off the rail so that the angle at which it approaches the rail equals the angle at which it bounces off the rail. This principle is known as the law of reflection. The law of reflection tells us in very clear terms the relationship between the angles of our incident and reflected rays. To define these angles, we first identify the normal, the imaginary line that is perpendicular to the reflective surface. When the incident ray strikes the surface, it creates an angle with the normal, which we call the angle of incidence. The angle of incidence measures the position of the incident ray in relation to the normal. Notice that the angle of incidence is not the angle between the incident ray and the surface, it's the angle between the incident ray and the normal. Just like our incident ray makes an angle of incidence, our reflected ray makes an angle of reflection. This angle measures the position of the reflected ray in relation to the normal. According to the law of reflection, the angle of incidence is equal to the angle of reflection. That means that if our light ray hits a mirror with a 15-degree angle of incidence, it will reflect off the mirror with a 15-degree angle of reflection. If it strikes the mirror at 70 degrees, then it reflects off the mirror at 70 degrees. It's very similar to our example with the pool table. The angle at which a wave strikes the surface equals the angle at which it reflects off the surface. The examples that we've seen so far have all involved surfaces that are flat. A regular mirror is flat and the rails on a pool table are flat. But what if you have a curved surface, like a doorknob, a funhouse mirror, or the inside of a spoon? How do waves reflect off of surfaces that are curved? The law of reflection still applies for curved surfaces, but the normal on a curved surface is different depending on where the ray strikes. You have to think of one curved surface as sort of a combination of tiny flat surfaces. Each little piece of the curve has its own unique normal. An incident ray striking here, for example, will end up reflecting over here, but an incident ray striking here will reflect way over here. Do you see how the reflected rays cross over one another? That's what happens when straight-line waves strike different parts of a curved surface. The law of reflection applies throughout a curved surface, even as the direction of the normal line varies. If you look at your own reflection on the inside of a spoon, you'll end up seeing an image that is upside down and backwards. The incident rays from the top of your head will be reflected towards the bottom. The incident rays from your chin will be reflected towards the top. Because the spoon is curved from top to bottom, your reflection appears upside down. But the spoon is also curved from one side to the other. So incident rays from one side of your face are reflected on the other side. Try it and see. You can stick out your tongue on the left side and you'll see it reflected on the right. The law of reflection explains why we see the images that we do in all types of reflective surfaces. The reflection of waves describes a change in the direction of waves when they strike a surface. We refer to these waves in terms of the incident ray that strikes a surface and the reflected ray that bounces off a surface. Perpendicular to this surface is the imaginary normal, a line which we use to measure the angle of incidence and the angle of reflection. According to the law of reflection, the wave's angle of reflection is equal to the wave's angle of incidence. This law applies to curved surfaces as well as those that are flat or straight. Because the law applies throughout a curved surface as the normal line varies, we can see strange, distorted reflections in curved objects like funhouse mirrors and silver spoons. Every time I go to the beach, I'm fascinated by all of the colored pebbles I find. Tiny stones of pink, yellow, blue, and violet flash under the shallow waves. I can't resist the urge to collect them, and I usually go home with a pocket full of my favorite pebbles. But once I get them washed and dried, I'm often disappointed with how dull they all appear. Where did their vibrant colors go? What happened to their glossy sheens? I should have known from the beginning that the dry pebbles would look different because of the effects of diffuse reflection. We've already learned that the reflection of waves involves a change in the direction of waves when they strike a surface. When talking about reflection, we think of waves as straight-line rays. The incident ray is the ray that initially strikes a surface. The reflected ray, obviously, is the one that reflects off a surface. The law of reflection tells us that the angle of reflection is equal to the angle of incidence. In other words, the angle at which the incident ray strikes the surface is going to be the same as the angle at which it reflects. Rays and angles are convenient ways to talk about single waves, but sources of sound and light typically send out many waves at once. How do we talk about the law of reflection when more than one wave is involved? All we have to do is imagine a whole bunch of rays parallel to one another. This picture here could represent a concentrated beam of light waves, say from a flashlight. Since each ray is hitting the surface at the same angle, the angle of incidence, then each ray reflects at the same angle, the angle of reflection. A person standing in the path of the reflected rays would see a perfect image of the flashlight's beam. It wouldn't be much different from staring into the flashlight itself. This type of reflection, in which a smooth surface causes reflected rays to travel in the same direction, is called specular reflection. Specular reflection is best known as the type of reflection you get from a mirror. It also occurs off of other smooth surfaces like glossy tabletops, car windows, and very still water. Specular reflection from a calm lake occurs because the surface is so flat that all the reflected rays bounce off in the same direction. But if a gust of wind disturbed the water, the resulting ripples would cause a different phenomenon called diffuse reflection. Diffuse reflection occurs when a rough surface causes reflected rays to travel in different directions. Most everyday objects exhibit diffuse reflection because of the tiny imperfections on the surface of the material. A piece of paper may look smooth on the surface, but at the microscopic level, the tiny fibers make it rough. Upholstery and clothing exhibit diffuse reflection because of the minute roughness of the fabric. Even a leaf has an element of roughness to it because of the multidimensional nature of the cells on the surface. In diffuse reflection, each individual ray strikes a part of the surface that is oriented in a different direction. The law of reflection still applies, but the normal is different for each ray, so the reflected rays end up going in all directions. This incident ray reflects over in this direction, this incident ray reflects here, and this one reflects way over here. The effect of all these rays going everywhere is that all of the waves are spread out. Diffuse reflection is the reason why you don't see your image reflected in most everyday objects. People who design auditoriums and recording studios are big fans of diffuse reflection. Imagine you're sitting in an auditorium listening to someone play a trumpet. If the auditorium walls are smooth, the sound waves from the trumpet will bounce off the walls with specular reflection. If you're sitting in the right spot, you'll get a blast of intense sound waves as the reflected rays all hit you at once. If you move a few rows back, you might perceive the trumpet as sounding very soft. Specular reflection in an auditorium is not a good thing because different people hear different things depending on where they sit. In order to break up the focus of the sound, people often use acoustic diffusers. These are wall and ceiling treatments that spread out sound waves by causing diffuse reflection. By engineering different shapes and angles into the walls, we can break up what would normally be specular reflections. Spreading out the sound waves results in a fuller, more uniform sound over the entire acoustic space. You'll often see diffusers inside recording studios and church sanctuaries. This is because diffuse reflection of sound waves sounds much better. We already saw how the specular reflection of light waves works. When a beam of light rays reflects off a smooth surface, the reflected rays are also seen as a beam of light. If the surface is rough, then it causes diffuse reflection of the light waves. But sometimes a rough surface is made smooth because a layer of liquid covers up the imperfections. Rainwater coating a road is one example. Normally, an asphalt road exhibits diffuse reflection because of the irregular materials making up its surface. During a rainstorm, water builds up in the cracks and crevices. If enough water collects on the road, then it will actually cover the asphalt with a thin, smooth layer. The result will be the specular reflection that you see when driving on rainy days. Rain coating causes nasty glares and reflections of distant headlamps and streetlights. This is why driving on wet roadways is especially challenging at night. The appearance of colored seashells and pebbles also changes when they're wet. These natural materials are somewhat rough at the microscopic level, even if they have been worn smooth by the elements. When I find my favorite pebbles at the beach, they're always richly colored because they're sitting in the ocean waves. The water coats the pebbles' imperfections, making them appear smooth and vibrant. But after my pebbles have dried off, they don't look nearly as good. Perhaps this is why we like to polish our most beautiful rock and mineral specimens. We want to appreciate the shapes and the colors of the rock, whether the surface is wet or dry. Polishing the surfaces of rocks and minerals reduces diffuse reflections so that we can see their true colors. The law of reflection states that for any wave striking a surface, the angle of reflection will be equal to the angle of incidence. This law remains true whether the surface is rough or smooth. If the surface is smooth, then all incident rays coming from the same direction will also reflect in the same direction. This is called specular reflection. If the surface is rough, then the rays will reflect in many different directions, in what is called diffuse reflection. Diffuse reflection of sound waves is preferable in auditoriums and studios, where it provides more uniform acoustics than specular reflection. Diffuse reflection is also preferable when driving a car at night. Specular reflection caused by rainwater can create disorienting glare. On the other hand, specular reflection looks better on colored stones, which are usually made to look dull by the effects of diffuse reflection.
How do people make beautiful music with wine glasses? How do you break a wine glass by singing loudly in front of it? Sound waves allow us to do some pretty neat things when we know how to use them. Light waves, too, interact in special waves with the objects around them. The behavior of sound and light waves explains why we hear sounds from musical instruments and why we see color in objects. A trumpet increases the amplitude of a sound wave. A colored object increases the amplitude of a light wave. These changes in amplitude are caused by an important principle called resonance. In this lesson, we'll talk about resonance and how it affects the transmission of sound and light. We already know that waves originate from vibrations. Sound waves come from mechanical vibrations in solids, liquids, and gases. Light waves come from the vibration of charged particles. Objects, charged particles, and mechanical systems usually have a certain frequency at which they tend to vibrate. This is called their resonant frequency or their natural frequency. Some objects have 2 or more resonant frequencies. You know when you drive on a bumpy road and your car begins to bounce up and down? Your car is oscillating at its resonant frequency, or really the resonant frequency of the shock absorbers. You may notice that when you're riding in a bus, the bouncing frequency is a little bit slower. That's because the bus's shock absorbers have a lower resonant frequency. When a sound or light wave strikes an object, it is already vibrating at some particular frequency. If that frequency happens to match the resonant frequency of the object it's hitting, then you'll get what's called resonance. Resonance occurs when the amplitude of an object's oscillations are increased by the matching vibrations of another object. This relationship is difficult to imagine without an example, so let's explore the subject of resonance further in the context of light waves. Let's take a typical light wave. We'll say it's a stream of white light that comes from the sun. And let's take a dark object, like a western rat snake, slithering through your yard. The molecules in the snake's skin have a set of resonant frequencies. That is, the electrons in the atoms tend to vibrate at certain frequencies. The light coming down from the sun is white light, so it has not just one, but many wave frequencies. It has frequencies of red and green, blue and yellow, orange and violet. Each of these frequencies strikes the snake's skin, and each frequency makes a different electron vibrate. The yellow frequency resonates with the electrons whose resonant frequency is yellow. The blue frequency resonates with the electrons whose resonant frequency is blue. So the snake's skin as a whole resonates with the sunlight. When light waves resonate with an object, they cause the electrons to vibrate with high amplitudes. The light energy is absorbed by the object, and we don't see that light coming back to us at all. The object appears black. Since a western rat snake absorbs all the frequencies of sunlight, then it appears as a black snake. What if an object does not absorb any of the sunlight? What if none of its electrons resonate with the light frequencies? If resonance does not occur, then what you'll get is transmission, the passing of light waves through an object. The light still causes vibrations of the electrons, but because it doesn't match the electrons' resonant frequencies, the vibrations are very small and they pass from atom to atom all the way through the object. An object with no resonance would exhibit 0 absorption and 100% transmission. So the object in this case wouldn't be white, it would be clear, like glass or water. We'll talk more about transmission and absorption in a later lesson. For now, let's switch gears and talk about how resonance works in sound waves. Resonance for sound works the same as it does for light. When one object is vibrating at the resonant frequency of a second object, then the first object causes the second one to vibrate with a high amplitude. Let's say you're going to play the trumpet. You press your lips to the trumpet's mouthpiece and you get your fingers ready. When you play, your lips vibrate against the mouthpiece, creating a whole bunch of low amplitude sound waves at many different frequencies. The sounds from your lips are very soft, so nobody really hears them. But one of those frequencies you're producing will resonate with the air molecules inside the trumpet. When you set your fingers to play one note, you created a column of air that measures a certain length and width. This air column has its own resonant frequency, and it matches one of the frequencies that are coming from your lips. The energy from your vibrations is absorbed by the air column. It is amplified by the air column, and it makes a loud sound. If you change your fingering, the column resets, and now you have a different resonant frequency to match. Resonance causes the amplitude of that frequency to increase so much that people hear a loud, single-frequency sound from your trumpet. That sound is only one of many frequencies that you're producing, but it's the only one we hear because it's the only one that is amplified by its resonance with the air column. Have you ever tried making a wine glass sing? You can do this just by wetting your finger and sliding it around the rim of the glass. The motion causes small vibrations because your finger is actually sticking and slipping on the glass in an alternating pattern. The slip-stick effect creates many frequencies of sound waves, one of which will resonate with the wine glass itself. A clear, ringing tone comes out of the glass, a sound which is the same as the glass's resonant frequency. Some people can use these tones to create beautiful music. Now, if you want to, you can try breaking the glass with your voice. Just find the resonant frequency, sing the note as loudly and clearly as you can, and wait for the wine glass to break apart. The high amplitude vibrations you create with your voice will cause even higher vibrations in the glass. At some point, the glass will be vibrating so much it won't be able to keep its shape. The vibrations will deform the glass to the point of breakage, and you can impress your friends with your talents. Just make sure you pick up the broken glass afterward. The principle of resonance affects how we perceive sound and light waves. All objects possess a natural or resonant frequency at which they tend to vibrate. When vibrations from one object match the resonant frequency of another object, the two are said to resonate because the first object amplifies the vibrations of the second object. Resonance in light waves results in absorption of the light frequency. When no resonance is present, then the light is transmitted through the object. For sound waves, resonance results in a loud sound that matches the resonant frequency of the instrument. Resonance in either case is always caused because one object vibrates at the resonant frequency of another.
What happens to light waves when they encounter objects? Do they go through the objects? Do they bounce off the objects? When a light wave strikes the surface of an object, a variety of things can happen. One of these things is called resonance. When resonance occurs between a light wave and an object, the object absorbs the energy of that light wave. The light energy stays inside the object when resonance occurs. But what about when resonance does not occur? What happens to light waves that are reflected off the object or transmitted through the object? In this lesson, we're going to study light waves a little further in order to understand transparency and opacity. An object is said to be transparent when light passes through it without being dispersed or scattered. Clear glass is transparent and clean water is transparent. Although light travels through these materials, we know that they also block things like wind, sound waves, and the movements of people and animals. For example, you can't walk through glass, so how can a light wave pass through the glass without being changed at all? Light waves are absorbed by an object when the frequency of the light wave matches the resonant frequency of the object. Absorption occurs when none of the light waves are transmitted through the object. Transmission, if you weren't sure, just means the passing of electromagnetic waves through a material. In the case of objects that are transparent, all of the light waves pass through. Transparent objects exhibit complete transmission of the light waves through the object. What really happens inside glass materials when a light wave passes through? We know that there aren't any tunnels connecting one side to the other, so what's going on? When a light wave strikes the surface of the glass, it sets the electrons vibrating at a certain frequency. This frequency is not the resonant frequency of the glass. The vibrations pass from the surface atoms to the neighboring atoms and then on to more atoms through the bulk of the glass. The frequency doesn't change when the vibrations pass from one atom to another. Once this energy gets to the other side of the glass, it is re-emitted from the opposite surface. The light wave effectively passes through the glass unchanged. As a result, we can see straight through the glass, almost as though it isn't even there. So now you know, transparency occurs because of the transmission of light waves through the bulk of an object. What about objects that are translucent? What's happening when light is scattered as it passes through an object? The scattering of light is related to a subject called refraction, but we won't be discussing that in this lesson. We're going to talk about opaque materials next. So we've learned that light waves are absorbed when they resonate with an object. They're transmitted when they pass through the atoms of an object. But what if a light wave does neither of these things? When a light wave is neither absorbed nor transmitted by an object, then it is reflected. Reflection is a change in the direction of a wave when it strikes a surface. Reflection can be specular, as in glossy or smooth surface objects, or it can be diffuse, as in objects with rough surfaces. In either case, reflection occurs because the vibrations of the surface electrons do not pass their energy down through the material. Instead, they vibrate a little bit and then re-emit the energy back away from the material. When this happens, the object appears to us as opaque. Opaque materials do not allow transmission of light waves. In other words, we can't see through an opaque object. We can only see the surface because the light waves are re-emitted from the surface back to our eyes. Opacity occurs because of the reflection of light waves off the surface of an object. Now I bet you're wondering, what about the different colors of opaque materials? Why does my car look red when my friend's car looks blue? Well, again, you're going to have to hold that thought. Color is related to the selective absorption of different wavelengths of visible light. For now, just keep your mind on transparency and opacity, whether or not we can see through an object or material. Transparency and opacity are easy enough to understand in the context of visible light. We can see the results of it, can't we? We can see when an object is transparent to a light wave. We can tell when something is opaque. But the principles of transparency and opacity apply to all the electromagnetic waves. Visible light, remember, is just one of those types. So here's a question. If glass is transparent to visible light waves, does that mean it's transparent to the other EM waves? The answer, surprisingly, is no. Transmission and reflection happen differently for every type of wave, so the rules about which objects are transparent and opaque also change. Glass is transparent to visible light, but opaque to infrared. Silicon is transparent to infrared, but opaque to visible light. What does this mean? It means that if your eyes were designed to pick up radiation in the infrared range, then you would be able to see through silicon, and you would not be able to see through glass. Weird! You may already have a sense of what is transparent or opaque to different kinds of waves. How do you protect your skin from the harsh UV rays of the sun? By wearing sunscreen, of course. Sunscreen is opaque to ultraviolet light, but it's transparent to visible light. This is why you can still see your skin when you're wearing it. X-rays follow different rules. Materials like skin and blood are transparent to X-rays, but bone and metal are not. This is why we can see bone and metallic objects in contrast to skin and soft tissue in radiographic images. The transparencies and opacities of the different EM waves dictate how we use modern technology and materials. Radio waves pass through brick walls, but not through steel. Gamma rays pass through outer space, but not through our atmosphere. Just imagine the strange things you would see if you could perceive light in the other regions of the electromagnetic spectrum. What if you could see through the walls of a building and still be unable to see the skin of your hand? In the end, I guess I'm glad that I can only see with visible light. The transparency and opacity of objects depends on how light waves interact with the materials of those objects. Light waves cause vibrations in surface atoms, which are either absorbed, transmitted, or reflected. Transparency is caused by the transmission of light waves. If the vibrational energy of a light wave is passed through the object, then the object appears clear or transparent. If the energy only causes vibrations in the surface before reflecting off the object, then the object appears opaque. Therefore, opacity is caused by the reflection of light waves. While we typically use these terms to describe our perceptions in the visible light range, they also describe interactions in the other regions throughout the EM spectrum. Materials that are opaque to one type of wave may be transparent to another type. Therefore, transparency and opacity are relative terms that vary by region of the electromagnetic spectrum. What makes a plant green? What gives a male cardinal his bright red feathers? Why is an orange, well, orange? All of the colors in the visible light spectrum are characterized by different frequencies. Green-colored light lives between 540 and 610 terahertz. For red, the frequencies are a bit lower. For violet, they are higher. But what determines the color of an object? How do the frequencies get divided out between red, green, and violet objects? To answer these questions, we first need to look into the mysteries of white light. If you pass a beam of white light through a prism, you will see the light split into the colors of the rainbow. There's red, orange, yellow, green, blue, and violet all spread out. You can also see a rainbow when sunlight passes through a crystal decoration or even the peephole in your front door. Sunlight and other white lights are actually made of many different frequencies. The sun emits infrared and ultraviolet waves in addition to the full spectrum of visible light. We don't see the infrared and UV waves, but we do see the full range of visible color all bundled together in the form of white light. White light is the combination of many different frequencies of visible light from all parts of the visible spectrum. The only way we can see these frequencies as separate colors is to separate them into a rainbow. So if sunlight is white light and sunlight reflects off of objects like plants and birds and oranges, then why don't we see those objects as white? It turns out that the different color frequencies are absorbed and reflected differently in every different object. Let's learn more about selective absorption and how it relates to color. Let's say you've got a nice ripe orange in your hand. You walk outside and the sunlight beams down on the orange from above. The sunlight is white light, so it contains all the different frequencies in the visible light spectrum. Many different waves of light beam down on the orange, each wave a different frequency. When a light wave strikes any object, it can do one of three things. It can be transmitted, it can be absorbed, or it can be reflected. We know that none of the light waves are transmitted through the orange. If they were, then the orange would appear transparent. Since we can't see through oranges, that means they're opaque, and that means all the light must be reflected or absorbed. Absorption of a light wave occurs through resonance. When the frequency of a light wave matches the resonant frequency of an object, then the object vibrates at that frequency. The energy of the light wave stays in that object as thermal or vibrational energy. In other words, you never see that light wave again. Let's take this one little light wave here, which happens to be the frequency of the color violet. When this violet light wave strikes the orange, there are some molecules in the orange which resonate at that frequency. The violet light wave is absorbed by those molecules, so we never see the violet reflecting off the orange's surface. What about green? When a green light wave strikes the orange, it also resonates with some of the molecules in the skin. It gets absorbed, and so we don't see green either. In fact, most of the frequencies inside the white sunbeam are absorbed by the orange. The only frequency that isn't absorbed is that of the color orange. So what is different about the orange light? Instead of being absorbed into the orange like the other colors, orange light is reflected by the skin of the fruit. In reality, there are a range of frequencies for the color orange. Some waves are more reddish-orange and some are more yellowish. But all those frequencies are reflected together, giving the orange the appearance of being orange. The appearance of color is due to the selective absorption of light waves. Orange wasn't the only color to be beamed down on the fruit, but it was the only color to be reflected. Selective absorption describes the tendency of an object to absorb some frequencies of light more than others. An object that appears a certain color reflects the light frequency that corresponds to that color, and it absorbs all the other frequencies in the visible light spectrum. An orange absorbs all of the frequencies but orange. A banana absorbs all of the frequencies except for yellow. Selective absorption occurs in just about everything that has color. It happens because of the specific properties of the molecules that make up objects. The molecules in red paint are slightly different from the molecules in blue paint. The molecules in red feathers are different from the molecules in blue feathers. In fact, most living things use special chemicals called pigments to make their bodies appear a certain color. A pigment is a chemical that alters the color of a light wave by selectively absorbing one or more light frequencies. The feathers of a male cardinal are made red by special organic pigments called carotenoids. Birds get carotenoids from the plant materials they eat. They can make red, yellow, or orange colors in their feathers this way. Another pigment they use is melanin, the same pigment that colors human skin. Melanin is used to make the blacks, browns, and tans in the feathers of birds and the hair of mammals. Structures that are totally black absorb all of the frequencies of light. In the case of white structures, there are no pigments. So white feathers and white hair appear that way because all frequencies of white light are reflected from their surfaces. One very important biological pigment is the plant pigment chlorophyll. Chlorophyll is what gives plants their green color. More importantly, it's what allows them to absorb the sun's energy and make food through the process of photosynthesis. Chlorophyll is found mostly in the leaves and stems of plants. It absorbs a huge amount of energy from white sunlight. It absorbs the waves in the red frequencies and the blue and the violet, orange, and yellow frequencies. But it doesn't do a great job of absorbing light in the green frequencies. So the green frequencies are reflected instead, and that's why plants look green. The common theme here is that color is not something that exists in objects. We perceive things to be a certain color because of the way our eyes sense the various frequencies of light reflected off of them. Objects that appear red do not contain the color red. They only contain the molecules that affect the visible light waves, so that only red is reflected. Therefore, color is the perception of a visible light wave's frequency. White light is a combination of all the frequencies of visible light. When white light strikes an object, each individual frequency of light is transmitted, reflected, or absorbed, depending on the properties of the surface molecules. If all frequencies are absorbed by the object, then it appears black. If all frequencies are reflected, then it appears white. Selective absorption describes how some frequencies of light are absorbed, while others are reflected. This results in the appearance of color. Pigments are natural or man-made chemicals that give color to objects through selective absorption. While we often describe objects as being a certain color, the truth is that color is only our perception of the light frequencies reflected off of objects. I remember when I was in elementary school, I used to play jump rope with my friends at recess. We sometimes got bored with actually jumping over the rope and just started making waves with it. Each of us would hold one end of the rope and we'd both swing our arms up and down, sending giant waves toward each other down the length of the rope. We noticed that the waves would sort of crash into each other, making the rope jump up and down in crazy patterns. Sometimes, though, we'd get the waves going so that they made a perfect pattern that seemed to stand in one place. Standing waves are intriguing phenomena that occur when two waves interfere with each other. To understand why they happen, let's learn more about how interference really works. Most of the time, when we think about waves, we tend to imagine a single wave traveling through a medium. When we think about water waves, for example, we imagine one wave traveling through the ocean all by itself. But obviously that's unrealistic. When is there ever just one wave traveling through the ocean? There are countless waves traveling north and south, east and west. Some ocean waves are bigger and some are smaller. Some waves are caused by the wind, others are caused by cruise ships, and others by tons of other things. Inevitably, some waves are going to cross over or meet with each other. When they do, the reaction between the waves is known as interference. This is the meeting of two or more waves traveling in the same medium. Waves meeting in the same medium actually disrupt each other's displacement. They interfere with each other so that the resulting wave is a completely new and different wave from either one of the original two. Let's take a look at these two waves. They're traveling toward each other in the same medium. One's traveling left and the other's traveling right. They both have the same amplitude of 1 meter. When the two waves meet up, there comes a moment when the crests of both waves end up in the same spot. Their crests overlap, and so their amplitudes add together. Instead of the crest being 1 meter tall, instead it's 2 meters tall. When the crests or troughs of two interfering waves meet, their amplitudes add together. This principle is known as constructive interference. So what happens when the crest of one wave meets the trough of another wave? Well, the opposite happens, and it's called destructive interference. When the crest and trough of two interfering waves meet, one amplitude subtracts from the other. Let's take our same two waves that we had before. They're still traveling toward each other, and they're still 1 meter in amplitude each. But this time, it just so happens that the crest of this wave lines up with the trough of this wave. Do you know what will happen to the overall amplitude? Well, there won't be any. The crest of the first wave will cancel out the trough of the other wave. The medium experiences zero displacement here. The net result is, at this particular spot, a completely flat surface. Constructive interference describes a situation where two waves are added together, while in destructive interference, the two waves cancel each other out. But really, the two types of interference are a result of the same thing. When two waves interfere with each other, their displacements at any point are added together to produce the displacement of the medium. Let me show you what I mean. We'll take two waves that have the same wavelength. One has an amplitude of 1 meter, the other has an amplitude of 2. Let's say they interfere in such a way that all the crests and troughs line up together. So we'll add up the displacement of both waves at every point, and that will give us the total displacement for the resulting wave when they meet. At point A, both waves have a displacement of 0, so the resulting wave is also 0 right here. At point B, we have a +1 amplitude for the first wave and a +2 amplitude for the second wave. So the amplitude of the resulting wave here would be 3. Now at point C, the waves both are back to neutral, and so is the resulting wave. At point D, we add the -1 amplitude for the trough of the first wave to the -2 amplitude for the trough of the second wave. The result is a sum of -3, meaning that our trough in the resulting wave is 3 meters down. It looks like we got some constructive interference here. Our waves of amplitudes 1 and 2 gave us a resulting wave with a total amplitude of 3. The exercise we just did illustrates the principle of superposition, the basic rule that tells us how to find the resulting wave from the interference of two different waves. You just treat all the crests as positive numbers and all the troughs as negative numbers. Then you add up the displacement of the waves for every point. For two interfering waves, the displacement of the medium at any point is the sum of displacements of the waves at that point. Let's try lining up these waves in a different way. We'll shift our second wave over so that its crest lines up with the trough of the first one. Now at point A, we still have a sum of 0, and the same is true for points C and E. But at point B, the +1 for the first wave is countered by the -2 of the second wave. This shows a little bit of destructive interference, meaning our resulting amplitude is a measly -1. At point D, our -1 trough is countered by the +2 crest, so the amplitude here is +1. As you can see, the principle of superposition helps us find the resulting amplitude for every point along two interfering waves. It's one thing to talk about waves that meet each other in a big open space, like the ocean, but waves can also interfere with themselves when they are reflected off another object. For example, if I'm holding one end of a jump rope and my friend is holding the other, then I can send a wave through the jump rope that will reflect off of my friend's hand and travel back toward me. If I'm still sending more and more waves down, then these will interfere with the waves that are traveling back. Interference occurs between the incident and reflected waves, and it usually looks pretty messy. However, if I time my wave propagation just right, I can get it so that the reflected waves line up perfectly with the incident waves. That is, each reflected wave interferes constructively with an incident wave. The waves double back on each other in such a way that some parts of the medium appear to be perfectly still. This type of phenomenon is called a standing wave. It's called standing because it really looks like it is standing in place instead of traveling along the length of the rope. In reality, the incident and reflected waves are traveling back and forth. They're traveling at just the right frequency to converge on each other and add together through constructive interference. Because there has to be a reflective surface, standing waves only occur in medium that are contained. For example, a guitar string is contained by its attachments to the guitar at both ends. When the string is played, it forms a standing wave between the two stationary ends. Standing waves are also generated in wind instruments like flutes. The ends of the flute act as containers for the medium, which is the column of air inside. The different notes that the flute can play are related to the different types of standing waves that are made within the column. Standing waves might seem like a completely different type of wave altogether, but really they're just the result of constructive interference between reflected waves. A standing wave is simply a special case where interference and reflection work in perfect harmony. Interference is the meeting of two waves that are traveling in the same medium. When two waves meet, they disrupt each other's displacement to form a completely new resulting wave. The principle of superposition describes how the amplitudes of each wave are added together to determine the amplitude of the resulting wave at every point. When two waves meet in such a way that their crests line up together, then it's called constructive interference. The resulting wave has a higher amplitude. In destructive interference, the crest of one wave meets the trough of another, and the result is a lower total amplitude. Standing waves are phenomena that occur when waves are contained and reflect back on themselves through the medium. This combination of reflection and constructive interference produces a wave that appears to be standing in place. Have you ever noticed that sounds change their pitch when they're traveling past you? Let's say you're sitting at a stoplight, minding your own business, when all of a sudden you hear an ambulance. The siren wails a high pitch from half a mile down the road. You see the approaching vehicle and wait patiently while the ambulance speeds through the intersection. Once it passes, you notice the siren sounds different. It has a lower pitch than it did before. Why did the sound of the siren change? This common occurrence happens because of something we call the Doppler effect. You may have heard about this before. The Doppler effect explains how we perceive changes in sound when the source of the sound is moving. While the ambulance siren doesn't change pitch at all, we perceive that it changes as the vehicle moves past us. The Doppler effect isn't just about ambulance sirens, though. It's an important phenomenon that occurs in all types of waves: sound waves, light waves, and even water waves. Scientists have used the Doppler effect to make some amazing discoveries. Let's learn a little more about this phenomenon so we can see why it's so important. We already know that a wave is caused by the disturbance of a medium. Let's say you're standing at the edge of a lake when Nessie the Loch Ness Monster pops her head up right in the center. Nessie's head causes a disturbance that travels outward as a circular wave. It takes a bit of time to reach you standing at the bank, but if the lake is perfectly circular, then the wave reaches the opposite edge at exactly the same time. If Nessie keeps bobbing her head up and down, she creates more circular waves moving outward from her head. These waves all reach the banks at a certain frequency, the same frequency of Nessie's head bobbing. If she bobs her head 2 times every second, then that's the frequency of the waves hitting the banks. Now, suppose Nessie begins swimming toward you, still bobbing her head 2 times every second. The circular waves begin to look much different. Because Nessie is traveling some distance between each head bob, each successive wave originates from a slightly different spot on the water. The waves bunch together right in front of Nessie's head and spread out behind it. From your perspective, it looks like Nessie must be bobbing her head faster because the waves coming toward you arrive at a higher frequency. You might even see 3 or 4 waves per second instead of just 2. Even though the actual frequency of the wave source hasn't changed, the apparent frequency is higher. In talking about how an observer perceives waves, we have to be clear about the difference between actual and apparent frequencies. Actual frequency is just what it sounds like. It's the true frequency of a wave, irrespective of external factors. The position of an observer does not affect the actual frequency of a wave. On the other hand, apparent frequency is the frequency perceived by an outside observer. It may or may not match the actual frequency. Before Nessie started swimming across the lake, the apparent frequency you observed was 2 waves per second, the same as the actual frequency. Once Nessie began swimming, the apparent frequency changed. The apparent upward or downward shift in frequency due to the movement of a wave source is called the Doppler effect. According to the Doppler effect, the observer perceives an upward shift in frequency when the wave source is approaching. When you were the observer being approached by Nessie, you perceived an upward shift in the frequency of the waves. Of course, if you were standing on the opposite edge of the lake and Nessie was swimming away from you, you would have observed the waves to be less frequent. The observer perceives a downward shift in frequency when the wave source is retreating. We've seen how the Doppler effect can work in water waves. What about sound waves? What about that ambulance siren we talked about? An ambulance with a ringing siren makes a sound with a certain frequency, the same frequency all the time, whether the ambulance is moving or not. Let's say the sound's frequency is 440 Hertz. So that's the actual frequency. Now pretend you're sitting at that stoplight and the ambulance is speeding toward you at 50 miles per hour. The sound waves emitted from the vehicle's siren are bunched up in front of it because of its movement through space. The air compressions are closer together. So when the sound waves hit you, you perceive a frequency that is higher than the actual frequency, maybe around 480 Hertz. This is the apparent frequency. Once the ambulance passes you by, the sound waves keep coming, but now they're more spread out. They arrive at your ears at a frequency lower than that of the actual siren, because the ambulance is moving away from you. Perhaps you hear an apparent frequency of 400 Hertz. Overall, you perceive the ambulance to drop the pitch of its siren by 80 Hertz. It really seems to you that whoever is ringing the siren suddenly changed the sound's pitch. But really, the actual frequency is the same, right in the middle at 440 Hertz. If this ambulance could travel fast enough, it might get the sound waves to compound upon each other right at the front of the vehicle. To do this, the ambulance would have to travel at the speed of sound, which is roughly 330 meters per second. Some airplanes can fly at the speed of sound. When they do so, their sound waves completely bunch together in the front, producing what we call a shock wave. A shock wave is a very abrupt disturbance in a medium. The airplane creates the shock wave by making the sound waves merge together. Since it's traveling at the speed of sound, each individual sound wave has no time to get out of the way before the next wave comes. The waves compound on top of each other to create one giant shock wave. If you could listen to this wave, what you would hear is called a sonic boom. Sonic booms are extremely loud sounds caused by the buildup of sound waves. You're most likely to hear a sonic boom from a supersonic aircraft, that is, an aircraft traveling faster than the speed of sound. If you're standing on the ground when this aircraft passes you by, you'll get hit with the edge of a wavefront that is shaped like a cone. This cone shape is caused by the successive spheres of sound waves coming from the airplane. At the edge of the cone, all of the compressions merge together to make one giant sound. When that high-pressure zone hits you, you experience it as a sonic boom. Can the Doppler effect work for light waves too? Of course, light waves have frequencies too, don't they? A light wave's apparent frequency can change based on the movement of the light source or the movement of the observer. Remember that the frequencies of visible light range from 430 terahertz, which we see as red, to 790 terahertz, which we see as violet. Let's say I had a light source that was somewhere in the middle, like 600 terahertz. It looks greenish-yellow. And let's say my light source was on top of an alien spacecraft. If you were standing in a field and my spacecraft flew quickly toward you, you may perceive the spacecraft as having a greenish-blue light. That's because the apparent frequency of its light waves would be slightly higher than the actual frequency. This phenomenon is known as a blue shift, an increase in a light wave's apparent frequency due to the wave source approaching the observer. The opposite of a blue shift is a red shift, which is a decrease in a light wave's apparent frequency due to the wave source retreating from the observer. You would see a red shift happen with my alien spacecraft if I had it fly quickly away from you. The light wave spreading out behind the retreating spacecraft would decrease the apparent frequency. You'd probably see it leaving with a yellowish-orange light. We don't often experience red and blue shifts in everyday life, but astronomers observe them all the time in the galaxies surrounding us. Galaxies that are moving toward the Earth have a high apparent frequency. That is, they exhibit a blue shift. Galaxies that are moving away from the Earth exhibit a red shift. In the early 1900s, Edwin Hubble and Vesto Slipher got the idea that they could use the Doppler effect to track the movement of galaxies. They began measuring the red and blue shifts of all the galaxies they could find. When they put all their information together, they saw that most galaxies are moving away from the Earth. They also figured out that each separate galaxy is moving away from every other galaxy. In other words, everything in our universe is moving further and further apart. This discovery led astronomers and physicists to conclude that the universe is expanding, a key element which supports the modern Big Bang theory. Back here on Earth, we can still appreciate the Doppler effect for explaining the phenomena we observe in waves. It tells us why the apparent frequency, which is perceived by an observer, is not always the same as the actual frequency. The Doppler effect is the apparent shift in wave frequency due to the movement of a wave source. The apparent frequency shifts upward when the wave source is approaching and downward when the wave source is retreating. The Doppler effect explains why we perceive a change in pitch of the sound of a passing siren. It also explains the presence of shock waves and sonic booms when observing supersonic aircraft. Light waves, too, can exhibit the results of the Doppler effect. An apparent blue shift occurs when a light source is approaching, and an apparent red shift occurs when it's retreating. Edwin Hubble and Vesto Slipher used the red and blue shifts of our surrounding galaxies to draw conclusions about our universe. Thanks to their discoveries, we now adhere to the modern view that the universe is continuously expanding.
You probably know what happens if you rub a balloon against your hair. When you take the balloon away, some of your hair stands straight up, as if it's trying to follow the balloon. You may even know that it's caused by something called static electricity. But do you know what static electricity is, or why it makes your hair become attracted to the balloon? To answer these questions, we have to start with the atom. Everything in the universe is made of atoms, and every atom contains three types of particles called protons, neutrons, and electrons. The protons and neutrons are packed together in the nucleus at the center of the atom, while the electrons zip around the outside in a constant motion. For our discussion on electricity, we only need to concern ourselves with protons and electrons because they have a property called electric charge. The electric charge that electrons and protons possess is responsible for the form of energy that we commonly call electricity. Protons have a positive charge, which is easy to remember because the word proton and positive both start with the letter P. Electrons, on the other hand, have a negative charge, which is equal but opposite to the charge on a proton. If you bring one electron and one proton together, their charges cancel each other out, and we say that together they have no net charge. In most atoms, there are equal numbers of protons and electrons, so the atom itself has no net charge. However, there are many atoms that either give away electrons or accept electrons with relative ease. When this happens, we call the atom an ion. If an electron goes away, then the atom is left with more protons than electrons, and the atom becomes a positive ion. Likewise, if an electron comes along and joins the atom, then there will be more electrons than there are protons, and the atom will become a negative ion. The transfer of electrons from one atom to another happens all the time. Remember rubbing a balloon on your hair? This is a great example of transferring electrons, but why does it happen? The answer is your hair contains atoms that are happy to give away some of their electrons. On the other hand, the balloon contains atoms that want to accept those electrons and hold on to them. Therefore, when you rub the two together, a bunch of electrons transferred from your hair onto the balloon. As a result of this transfer, your hair became positively charged because its atoms were left with more protons than electrons, and the balloon became negatively charged because its atoms had more electrons than protons. A very important observation from this example is that we didn't make more electrons to build up a negative charge on the balloon, and we didn't destroy any electrons to build up a positive charge on your hair. All we did was transfer the electrons from one place to another. This concept is known as the conservation of charge. Simply stated, charge is neither created nor destroyed. It only transfers from one place to another. Let's talk about why your hair was attracted to the balloon after they were rubbed together. Have you ever heard the saying, opposites attract? A very important phenomenon of charged particles is that opposite charges exert a force on each other that tends to pull them together. Because your hair was positively charged and the balloon was negatively charged, they did in fact become attracted to each other. Now if you take the balloon away completely, you might observe that some of your hairs won't lay back down on your head, but instead stick straight up in the air. This observation demonstrates the other phenomenon that similar charges exert a force on each other that tends to push them away. All of your hairs are positively charged, so they're trying their best to stay away from each other. When electric charge accumulates on an object, such as on the balloon, we call this static electricity. The term static simply refers to the fact that the electric charge doesn't move around, but instead stays on the balloon. Have you ever been zapped by static electricity? I'll bet you have, and there's nothing static about that. To understand why this happens, let's take a look at our balloon example again. When the balloon was rubbed against your hair, it accumulated a whole bunch of electrons. Now let's say we bring the balloon close to an object with a positive charge. The electrons on the balloon will simultaneously be attracted to the positively charged object and repelled from each other. If the attractive and repulsive forces are strong enough, the electrons will jump straight through the air to get to the positively charged object. This rapid transfer of electrons is what you see, hear, and feel as an electric spark. On a larger scale, this is exactly the same phenomenon that causes lightning. Let's review what we've learned. The electric charge possessed by electrons and protons is responsible for the form of energy called electricity. Protons have a positive charge, and electrons have an equal amount of negative charge. When an atom with no net charge gains or loses an electron, it becomes an ion. Electrons can be transferred from the atoms of one object to the atoms of another object. This transfer of electrons leaves one object positively charged, while the other object becomes negatively charged. The conservation of charge states that charge is neither created nor destroyed, but only transferred. Objects with opposite charges exert an attractive force on each other, while objects with similar charges exert a repulsive force on each other. And finally, static electricity is the stationary accumulation of charge on an object that can result in a spark, which is the rapid transfer of electrons between objects. Just the other day, I was watching a science fiction movie where a space station was surrounded by an invisible force field that protected it from attacks. This would be a great invention to have in real life, but we all know that force fields don't really exist, right? Well, maybe not one strong enough to protect a space station, but they're not so far-fetched when we shrink down to the atomic level. You see, electrically charged particles, such as protons and electrons, do in fact have invisible force fields surrounding them. In this lesson, we're going to talk about those fields and the way that scientists use diagrams to represent them. Before we talk about electric force fields, we need to review some of the characteristics of electric force. All electrically charged particles exert a force on other charged particles. If the two particles have the same type of charge, such as two electrons, then the force will be repulsive and try to separate them. On the other hand, if the two particles have opposite charges, such as a proton and an electron, then the force will be attractive and try to pull the particles together. The strength of the force is very dependent on the distance between charged particles. The force is very weak when the particles are far apart, but gets much stronger as they move closer together. Another thing to note is that the force acts equally in all directions, which is why we use the term field. An electric force field is just the space surrounding a charged particle where a force will be experienced by other charged particles. Scientists often use diagrams to help us visualize concepts that we can't actually see. To make the diagram for an electric force field, we start with a circle that represents our charged particle. Next, we need a way to represent the force that our particle exerts on other particles. The problem we run into is that our particle can either repel or attract other particles depending on whether they have similar or opposite charges. To show these two scenarios, we actually use two separate diagrams, one with the arrows pointing out from the circle and the other with the arrows pointing in. The arrows are called field lines and simply indicate whether the particle is repelling or attracting. Now what if we wanted one of these diagrams to represent a proton? At this point we don't have enough information to decide because a proton can exert a repelling or an attracting force depending on the type of charge on the other particle. Scientists recognized this problem, so they came up with a rule that everyone would follow when drawing electric field diagrams. That rule stated that the field lines always point in the direction of the force experienced by a positively charged particle placed in the field. It sounds confusing at first, but it's actually quite simple when we draw it out. Let's go back to our two diagrams of repelling and attracting forces. Which one of these would represent a proton? We know that protons repel other positively charged objects, so the field lines would point out and away. On the other hand, an electron would attract a positively charged object, so the field lines would point in. Although it's good to know the rule, you can skip straight to the conclusion that if you see a diagram with the field lines pointing out, it always represents a positively charged particle. Likewise, field lines pointing in always represents a negatively charged particle. With all this talk about field line direction, I'll bet you didn't even notice that our diagram also tells us something about the strength of the force. Take a look at the spacing of the field lines. Near the particle, the lines start out very closely spaced, which indicates the force is very strong. As we move outward, the lines spread farther apart, indicating that the force is weaker. This is exactly what we learned earlier, that the force between particles is strongest when the particles are close together and grows weaker as they move apart. To sum things up, all electrically charged particles exert a force on other electrically charged particles. Opposite charges attract, while similar charges repel. The force between charged particles is very dependent on the distance between them. The force increases as the distance between the particles decreases. The force that a charged particle exerts on other charged particles is equal in all directions. An electric force field is the space surrounding a charged particle where other charged particles will experience a force. Scientists use diagrams to represent the electric force field surrounding a charged particle. When the field lines point away from the particle, the diagram represents a positive charge. When the field lines point toward the particle, the diagram represents a negative charge. Finally, the spacing of the field lines represents the strength of the field, which is strongest near the particle and becomes weaker farther away. Back in the 18th century, it was well known that an electrically charged particle would exert a force on any other charged particle. The problem was, no one knew how strong the force was or what factors affected its strength. That is, until a very bright scientist by the name of Charles Coulomb conducted several experiments that led him to propose what is now known as Coulomb's law. As we'll discuss in this lesson, he found that the force between charged particles was dependent on only two factors: the distance between the particles and the amount of electric charge that they carried. We won't worry about memorizing the equation, but we will focus instead on understanding what the equation tells us about the relationships between force, distance, and charge. The force between charged particles is directly related to the amount of charge carried by each particle. Aside from electrons and protons, most charged particles carry a variable amount of charge. Think of rubbing a balloon on your hair. The balloon will pick up negative charges from your hair and begin to act like one big charged particle. The amount of charge on the balloon will depend on how long you rub it on your hair. Now, if you repeat this experiment with a second balloon, the two will try to repel each other, and the strength of that repelling force will depend on how much charge each balloon picked up from your hair. Going back to Coulomb's equation, we can see that the amounts of charge carried by each balloon are represented by the terms Q1 and Q2. To allow us to focus on the relationship between the force and the charges, let's strip away the other parts of the equation. What this part of the equation tells us
is that the force is directly related to the product of the two charges. In other words, if the product of the charges increases, then the force will also increase. To really understand what this means, let's try some examples. We'll start out with equal amounts of charge on each balloon, which results in a repelling force between them. If we double the amount of charge on one of the balloons, then the product of the charges will also double, and in turn, the force will double. Next, let's double the amount of charge on the other balloon and see what happens. The product is now 4 times larger than it was to begin with, which means the force will also be 4 times larger. To demonstrate why it's the product of the charges that's important, as opposed to the individual charges, let's go back to the beginning. This time, we'll double the charge on one balloon, but cut the charge in half on the other balloon. When we do the math, we can see that the product remains the same, which means that the force will be unchanged. This is why it's never safe to assume that just because the charge on one particle changes, that the force will change as well. The force between charged particles is very dependent on the distance between them, even more so than on the particle charges we just discussed. In Coulomb's equation, the distance between particles is represented by the term d. To allow us to focus on the relationship between the force and the distance, let's strip away the other parts of our equation. We can see that the distance term is on the bottom of the fraction, which tells us the force and the distance are inversely related. In other words, if the distance increases, then the force will decrease. Or, if the distance decreases, then the force will increase. Force and distance always change opposite of one another. The next thing to notice is that the distance term is squared, which is really just another way to say distance multiplied by distance. Written like this, it becomes clear that the distance is actually represented twice in the equation. This tells us that a change in the distance will have more effect on the force than the same amount of change in the particle charges. To help clarify, let's look at some more examples. We'll start out just like before, with two balloons a distance apart and a repelling force between them. Next, we'll double the distance between the balloons to see what effect it has on the force. Referring back to Coulomb's equation, we can see that because the distance term appears twice, and each one is doubled, the bottom of the fraction becomes 4 times larger. Rearranging the terms makes it easier to see that the force is now 1/4 of its original strength. The same rule applies if we go in the other direction. Starting back at the beginning, we'll bring the balloons closer together until the distance is cut in half. Again, using the equation to do the math and rearranging the terms allows us to see that the force becomes 4 times stronger than it was to begin with. Throughout our discussion, we've treated the particle charges and distance separately. However, it's important to realize that they always work together to affect the force. For example, if we doubled the charge on each particle, the top of our fraction would become 4 times greater. At the same time, if we double the distance, the bottom of our fraction also becomes 4 times greater. The simultaneous changes have the effect of canceling each other out, and the force between the particles remains exactly the same. Before we conclude our lesson, it's worth mentioning that Charles Coulomb's contributions to the understanding of electrostatic force were so important that the unit for electric charge was named after him. A coulomb of charge is actually a really big number that we rarely ever encounter in day-to-day life. Just to give you an idea, we would have to transfer over 6 billion electrons to one of our balloons to give it a charge of just 1 coulomb. It's not important to remember such a mind-boggling fact, but now you know that if you ever see a number expressed in coulombs, then that number is referring to a quantity of electric charge. It's time to wrap up everything we've learned in this lesson. Coulomb's law tells us how the force between charged particles is affected by the individual charges and the distance between them. The force changes in direct relation to the product of the particle charges and in inverse relation to the distance. Increasing the particle charges generally results in an increase of force, whereas increasing the distance generally results in a decrease of force. In comparison to the particle charges, a change to the distance has more influence on the force. However, the particle charges and distance always work together to affect the force. Finally, the unit of electric charge is called the coulomb. Back in the old days, if someone's house caught on fire, volunteers would rush to the scene and form a bucket brigade to put out the flames. If you think about it, you could say that the bucket brigade was conducting water from the source to the fire. But what if the volunteers stopped passing the water? Well, we know one thing. The house would burn to the ground because it was effectively insulated from the water. The bucket brigade scenario is actually very similar to why some materials act like electrical conductors and others act like electrical insulators. But to find the actors in our electrical bucket brigade, we have to start at the atomic level. Not all atoms are created equal. Some atoms don't hold on to their outer electrons very tightly. These are known as free electrons because they are literally free to roam around from atom to atom. Free electrons are the members of our electrical bucket brigade, passing electrical energy from one electron to another. A material with many free electrons allows easy transfer of electrical energy and is therefore called a conductor. If we send an energetic electron into a conductor, it will impact a free electron, knocking it down the line until it hits another free electron. This sets up a chain reaction of impacts that conducts the electrical energy through the material. A good way to think of it is like a group of balls spread out on a billiards table. Our energetic electron is like the cue ball being shot into the group and impacting one ball, which in turn knocks into another ball, and so on down the line. Before you know it, the energy from the cue ball has been conducted all the way to the other end of the table. The only real difference between billiard balls and electrons is that electrons conduct electrical energy at nearly the speed of light. On the other end of the spectrum, there are atoms that hold on to their electrons very tightly. A material that contains these types of atoms has very few, if any, free electrons and does not transfer electrical energy well, if at all. This type of material is called an insulator. If we send an energetic electron into an insulator, it effectively bounces off the atoms, unable to transfer its energy to the tightly bound electrons. It will keep bouncing around until it either frees another electron or until it simply runs out of energy. Going back to our billiard table analogy, this is very similar to the cue ball simply bouncing off the sides of the table. Either it will hit another ball and transfer its energy, or it will just stop rolling because of friction. The ability of a material to conduct electrical energy is known as its conductivity. Not surprisingly, materials that are good conductors have high conductivity, while materials that are good insulators have low conductivity. The conductivity of a material is dependent on the number of free electrons available, and this varies greatly between the different types of atoms. In general, the materials with the highest conductivities, or best conductors, are metals, but this doesn't mean that other materials aren't capable of conducting electricity. If that were true, no one would ever be in danger of getting electrocuted. On the other end of the spectrum, the materials with the lowest conductivities, or best insulators, are glass, ceramic, rubber, and some plastics. Not all materials are classified as insulators or conductors, because in the real world they don't do a particularly good job of either one. One final note on conductivity. Good electrical conductors are also good heat conductors. Electricity and heat are just two different forms of energy, but both rely on free electrons to transfer through the material. Sometimes it's easier to tell if a material would be a good conductor by using our sense of touch to see how well it conducts heat. Let's look at some everyday examples of conductors and insulators. Have you ever given much thought to the electrical cords that power just about everything in your home? An electrical cord is made of both conductors and insulators. The wire in the center is typically made of copper, and the outer jacket from plastic or rubber. An electrical cord is a dramatic example of the different levels of conductivity between materials. Copper is so much more conductive than rubber that the electrons can travel through 100 feet of copper with ease, but can't pass through a tiny fraction of an inch of rubber insulation. In fact, the conductivity of copper is about 1,000,000 trillion times greater than that of rubber. Now, what about glass or ceramic? Can you think of a place where you've seen these materials used as electrical insulators? You've probably seen them, but perhaps you didn't realize what you were looking at. Lots of high voltage power lines are protected by these funny-looking insulators because they're so good at not conducting electricity. Let's summarize what we've learned. Materials that are composed of atoms with free electrons are good conductors. Electrical energy is conducted through a material by the transfer of energy from one electron to the next. Materials that are made of atoms with tightly bound electrons are good insulators. These materials have very few, if any, free electrons available to transfer energy. The ability of a material to conduct electrical energy is called conductivity. All metals have high conductivity and are good conductors, while rubber, plastic, ceramics, and glass have low conductivity, making them the best insulators. Good electrical conductors are also good heat conductors, because both forms of energy rely on free electrons to transfer through the material.
Gauss's law is a law that describes what an electric field will look like due to a known distribution of electric charge. It was first formulated in the 19th century. Gauss's law also comprises one of the four Maxwell's equations that describe the force of electromagnetism. To be more specific, Gauss's law can be explained in words as the total of the electric flux out of a closed surface is equal to the magnitude of the charge enclosed divided by the permittivity of free space. As a mathematical equation, it looks like this. Q is the charge enclosed by the surface, epsilon 0 is the permittivity of free space, which is just a constant that's always equal to 8.85 times 10 to the minus 12, and phi is the electric flux through the surface. But what is electric flux? The electric flux, represented by the Greek letter phi, is the electric field E multiplied by the area A of a surface perpendicular to the field. Phi equals EA. It's basically the number of field lines that pass through a surface. More field lines means a larger flux. So for example, you could use Gauss's law to figure out the electric field created by a charge-conducting sphere. In that case, you have a charge surrounded by a spherical surface. If you wanted to know the total flux, you would take the electric field strength at the surface of the sphere and multiply it by the surface area of the sphere. But not all surfaces are spheres, so the exact equation for Gauss's law varies depending on the particular surface you're looking at. This might be easier if we went through a few examples. Let's first go back to the sphere. Gauss's law tells us that the flux is equal to the charge Q over the permittivity of free space, epsilon 0. But flux is also equal to the electric field E multiplied by the area of the surface A. So EA equals Q over epsilon 0. For a sphere, the surface area is given by 4 pi r squared, so we can plug that in for the area A. And finally, if we rearrange it for the electric field E to make electric field the subject, we find that the electric field E is equal to Q over 4 pi epsilon 0 r squared. This is an expression for the electric field created by a charged sphere. Okay, let's try another one. How about a conducting cylinder? We start with the same basic equation, but this time the area is different. The surface area of a cylinder is equal to 2 pi RL, where R is the radius of the cross-section of the cylinder, and L is the length of the cylinder. If we rearrange that for E again, this time we get Q over 2 pi epsilon 0 RL. So that's an expression for the electric field created by a charged cylinder. We could do the same thing for any uniformly shaped object, so Gauss's law is a very powerful tool. Okay, let's try using one of these equations in a practice problem. Let's imagine we have a metal sphere with a total charge 0.1 coulombs. Use Gauss's law to find the electric field strength at a distance of 0.4 meters from the sphere, assuming the sphere has a radius less than 0.4 meters. Well, first of all we should write down what we know. The total charge Q is 0.1 coulombs. The radius R is 0.4 meters, and epsilon 0 is always equal to 8.85 times 10 to the minus 12. Gauss's law looks like this, and the surface area of a sphere is 4 pi r squared. Like we said earlier, this rearranges to form this final equation, and then all we have to do is plug numbers in and solve. Typing all that into your calculator, you should come up with an electric field strength of 5.6 times 10 to the 9 newtons per coulomb. And that's it. That's our answer. Gauss's law is a law that describes what an electric field will look like due to a known distribution of electric charge. To be more specific, Gauss's law can be explained in words like this. The total of the electric flux out of a closed surface is equal to the magnitude of the charge enclosed divided by the permittivity of free space. As a mathematical equation, it looks like this. But what is electric flux? The electric flux, represented by the Greek letter phi, is the electric field E multiplied by the area A of a surface perpendicular to the field. Phi equals EA. It's basically the number of field lines that pass through a surface. More field lines means a larger flux. To use Gauss's law, you have to plug in an expression for the area A. That might be the area of a sphere, 4 pi r squared, or the area of a cylinder, 2 pi RL, or something else. You decide what to plug in based on the shape of the object that contains the charge. Once you do that, you have a final equation you can use to solve problems.
This past weekend, I was out in the garden watering the flowers when suddenly the flow of water nearly stopped. I looked behind me and realized there was a kink in the hose that was restricting the water flow. After I straightened out the kink, the water flow came back and I resumed my watering. But a few minutes later, the water flow slowed down again. I looked for another kink in the hose, but this time I couldn't find one. I went in the house and found that my roommate was taking a shower while running the washing machine and the dishwasher all at the same time. Our water pump couldn't keep up with so much demand for water, and as a result, the water pressure to my garden hose had dropped, which reduced the water flow. This got me thinking about how similar water flowing through a hose is to electric current in a circuit. Just like the water flow was determined by the amount of pressure and resistance in the hose, electric current is determined by the amount of voltage and resistance in an electric circuit. The relationship between voltage, current, and resistance is described by Ohm's law. This equation tells us that the current I flowing through a circuit is directly proportional to the voltage V and inversely proportional to the resistance R. In other words, if we increase the voltage, then the current will increase. But if we increase the resistance, then the current will decrease. We saw these concepts in action with the garden hose. Increasing the pressure caused the flow to increase, but getting a kink in the hose increased the resistance, which caused the flow to decrease. The way the equation is written here, it would be easy to use Ohm's law to figure out the current if we know the voltage and the resistance. But what if we wanted to solve for the voltage or the resistance instead? One way to do this would be to rearrange the terms of the equation to solve for the other parameters. But there's an easier way. This diagram will give us the appropriate equation to solve for any unknown parameter without using any algebra. To use this diagram, we simply cover up the parameter we're trying to find to get the proper equation. This will make more sense once we start using it, so let's do some examples. Here is a simple electric circuit that we'll use to do our examples. Our voltage source is a battery that is connected to a light bulb, which provides resistance to the electric current. To start off with, let's say our battery has a voltage of 10 volts, the light bulb has a resistance of 20 ohms, and we need to figure out the current flowing through the circuit. Using our diagram, we cover up the parameter that we're trying to find, which is current, or I, and that leaves us with the voltage V over the resistance R. In other words, to find the current, we need to divide the voltage by the resistance. Doing the math, 10 volts divided by 20 ohms, results in 1/2 ampere of current flowing in the circuit. Next, let's increase the voltage to see what happens to the current. We'll use the same light bulb, but switch to a 20-volt battery. Using the same equation as before, we divide 20 volts by 20 ohms, and we get 1 amp of current. As we can see, doubling the voltage caused the current to double as well. This makes sense when we think about the garden hose. If we increased the pressure in the hose, we would expect the flow of water to increase as well. It's always good to double-check your work by asking if the results match what you expected to happen. If we increase the resistance of the light bulb, what would you expect to happen to the current? To find out, let's swap out our existing bulb with a different one that has a resistance of 40 ohms. Since we're still looking for the current, we use the same equation as before. Dividing 20 volts by 40 ohms gives us 1/2 ampere of current. This result tells us that doubling the resistance reduced the current by half. Is this what you expected? Thinking back to our hose, it makes sense that putting a kink in the hose would reduce the water flow, just like increasing the resistance in the circuit would reduce the current. Thus far, we've only calculated the current in the circuit. But what if someone had swapped out our light bulb when we weren't looking, and we needed to figure out the resistance of the new one? Well, we know the voltage of our battery is 20 volts, and we can measure the current in the circuit with a tool called an ammeter, so all that's left is to do some math. Using our diagram, we cover up the parameter that we're trying to find, which is the resistance R. The diagram now shows us that we need to divide the voltage by the current. If our ammeter measured a current of 5 amperes flowing through the circuit, then the resistance is equal to 20 volts divided by 5 amperes, which is 4 ohms. Finally, imagine that someone replaced our battery and we needed to figure out its voltage. The process is pretty much the same. We know our new bulb has 4 ohms of resistance, and we can measure the current in the circuit with the ammeter. Using the diagram, we cover up the voltage, V, which tells us that we need to multiply the current by the resistance. If the ammeter measured a current of 3 amperes, then the voltage would be 3 amperes multiplied by 4 ohms, which is 12 volts. That's all there is to it. By knowing any two of the 3 parameters, we can always calculate the third by using Ohm's law. Ohm's law defines the relationship between the voltage, current, and resistance in an electric circuit. The current is directly proportional to the voltage and inversely proportional to the resistance. This means that increasing the voltage will cause the current to increase, while increasing the resistance will cause the current to decrease. Knowing any two of the 3 parameters allows us to calculate the third, unknown parameter. We can do this by rearranging the terms in the Ohm's law equation, or by using the following diagram. Covering up the parameter that we're trying to find shows us the appropriate equation using the 2 known parameters.
There are lots of types of waves, but they all move. Sound waves move from an object making a sound to your ear. If they didn't, you wouldn't hear anything. Light waves move from the sun, bounce off an object, and go into your eye. If they didn't, you wouldn't see anything. So it isn't hard to prove that waves move. But what is a wave? A wave is a vibration in space and time that carries energy. Ocean waves, for example, are able to move large amounts of sand and rock from place to place. They can only do that because of the large amount of energy stored inside them. Wave propagation is the physics term for the movement of waves. Today we're going to discuss the various ways that waves of different types can move, and how those are different from each other. If waves move, it makes sense that they should have a speed. If you literally measured how fast a peak of an ocean wave got from point A to point B, you will be measuring the wave speed. But what decides how fast a wave moves? It turns out that some waves need a medium, a material, to travel through, and others don't. The only type of wave that doesn't is electromagnetic waves like light, infrared, microwaves, ultraviolet, and radio waves. Since they don't have to move through a material, that material doesn't slow them down. They're the fastest moving waves, and they propagate at the speed of light, which is 3 × 10⁸ meters per second. Waves that do need to travel through a medium go more slowly. The exact wave speed depends on the material they travel through, the presence of any tension in the material, and the temperature of the material. If these factors change, so does the wave speed. Denser materials, like jello, tend to have lower wave speeds, because it takes longer for the vibrations to pass from particle to particle. But often denser materials are also more rigid. More rigid materials, like cookies, have a higher wave speed. So it's hard to predict what the wave speed will be using density alone. Stretched out materials, materials with a tension, like saltwater taffy, tend to have higher wave speeds, because particles are more spread out. Last of all, high temperatures lead to higher wave speeds, because particles move faster when they're heated up, causing the wave to pass through the material, like hot fudge, more quickly. The way waves propagate also varies, because there are 2 types of waves, transverse and longitudinal. Transverse waves vibrate at 90 degrees to the direction of propagation. A wave might be moving forward, but transverse waves vibrate side to side. Longitudinal waves, on the other hand, vibrate parallel to the direction of propagation. Examples of transverse waves include electromagnetic waves like light and water waves. An example of a longitudinal wave would be sound, because sound is just air molecules hitting each other in a wave pattern. Transverse and longitudinal waves might vibrate in different directions, but those vibrations don't affect the propagation of the wave. The wave still continues forward, the energy moving along with it in the same way, whether the wave is transverse or longitudinal. A wave is a vibration in space and time that carries energy. So movement is a key part of what makes a wave a wave. Wave propagation is the physics term for the movement of waves. Electromagnetic waves don't need a material at all, and so they always travel at the same speed, 3 × 10⁸ meters per second. But waves that do need a material are slower and vary in speed. The wave speed is affected by many factors: the density of the material, the rigidity of the material, the temperature, and the tension in the material. The way waves propagate varies because there are 2 types of waves, transverse and longitudinal. Transverse waves vibrate at 90 degrees to the direction of propagation. The wave might be moving forward, but transverse waves vibrate side to side. Longitudinal waves, on the other hand, vibrate parallel to the direction of propagation. But whatever type of wave you're interested in, the direction of vibration has no effect on the propagation direction of the wave itself.
Imagine plucking a string on a guitar or blowing into a whistle. In both situations, you are creating vibrations, also known as mechanical waves, within the body of the instrument. The vibrating instrument creates sound that your ears detect after energy from the vibration, in the form of a sound wave, travels through the air to your ear. The vibrations that are created within the instrument itself are known specifically as standing waves. A standing wave is a particular kind of wave that can only be created when a wave's motion is restricted to a finite region. To understand exactly what this means, let's focus on a vibrating guitar string. The guitar string's motion is restricted on both ends of the string, on the fretboard by your finger on one side and by the bridge on the other side, where it attaches to the body of the guitar. When the string is plucked, the wave reflects off each of these boundaries. The wave's energy quickly spreads out as it repeatedly moves back and forth between the two ends of the string. Through a complicated process of interference, standing waves are produced. A standing wave gets its name from the fact that it does not appear to be traveling from one side of the string to the other. Rather, it is waving while it stands in place. Take a look at this standing wave, modeled after the string of a guitar. Even though the string is only fixed in place at the ends, so the entire middle can vibrate freely, you can see that there are some points on the string that are not moving at all. These stationary points on a standing wave are called nodes. The standing wave shown has 3 nodes. We only count the untethered stationary points, not the endpoints of the string where it is being held down. The points that are halfway between 2 adjacent nodes, where the motion of the string has the greatest deviation from its unplucked position, are called antinodes. The wave depicted has 4 antinodes. A standing wave always has 1 more antinode than its number of nodes. So why do notes played on an instrument sound musical compared to, say, the waves that are created when you turn on a garbage disposal or knock over a box? The answer to this question is related to the frequencies of oscillation of standing waves. The frequency of any wave, which includes standing waves, is measured in units of hertz, Hz, and is defined as the number of times the wave repeats its up and down motion in 1 second. The frequency of a standing wave is directly related to its number of antinodes. Specifically, if L is the length of the string, and V is the translational speed of waves on the string, then the frequency of oscillation of the standing wave F with N number of antinodes is given by the formula F equals N times V over 2L. Musical sounds tend to consist of a limited number of specific frequencies that are related in mathematically simple ways, whereas general noise consists of a continuous range of frequencies. The frequencies of standing waves turn out to be limited by a simple mathematical relation. When a string that is restricted on both ends is plucked, the frequencies of the waves that appear on the string are limited to certain values that can be calculated with the formula. The fact that the frequencies are limited is seen in the formula because the number of antinodes n can only take on integer values, 1, 2, 3, etc. Because a standing wave cannot have, say, 1.5 or 2.75 antinodes. It can only have a whole number of antinodes, and it follows that the frequencies of standing waves on a plucked string can only take on very specific values. The set of allowed frequencies for a particular string, defined by the formula mentioned earlier, is called the harmonic series of the string. Since each allowed frequency corresponds to a vibration with a different number of antinodes, the harmonic series is usually represented in a diagram depicting the general shape of the string for each possible frequency or harmonic. The first 3 harmonics, with 1, 2, and 3 antinodes, are depicted in this diagram. As the number of antinodes n increases, so does the frequency of the wave. Standing waves, or waves with fixed stationary points on them, can be observed on guitar strings when plucked, and, in some form, within nearly every other musical instrument. They form when a vibration is restricted, confined to a region with boundaries or endpoints. The stationary points on the wave are called nodes, and their inverse, the points of greatest deviation from the center, are referred to as antinodes. Due to the restriction of the vibration to a particular region, the frequencies of standing waves are limited, which is the feature of musical sounds. We can predict the base frequency of a standing wave with a particular length, wave speed, and number of antinodes using the formula F equals N times V over 2L. The same standing wave is then only capable of achieving frequencies that are whole integer multiples of its base frequency. The set of allowed frequencies is called the harmonic series and is an important term that is used to discuss the physics of music.
The photoelectric effect occurs when electrons are released after light is shone onto a metal. Electrons released in this way are called photoelectrons, which leads to the name photoelectric effect. According to classical physics, this happens because energy is transferred to the electrons from the light. This theory turned out to be true, although the way it happens is quite different than we originally expected. Heinrich Hertz was the first to observe and publish observations about the photoelectric effect in 1887. He employed a spark gap with an ultraviolet light source. He realized that if the light was partially blocked, sparks didn't occur as often. This turned out to be because electrons were being given energy by the ultraviolet light, which released them from their atoms and allowed them to jump across the gap. Sparks, and electricity in general, are caused by the movement of electrons. J.J. Thomson studied this further using cathode ray tubes. He found that the particles released in the photoelectric effect were the same ones observed previously in so-called cathode rays. At the time, these were called corpuscles, but later were named electrons. Until this point, the observations were not especially difficult to explain. But in 1902, Philip Lenard noticed that the energy electrons produced increased as the frequency or color of the light increased. This was very unexpected. Something called Maxwell's wave theory of light said that brighter, higher intensity light would lead to higher energy electrons, but this isn't what Lenard observed. Only a higher frequency light produced higher energy electrons. A brighter light only produced more numerous electrons. Albert Einstein explained this problem in 1905. He realized that light must contain packets, or quanta, which are quantities, of energy called photons. He also noted that the amount of energy of those packets depended on the frequency or color of the light by the following equation. In this equation, E is the energy in the packet in joules, H is Planck's constant, just a number, and F is the frequency of the light in hertz. Based on this equation, low-frequency light has packets that have less energy, so if you shine a light of low enough frequency, the electrons can't get enough energy to escape from the metal. And as you increase the frequency above the minimum level needed, called the threshold frequency, the electrons leave the metal with more and more energy. They leave at a faster speed. The brightness or intensity of the light only determines how many packets there are, and therefore how many electrons are able to escape, not how much energy those electrons have. This fit perfectly with the observations made by Lenard and others. The explanation of the photoelectric effect led to the birth of quantum mechanics, which has a multitude of applications. But the biggest direct application of the photoelectric effect is the development of the television. Old TVs are called CRTs, or cathode ray tubes, and use a setup very similar to Thomson's experiment. The electrons produced hit a fluorescent screen that emits light, giving you the image on these early televisions. The photoelectric effect is when electrons are released when light is shone onto a metal. This happens because energy is transferred from the light to the electrons. When you shine brighter light on the metal, more electrons come out. When you shine higher frequency or bluer light on the metal, higher energy electrons come out. These observations were not expected when they were first observed. Albert Einstein explained them by saying that light contains packets of a particular amount of energy called quanta. Higher frequency light contains larger packets of energy. Higher intensity or brighter light contains more packets. These packets hit the electrons and give them the energy needed to escape. Old CRT televisions use the photoelectric effect. Electrons are produced and hit a screen made of a material that will emit light. By controlling these electrons, you can control the image produced.
In the early 20th century, we discovered something amazing about particles and waves. Light was both a particle and a wave. If that strikes you as impossible or hard to fathom, you wouldn't be alone. It took a long time to convince a world of skeptical physicists. But the work of Albert Einstein and Max Planck had led to the realization that light didn't always act like a wave. Light would indeed refract, reflect, and diffract just as you'd expect waves to. But Einstein's photoelectric effect experiment showed that light also acts like it contains some sort of particle. Light, as it turns out, contains packets of energy of a particular size called quanta, and these quanta can collide with atoms and be absorbed by them. But the full concept of wave-particle duality was introduced by Louis-Victor de Broglie in 1923 as part of his doctoral dissertation. He suggested that perhaps not only did waves like light behave as particles, but particles could also behave as waves. He suggested that matter had wave-like properties. But if that's true, why don't we see those properties in everyday life? Why don't you see dogs bouncing off mirrors, or people spreading out and producing diffraction patterns when they walk through doors? To answer that question, we need to do some math. De Broglie suggested that matter had a wavelength, which was later called the de Broglie wavelength. The de Broglie wavelength, lambda, of an object or particle, measured in meters, would be equal to Planck's constant h, which is just a number that's always equal to 6.63 times 10 to the negative 34, divided by the momentum of the object or particle, p, measured in kilogram meters per second. And let's also remember the basic equations for momentum, which say that the momentum of an object or particle is equal to the mass, measured in kilograms, multiplied by the velocity, measured in meters per second. To test this out, let's try calculating the wavelength of, say, a grand piano. Suppose our grand piano weighs 400 kilograms, and let's roll it down the stairs, such that it's moving at a speed of 2 meters per second. What is the wavelength of the grand piano? Well, 6.63 times 10 to the minus 34, divided by the momentum mv, which is 400 multiplied by 2, type that all into a calculator, and that gives us a wavelength of 8.3 times 10 to the negative 37. This is a tiny, tiny number. What this means is that for a grand piano to act like a wave, for example by diffracting as it goes around an obstacle, the obstacle would have to be just 8.3 times 10 to the negative 37 meters across. Significantly bigger, and nothing would happen. To put that into perspective, an electron is 10 to the negative 16 meters across. So the obstacle would have to be 1 and 21 zeros smaller than an electron. No such object even exists. So when we do the math, it becomes pretty obvious why we never see a grand piano acting like a wave. It has a wavelength, it's just much, much too small. Although grand pianos might just be too large, electrons are still pretty tiny. The de Broglie wavelength of an electron is small enough that you can observe wave properties. This is used most famously in the electron microscope. This incredible piece of technology bounces electrons off the atom, observing diffraction effects as it does, and uses the paths of the electrons afterwards to create an image of the atom itself. De Broglie was the first to suggest and show mathematically that not only could waves act like particles, but particles, matter, could also act like waves. He introduced it as part of his doctoral dissertation in 1923. This is the concept of wave-particle duality. The only reason we don't see matter act like a wave in everyday life is that the wavelength of everyday size objects is just too small. You can calculate this so-called de Broglie wavelength using this equation. It says that the de Broglie wavelength, lambda, of an object or particle measured in meters would be equal to Planck's constant h, which is always 6.63 times 10 to the negative 34, divided by the momentum of the object or particle, p, measured in kilogram meters per second. Probably the most famous application of this theory is the creation of the electron microscope, a device that uses the wave properties of electrons to create an image of the atom itself. Planck's constant is a number that describes the size of the energy packets, or quanta, that are contained within light. These packets of energy are called photons. Planck's constant is given the symbol h in physics, and numerically is equal to 6.63 times 10 to the negative 34 joule seconds. Towards the end of the 19th century, Planck was working to understand black body radiation, a kind of radiation that would be emitted by a perfect absorber and emitter of radiation. This is very close to the kind of radiation we receive from the sun. Planck successfully created an equation to describe black body radiation, but then realized his solution was one of many, which could lead to many different values of energy produced. In a last-ditch attempt to make his ideas work, he proposed that the energy of light was not a continuous quantity. You couldn't just have absolutely any value of energy. Rather, light must contain packets of energy of a particular size. Although it was an act of desperation, he turned out to be right, and won a Nobel Prize in 1918 for his work. While Planck's constant can now be found in many equations, the equation that defines Planck constant is called the Planck-Einstein relation, and it looks like this. Here, E is the energy of each packet or quanta of light measured in joules, F is the frequency of light measured in hertz, and H is of course Planck's constant. So the constant describes how to take the frequency or color of light and use it to determine the size of the packets of energy or photons it contains. It's a pretty straightforward equation, but one that was part of a revolution in physics. Understanding the existence of these quanta led over the following few decades to the development of quantum mechanics, a topic that has revolutionized physics and in turn led to huge advances in the world. Let's go through an example. Let's say you're shining blue light of frequency 6.2 times 10 to the 14 Hz on a piece of metal, causing electrons to be produced from the surface. How much energy does each photon of light contain? To solve this, we just plug numbers into the Planck-Einstein relation. We know the frequency is 6.2 times 10 to the 14, and Planck's constant is always 6.63 times 10 to the negative 34. The energy is just h multiplied by f. So multiply those two numbers together, and we get 4.1 times 10 to the negative 19 joules. And that's it. That's our answer. Planck's constant is at the heart of quantum mechanics, and so any application of quantum mechanics is essentially an application of Planck's constant. Quantum mechanics has been hugely successful in explaining many of the features of the universe, from subatomic particles to explaining why chemical bonding works. And this understanding led to the development of many technologies. Whenever something works on a tiny scale, quantum mechanical principles have to be taken into account. Technologies that rely on quantum mechanics include lasers, the transistor found in all circuitry, MRI scanners in hospitals, flat-screen televisions, flash drives, CCDs in digital cameras. There are too many to list. Our lives will be completely different without quantum mechanics, and therefore without Planck's constant. Planck's constant is a number that describes the size of the energy packets, or quanta, that are contained within light. These packets of energy are called photons. It's given the symbol h in physics, and numerically is equal to 6.63 times 10 to the negative 34 joule seconds. The fundamental idea is that the energy of light is not a continuous quantity. You can't have absolutely any value of energy. Rather, light must contain packets of energy of a particular size. Although it was an act of desperation, Planck turned out to be right. The equation that defines Planck constant is called the Planck-Einstein relation, and it looks like this. Here, E is the energy of each packet or quanta of light measured in joules, F is the frequency of light measured in hertz, and H is of course Planck's constant. So the constant describes how to take the frequency or color of light and use it to determine the size of the packets of energy it contains. Applications of Planck's constant include lasers, the transistor found in all circuitry, MRI scanners in hospitals, flat-screen televisions, flash drives, and CCDs in digital cameras.
One day, you decided to climb a tree in your backyard. Maybe you were 8 years old, maybe it was yesterday. Either way, you overestimated your climbing abilities, and just as you were reaching that top branch, you tumbled to the ground. Ow! A few painful hours later, you're in the x-ray room covered in a lead apron, waiting for your arm to be x-rayed. Why did you have to wear that lead apron? What's all the fuss about x-rays? You couldn't feel them. They didn't hurt when the pictures were being taken. What were they doing to your arm? In this lesson, we're going to cover just what those X-rays were doing to the atoms in your arm and what makes X-rays potentially harmful. We're also going to expand this knowledge to the periodic table so we can use it to make predictions about atoms. Earlier, you learned that when an atom absorbs energy, its electrons move out to outer energy levels. The more energy an atom absorbs, the more energy the electron absorbs, and the farther out it will go. I may have left you with an unanswered question, though, because I never did tell you what happens when an atom absorbs too much energy. I'm about to explain that, but first, let's start out by reviewing some of the forms of electromagnetic radiation. This is the source of the energy. Electromagnetic radiation is just a form of energy that travels through space. There are many different kinds that have different amounts of energies. For example, all visible light has a medium amount of energy, red light having the lowest and violet light having the highest. Electromagnetic radiation that has even more energy than violet light is ultraviolet light. You may know that UV light can be bad for you, but the reason is that it carries very high amounts of energy. Higher than UV is energy from X-rays, and even higher than that is radiation from gamma rays. So, what do all these forms of electromagnetic radiation do to atoms? The forms that have low energies just excite the electrons of atoms, which cause them to move out to higher levels, eventually falling back down and releasing energy. However, if too much energy is added to an atom, the electrons won't just go out to a higher energy level, they'll leave the atom altogether. That's it. Gone. So, just how much energy does it take to remove electrons from an atom? Well, that depends on the type of atom. This amount of energy is so important that it has a special name: ionization energy. Ionization energy is the amount of energy required to remove an electron from an atom. The electron that is most likely to leave the atom first is the one that's the farthest out already. So when it becomes ionized, it is losing an outer electron. Because each atom is structured a little bit differently, each atom will have a different ionization energy. You won't need to memorize the specific amounts of energy for each atom, but you should be able to identify and explain ionization energy trends as you move down groups or across periods on the periodic table. Remember, a group on the periodic table is just a column. We're first going to compare the ionization energies of atoms in the same column. To do this, I want you to imagine that an atom is a bank filled with security guards in the basement. These are going to be protons in the nucleus. The electrons will be represented as money located on different floors of the bank, which are our energy levels. And that robbers are trying to steal this money, which would cause the bank to be ionized. Also, it should make sense that the easier something is, the less energy it takes to do it. So we are going to determine how easy it will be for the robbers to steal the money from the bank, or how easy it is to remove an electron from an atom. As you may know, as we move down a column on the periodic table, the atoms get larger because they have more energy levels, which are the floors of our bank. We also have more security guards, the protons, but they're all the way in the basement, the nucleus, and they would really have trouble stopping a robber that landed on the roof and is trying to steal money from the top floor. So, the more floors the bank has, the easier it is for the robbers to steal the money from the top floor, because the security guards don't have as much control over the top floors as they do the ones closest to the basement. In chemistry terms, the bigger an atom is, the lower its ionization energy will be. As we move down a column on the periodic table, the atoms get bigger. So as you move down a group or column on the periodic table, the ionization energy decreases. This is because those protons are so far away from the outer electrons that their pull in is very weak. Next, we'll compare atoms across a period. Keep in mind that it's only when you move down a column that new energy levels, or floors, need to be added. So we are going to compare banks with the same number of floors, but an increasing number of security guards. So which bank do you think would be the most difficult to rob? One with 2 floors and 4 security guards, or one with 2 floors and 10 security guards? I think it would require much more energy to rob a bank with 10 security guards than 4. So given the number of floors, or energy levels, remains the same, The bank with the most security guards, or protons, would be the most difficult to rob. In chemistry terms, given the same number of energy levels, the more protons an atom has, the higher its ionization energy will be. So as you move across a period on the periodic table, the ionization energy increases. Neon has a higher ionization energy than beryllium. Neon has 10 security guards and 2 floors, and beryllium only has 4 security guards and 2 floors. Electromagnetic radiation that has the energy of ultraviolet light or higher, so X-rays and gamma rays, is damaging to living tissues because it can cause the atoms to lose their electrons. Later on, you'll learn that electrons are pretty much the glue that holds bonds together. And if bonds start losing electrons, they start breaking. And if you have enough bonds that break, especially in DNA, mutations or even cell death can occur. This is both good and bad. DNA mutations from ionizing radiation can cause cancer. However, ionizing radiation can be used in very specific locations in the treatment of cancer by killing cancer cells. The trends mentioned in this lesson are very general. There are always going to be exceptions here and there. Don't worry about memorizing the exceptions, but do feel comfortable with explaining what the trend is and why. So, to review, as you move from top to bottom in the same group or column on the periodic table, the ionization energy will decrease, meaning that it will become easier and easier to remove an atom's outer electron. This is because these electrons are being removed from farther and farther away from the nucleus as the atoms increase in size. As you move from left to right in the same period, or row on the periodic table, the ionization energy will increase. This is because electrons are all located in the same energy levels, so elements with more protons, those on the right-hand side, will have a greater pull on those outer electrons, making it more difficult to remove them from atoms.
At the beginning of this century, it was already known that atoms were made of protons at the center, the nucleus, and electrons orbiting around them. Scientists later realized that the light emitted from a particular type of atom occurred at specific frequencies. That is, the light given off by a collection of atoms in the gas phase could only be of certain colors. To explain this observation, Niels Bohr proposed that electrons inside an atom occupy only certain allowed orbitals with a specific energy. In other words, the energy of an electron in an atom is not continuous, but quantized. The energies corresponding to each of the allowed orbitals are called energy levels. To understand this better, think about a bookshelf. Each shelf contains books, just like how each possible orbital in an atom contains electrons. Each shelf is different from the others, just like how each orbital represents different energy levels for electrons. An electron can't have an energy value halfway between two energy levels in an atom. Similarly, a book cannot be placed halfway between consecutive shelves. It can only be placed within one shelf. Each energy level is labeled with the quantum number, n. n equals 1, 2, 3, and so forth. And the energy of a particular level can be determined by En is equal to negative RH times 1 over n squared. This is where RH is the Rydberg constant of the element. For the simplest atom, the hydrogen atom, RH is equal to 2.18 times 10 to the negative 18 J. The electrons of individual atoms can be excited from a lower energy state to a higher energy state as shown in the image on screen. This happens, for example, when a high voltage is applied through a collection of atoms in the gas phase. However, electrons tend to avoid excited states, so after a short time they transition to a lower energy state, called relaxation. Because energy was absorbed to excite the electron, energy has to be emitted after the electron transitions to its initial state. The energy is then released in the form of light, electromagnetic waves. The energy difference between the two energy levels involved in the transition defines the color of the light emitted from the atoms. Each color of light has a particular energy and frequency. The energy of the light emitted from a particular transition can be calculated like this. Notice that if the transition goes from a higher energy level to a lower one, the change in energy is negative, loss of energy. If the transition is from a lower energy level to a higher one, the change in energy is positive. Energy had to be absorbed by the atom. This image shows an energy diagram showing possible transitions between the first 7 energy levels in the hydrogen atom. Each series of transitions is named after the scientist who discovered them. Different elements have different energy values associated to each level. Because of this, the possible transitions from each element correspond to different light energies and frequencies. The combination of frequencies that an element emits is called the emission spectra. The emission spectra of each element is unique, just like fingerprints are unique for each person. It's used to identify unknown elements as fingerprints are used to identify who a person is. Energy levels inside an atom are the specific energies that electrons can have when occupying specific orbitals. Electrons can be excited to higher energy levels by absorbing energy from the surroundings. Light is emitted when an electron relaxes from a high energy state to a lower one. Each element has a unique light emission spectra that can be used as a way to identify the element.
The 1903 winners of the Nobel Prize in Physics, Marie and Pierre Curie, were dedicated scientists who studied and advanced the use of X-rays. Marie Curie, born Marie Skłodowska, immigrated to Paris from Poland at 24 years old to continue her study of math and physics. There, she met and married Pierre Curie, a respected physicist, and they soon began working together, testing different elements to see which gave off radiation, or waves of electromagnetic energy. We know now that radiation can be very dangerous stuff, but little was known back then. Marie and Pierre Curie and their daughter Irene, who also worked with them in their laboratory, were exposed to such extremely high levels of radiation every day that they all suffered from health problems because of it. Marie and Irene administered thousands of X-rays on French battlefields during World War I, with nothing to protect them but the clothes on their backs. Both mother and daughter eventually died of illnesses caused by their repeated exposure. Even now, the Curie's work papers and even their cookbook contain such dangerous levels of radioactivity you have to sign a waiver before you are allowed to handle them. X-rays are powerful waves of electromagnetic energy. Waves, like those found in the ocean, are the movement of energy. When you clap your hands, energy, in this case sound, begins at a source. The sound travels through the air as waves until it reaches your eardrums and registers as sound. Waves that travel through a physical medium, like air and water, are called mechanical waves. Electromagnetic, or EM waves, don't require a physical medium to travel across, so they can exist on both Earth and in space, where there is no air for even sound waves to travel through. EM waves are organized along a spectrum according to the distance between each wave and the frequency of waves per second, measured in hertz. The waves with the lowest frequencies and the greatest distances between waves give off relatively low amounts of energy. Radio waves, for example, have the lowest frequencies of the different categories of the waves on the electromagnetic spectrum, while gamma rays, created by nuclear explosions, have the highest frequencies. X-rays are the band of electromagnetic waves just before gamma rays on the EM spectrum. They are at the far end and, along with gamma rays and some ultraviolet rays, are shown as damaging to DNA. As we know from the injuries sustained by Pierre, Marie, and their daughter Irene during their X-ray experiments, X-rays are very powerful in their own right. At about 1 quintillion waves per second, that's 1 quintillion hertz, we think of them as rays of energy rather than waves. When they were first discovered over 100 years ago in 1895 by Wilhelm Conrad Röntgen, X-rays were used in much the same way that we use them now, to see the bones inside our bodies. Röntgen would often demonstrate X-rays by taking an image of the bones in his wife's hand. Bones, and other objects, are denser than skin. They absorb enough radiation to create shadows on X-ray film and show us when bones are broken or if little Timmy has indeed swallowed a penny.
We use X-rays to do more than look at bones. We also use them in other diagnostic ways, to look for tumors, lung infections, dental problems, and blocked blood vessels. X-ray technology is put to use by airport security to search for potential weapons inside luggage, and by builders to examine structures for possible fractures or weaknesses. Since we know so much more about how X-rays work than early scientists like Curie and Röntgen, we are able to take precautions to use them safely, like wearing lead vests to protect our vital organs during dental X-rays. The band of visible light on the EM spectrum is the frequency of electromagnetic waves that are visible to the human eye. While we can see the sun with our eyes, the atmosphere surrounding the sun, the corona, gives off very hot X-rays. Scientists use special X-ray detectors to get a better idea of what kind of unseen energy is emitted by the sun and other celestial bodies, like pulsars and supernova remnants. The Mars Exploration Rover uses X-rays to determine the composition of different rocks it encounters in the foreign Martian landscape. Marie and Pierre Curie were talented scientists who studied and advanced the many uses of X-rays. Unfortunately, they were not aware of the damaging health consequences of repeated and prolonged exposure to intense radiation or waves of electromagnetic energy. X-rays are powerful waves of electromagnetic energy, and we know today to take precautions around them. Unlike mechanical waves, which require a physical medium to travel through, X-rays don't require a physical medium to travel across, so they belong in the category of electromagnetic or EM waves. X-rays are on the far end of the electromagnetic spectrum and have very high frequencies, in the neighborhood of a quintillion waves per second. Of course, there's much more to X-rays than potential health risks. These electromagnetic waves are used to look inside the human body and to better observe the universe.
Rainbows are one of the most beautiful things on Earth, containing a spread of the colors that our eyes can see. That's why we use the expression, every color of the rainbow. But did you know this expression isn't technically true? That the rainbow is actually missing a few colors. If you could look extremely closely at a rainbow and analyze its light, you would find dark gaps in the otherwise continuous spectrum of light. This is because pure white light can be shined through a prism and split into every color our eyes can see. But the sun doesn't send us pure white light, it sends us an atomic spectrum. An atomic spectrum is a spectrum that has been shined through or originates from a material, usually a gas, and contains patterns that are characteristic of the elements present in the material. When we analyze the sun's spectrum, for example, we can figure out what elements are present in the sun. To analyze the sun's light, we shine it through a spectrometer, which is a device that separates light by energy and color. When we do that, we create an image of the sun's spectrum that looks like this. An absorption spectrum similar to the sun. The black lines show where light is absorbed by the elements in the outer layers of the sun. Red light is the lowest energy and blue light is the highest energy. Just like how a red ember on a fire is not as hot as a yellow flame, and blue flames are the hottest of all. The black bars, the gaps, in the sun's spectrum are known as absorption lines, and they're caused by the gases in the outer layers of the sun absorbing some of the light. The sun contains many elements: hydrogen, helium, carbon, and smaller amounts of heavy elements. When the light from the sun shines through these elements, the atoms absorb the energy, but they only absorb light that is just the right color to match the energy they need. This gives us those gaps in the sun's spectrum, and by looking at the gaps, we can see what the sun is made of. An emission spectrum is the opposite of an absorption spectrum. Instead of getting light with a few colors missing, in an emission spectrum, those are the only colors we get. To create an absorption spectrum, we had to shine light through a gas, but to create an emission spectrum, we heat up a gas instead. The atoms in the gas will absorb this energy, but only for a little while. Heating the gas causes the atoms to be jiggled up and energetic. They have too much energy. Eventually, this energy is re-released, or emitted, as light, and the color of the light that is emitted is different for every element. so we can look at the emission spectrum of any given gas to figure out what elements are in the gas we're heating. So far, we've learned about how atoms can absorb the light of particular colors, or when heated up, emit light of those same colors. But how does it do that, and why is it only certain colors? Atoms contain electrons orbiting around the nucleus, and those electrons sit inside energy levels, also known as shells. Energy levels are particular orbits or particular amounts of energy that electrons are allowed to have. Some examples are shown here. As you can see, we can draw them as circular orbits, like on the right, or represent them as straight lines, like floors of a hotel, like on the left. The electrons in an atom can absorb energy and jump from a lower energy level to a higher one, but only if they get exactly the right amount of energy to make the jump. If they jump too far, or not far enough, they'll miss. And if they're going to miss, then they stay where they are. As you can see in this image, atoms can only absorb light of certain energies, or colors. The straight arrows show electrons jumping to higher energy levels. When you shine light through a gas, the electrons absorb light that has enough energy to help them jump up. This gives you the absorption spectrum, with particular colors of light absorbed. And when you heat up a gas, the electrons also jump up, before later falling back down and releasing this energy as light. This gives you the emission spectra, which contain certain colors of light. The colors match the atom's energy levels. In this lesson, we've discussed two types of atomic spectra: emission spectra and absorption spectra. Absorption spectra are what you get when you shine white light through a gas. Certain colors or energies of light are absorbed by the gas, causing black bars or gaps to appear in the spectrum. This happens because the electrons in the atom of gas can only absorb certain amounts of energy, the amount needed to jump up into a higher orbit or energy level. So light that has this energy is absorbed, and the rest of the light passes through. Emission spectra are what you get when you heat up a gas. The electrons in the atoms absorb the heat energy, allowing them to jump into higher energy levels. After a while, the electrons fall back down into lower levels, and the energy they lose in the process is released as light. The light that is emitted matches the energy levels of the atoms, and so has particular colors. Because every atom has different energy levels, every atom will produce different absorption and emission spectra. We can use absorption spectra and emission spectra to find out what elements are present in the gas, including the elements present in the sun. When you shine a white light through a prism, you find out that it contains a rainbow of colors. This is called dispersion, and it happens because light of different wavelengths or colors refracts or bends by different amounts inside the prism. The rainbow could be described as a spectrum, and if the spectrum goes all the way from red to violet with no gaps, then it is a continuous spectrum. A beam of perfectly white light, like you would get under certain laboratory conditions, contains this kind of spectrum. But as we'll find out, most light, even the light from the sun, does not contain a continuous spectrum. White light might be a continuous spectrum, but it's only part of the electromagnetic spectrum. There are more wavelengths than we can see with our human eyes. A wider continuous spectrum would include radio waves, microwaves, and infrared, ultraviolet, X-rays, and gamma rays. As far as we know, no object in the universe sends out waves across the whole of the electromagnetic spectrum, so finding a continuous spectrum spanning the whole of the electromagnetic spectrum would be impossible. The following diagram shows the full electromagnetic spectrum and everything it contains. The energy of waves increases from left to right across the electromagnetic spectrum. The sun is extremely bright and gives off an immense amount of energy, but it turns out that it isn't even close to giving off a truly continuous spectrum. Even though we do see a rainbow when light is refracted after it rains, when we look at the sun's light and analyze it in detail, we find that there are gaps where we see nothing at all. When we take the sun's light and put it through a spectrometer, a device that separates light by wavelength, the sun's spectrum looks something like this. The gaps in the sun's spectrum are called absorption lines, and they give us valuable information about the sun. Here's how it works. The sun contains elements like hydrogen and helium. When the sunlight, including ultraviolet and infrared that we can't see, shines through these elements, they absorb the energy. but they only absorb electromagnetic waves that are just the right color to match the energy they need. This gives us those gaps in the sun's spectrum. Each element in the universe has a different combination of absorption lines, so we can use the sun's absorption spectrum to figure out what elements are present in the sun. This is how we know what the sun's made of. An emission spectrum is the opposite of an absorption spectrum. Instead of getting a mostly continuous spectrum with a few particular colors missing, in an emission spectrum we only get those few particular colors. These are called emission lines. Instead of shining light through a gas, as we do to create an absorption spectrum, to make an emission spectrum we heat the gas up. This causes the atoms to absorb the energy. Before long, that energy is re-released as light, and the color of the light that is emitted is different for every element. So we can look at the emission spectrum of any given gas to figure out what elements are in the gas we're heating. Let's review. There are three main kinds of spectra that we have explored: continuous spectra, absorption spectra, and emission spectra. A continuous spectrum contains many different colors or wavelengths with no gaps. Perfectly white light shined through a prism causes dispersion of the light, and we see a rainbow. This is a continuous spectrum. However, visible light is only one part of the electromagnetic spectrum, which also contains infrared, microwaves, and radio waves on the red side, and ultraviolet rays, X-rays, and gamma rays on the blue side. Even though we see a rainbow in the sky when the sun shines after it rains, this is not actually a continuous spectrum. Most light in the universe, including light from the sun, is not a continuous spectrum, but is instead either an absorption spectrum or an emission spectrum that we can see through a spectrometer. When light is shined through a gas, like in the sun, the elements there absorb some of the light, creating an absorption spectrum with absorption lines. Conversely, when a gas is heated, the atoms in the gas absorb the energy and emit light, and an emission spectrum results. The lines in the emission spectrum are called emission lines. Looking at absorption and emission spectra can tell you what elements are present in stars like the sun and other gases.
When Bruce Banner gets angry, he turns into the Hulk. This happens due to a hefty dose of gamma radiation. But can radiation really turn you into the Hulk? Is the green glow of radioactivity real? And just what are radioactive substances anyway? Radiation might sound like something dangerous, but that depends on what kind of radiation you're talking about. There are a lot of different types of radiation. The light coming from a household lamp is a type of radiation, and the microwaves that cook your food are radiation. But when we talk about radioactive substances, we're concerned with particular types of radiation. A radioactive substance is unstable and produces dangerous kinds of radiation. It is unstable because the strong nuclear force that holds the nucleus of the atom together is not balanced with the electric force that wants to push it apart. Because it's unstable, the atoms will decay into more stable ones. Another way of thinking about radioactivity is in terms of energy. A radioactive atom has a higher energy than it needs to have. Energy in the universe tends to spread out, and so when something has more energy than it needs, it's only a matter of time until it loses that energy. When a radioactive atom loses its extra energy by decaying, that energy has to go somewhere. Energy in the universe is never created or destroyed. It is said to be always conserved. Where does it go? It goes into the radiation that is produced. Radioactive substances are continually producing three kinds of dangerous radiation: alpha particles, beta particles, and gamma rays. These types of radiation are invisible to the naked eye, and so you don't see a green glow, but they can interact with nearby phosphorescent or fluorescent materials that will glow green. This is why a green glow is associated with radioactivity. Unfortunately for superhero fans, there is no evidence that these three kinds of radiation can turn you into the Hulk. Radioactive substances produce alpha particles, beta particles, and gamma rays. But what are these three types of dangerous radiation? Alpha particles are the nuclei of helium atoms. They move slowly, don't penetrate the skin, but can cause a lot of damage if swallowed. Beta particles are high-energy electrons that can penetrate through paper and even part of the way into the human body, but cause less damage when they do. And gamma rays are extremely high-energy electromagnetic waves that can only be stopped with thick lead or concrete. Let's look at some different uses of radioactive substances. Nuclear power plants. One example of a radioactive substance is uranium. In nuclear power plants, uranium is used to produce electricity. When radioactive substances like uranium produce radiation, they also create a lot of heat. That heat causes water in the power plant to boil, turning turbines and creating electricity. Killing cancer. Radium is another radioactive substance and is used to treat cancer. Although the radiation produced by radioactive substances can be dangerous, it can also be used to kill cancer cells. A small amount of radium is encased in a gold seed and implanted inside the tumor. This delivers radiation directly to the cancer cells without destroying other tissues in the body. Smoke detectors. Smoke detectors also contain a radioactive substance, americium. Packaged inside the smoke detector is a tiny sample of americium. This americium produces alpha particles, radiation, which then collides with oxygen and nitrogen in the air to produce ions. Ions are charged particles and therefore conduct electricity. These ions allow electricity to flow between two electrodes. But when smoke enters the ion chamber, the smoke particles neutralize the ions and reduce the amount of electricity that flows. When the flow of electricity reduces, the alarm is triggered, and everyone in the kitchen has to cover their ears. Let's review. A radioactive substance is unstable and produces dangerous kinds of radiation. Radioactive substances produce three types of dangerous radiation. Alpha particles are the nuclei of helium atoms. They move slowly, don't penetrate the skin, but can cause a lot of damage if swallowed. Beta particles are high-energy electrons that can penetrate through paper and even part of the way into the human body, but cause less damage when they do. And gamma rays are extremely high-energy electromagnetic waves that can only be stopped with thick lead or concrete. Different uses for radioactive substances include nuclear power plants, cancer treatment, and smoke detectors.
Radiation is part of our everyday lives. There are natural sources of radiation, such as radiation from outer space, as well as man-made sources of radiation, like nuclear power plants and cell phones. Radiation is given off from a process called radioactive decay. Radioactive decay occurs when the original nucleus, or parent nucleus, of an unstable atom decomposes and forms a different nucleus, or the daughter nucleus. The rate at which radioactive decay occurs is measured using half-life, which is the time it takes for half the amount of the parent nucleus to decay. Each time the half-life of a radioactive material occurs, the amount of radioactive material decreases to half of the original value. In order to calculate the half-life of a radioactive material, we use the following equation. N sub 0 is the initial quantity of the substance. Nt is the quantity that still remains and has not yet decayed after a time t. T sub 1/2 is the half-life of the decaying quantity. E is Euler's number, which equals 2.71828. For example, we can use the formula to solve this problem. The radioisotope strontium-90 has a half-life of 38.1 years. If a sample contains 100 milligrams of Sr90, how many milligrams will remain after 152.4 years? Here are the steps in calculation. 1. Negative 0.693 multiplied by 152.4 equals negative 105.6132. 2. Negative 105.6132 divided by 38.1 equals negative 2.772. 3. E raised to the power of negative 2.772 equals 0.0625. 4. 100 multiplied by 0.0625 equals 6.25. When radioactive decay occurs, a particle or energy is emitted when the nucleus of the parent atom decays to the daughter nucleus. Before we proceed to the different types of decay, let's review that the atomic mass is the superscript, or the small number at the upper left side of the element symbol, indicating how many protons and neutrons are in the nucleus, and the atomic number is the subscript, or small number at the lower left side of the element symbol, indicating how many protons are in the nucleus. There are three main types of radioactive decay. These are alpha decay, beta decay, and gamma emission. Let's talk about alpha decay first. Alpha decay or alpha emission is the release or emission of an alpha particle, which is a helium nucleus consisting of 2 protons and 2 neutrons. This type of decay usually occurs in larger and heavier atoms. In this figure, you'll see that a helium particle, alpha particle, is emitted from the parent nucleus. Due to the release of the alpha particle, the daughter nucleus has an atomic mass that is 4 less than the original and an atomic number that is 2 less than the original. Since the atomic number is different, then the chemical element is also different. Here is the equation for the radioactive decay of uranium to thorium. If we add all the superscripts from the product side, 234 plus 4, it will be equal to the atomic mass of uranium, which is 238. If we add all the subscripts from the product side, 90 plus 2, it will be equal to the atomic number of the parent nucleus uranium. Beta decay or beta emission occurs when a neutron transforms into a proton or a proton transforms into a neutron inside the nucleus. This conversion results in a beta particle, either an electron or positron, to be emitted, accompanied by either an electron antineutrino, a subatomic particle that is electrically neutral, or electron neutrino. There are 2 types of beta decay, beta minus decay and beta plus decay. Beta minus decay occurs when a neutron turns into a proton. This causes an electron, accompanied by an electron antineutrino, to be emitted. As a result, the daughter nucleus's atomic number increases by 1. Below are the symbols typically used for a beta minus decay. An example is shown where the iodine undergoes radioactive decay, producing xenon. We can see that the atomic number increases. We can also see that an antineutrino is emitted. If we check the superscripts, atomic masses, and subscripts, atomic numbers, they are balanced in the reactants and products. 131 equals 131, and 53 equals 54 minus 1. Beta plus decay or positron emission occurs when a proton turns into a neutron, causing an electron neutrino and a positron, a particle that has the same mass but opposite charge as an electron, also called a positive electron, to be emitted. As a result, the daughter nucleus's atomic number decreases by 1. The illustration shows the 2 possible symbols of a positron as well as a positron emission reaction, with carbon decaying to boron. The atomic masses, 11 equals 11, and the atomic numbers, 6 equals 5 plus 1, are balanced. Gamma emission involves a release in energy in the form of gamma rays, very high-energy electromagnetic radiation. This type of emission usually accompanies other decays, such as alpha or beta decay. Gamma rays are emitted because when the nucleus undergoes alpha or beta decay, the nucleus is all shaken up and needs to release energy. Gamma rays have no atomic mass and no atomic number. Here is the reaction of a gamma emission that occurs accompanying beta decay of cobalt to nickel. If we check all the superscripts, atomic masses, they are balanced in the reactants and products. 60 equals 60. The subscripts, 27 equals 28 minus 1, on both sides are also balanced. When radioactive decay happens, radiation occurs due to the parent nucleus decomposing to another nucleus, which is what we call the daughter nucleus. Radioactive decay of a radioactive substance or material can be measured by the half-life, which is the time it takes for the radioactive material to decay to half of its original amount. Radioactive decay has 3 main types of decay: alpha decay or alpha emission, beta decay or positron emission, and gamma emission. It's important to note that there are 2 types of beta decay, beta minus decay and beta plus decay, or positron emission. The table shows the symbols of the particles emitted for each type of radioactive decay. The particles that are emitted, depending on atomic numbers and atomic masses, change the parent nucleus.
You are going to the gas station and for some reason decide to put 3 kilograms of gasoline in your car. This is the equivalent of almost 1 gallon of gas, so not much. And it may get you somewhere around 25 to 35 miles, depending on the gas mileage of your vehicle, of course. 35 miles per gallon might seem great, and this is what you would get out of it if you combusted it in your car. Now, what if I told you that those 3 kilograms of fuel could take you around the Earth hundreds of times? if your car were equipped to run on nuclear energy instead of chemical energy, the combustion of gasoline, you would be able to get billions of times more energy out of the 3 kilograms of gasoline. At this point, having a nuclear-powered car seems about as technologically far off as having a time machine. But the idea is that nuclear reactions produce much more energy than chemical reactions. Why? The energy involved in a nuclear reaction can be calculated using the well-known equation E equals mc squared. In this equation, E stands for energy, m represents mass, and c stands for the speed of light, which is 3.0 times 10 to the 8th meters per second. If the mass is measured in kilograms, as in my opening example, then the amount of energy obtained from that amount of mass would be represented in joules, a common unit of energy in chemistry. What this equation states is that mass and energy are directly proportional to each other. If a substance gains mass, it will gain energy. If it loses mass, it will lose energy. This mass-energy conversion is really interesting because it usually deals with very small amounts of mass, barely even noticeable, and very high amounts of energy, enough to power a city. We are going to go into more detail on this by zooming in on just one alpha particle, or a helium nucleus. In nuclear symbols, we would write it like this. Now, let's imagine that the helium nucleus is busted up into little pieces. If this happened, it would require a great deal of energy. And just like there's a special name for the energy required to remove an electron, ionization energy, this great deal of energy required to separate the nucleus into its individual pieces has a special name, nuclear binding energy. The higher the nuclear binding energy, the more stable the nucleus, meaning that the really stable nuclei will require more energy to split up. So far, we have discussed what happens when this little helium nucleus gets hit with a lot of energy, enough to break it up into smaller pieces. So let's write this in equation form. So here is our helium nucleus, represented by 4,2He. 4 being the mass number, or the number of particles in the nucleus, the protons and neutrons, and 2 being the atomic number, or the number of protons. We're then going to use a plus sign and write out the word energy, because we're adding energy to this little guy. We're going to go a little further and write down the mass of our helium nucleus. If we report out a very accurate mass of a helium nucleus, many places past the decimal, we get a mass of 4.00150 AMU. Next, we're going to draw our arrow, indicating that a change will take place once all of this energy is added. And on the other side, we write out each particle that is created. 2 protons, each symbolized as 1p, and 2 neutrons, each symbolized as 10n. Finally, we will write down the mass of each of these particles, measured out many places past the decimal. Usually, we express the mass of a proton as 1 AMU, which is acceptable in most situations. In this situation, however, we need to be more precise. The mass of a proton measured out to 6 significant figures is 1.00728 AMU. The same applies for the mass of a neutron. Usually it is reported as 1 AMU. But measured out to 6 significant figures, we have 1.00866 AMU. Do you notice anything strange about these masses? What if we add up the masses of each of the 4 particles? We get a total mass of 4.03188 AMU. That is 0.03038 AMU higher than the mass we started out with. This difference in mass is called mass defect. Mass defect is basically the difference between the mass of a nucleus and its pieces. And by pieces, I mean specifically its nucleons, or its protons and neutrons. So, how can mass just be created? To answer this, we go back to the equation mentioned earlier, E equals mc squared. If we add enough energy to a nucleus and split it apart, we will see an increase in mass, because this is proportional to the amount of energy we added. The same goes for the reverse. If we were to flip that arrow around and take all of our individual particles with the higher total mass and fuse them together to form a nucleus, we would get a helium nucleus with a lower mass, and a lot of energy would be released. This reiterates my earlier statement about how if a substance gains or absorbs energy, it will gain mass, and if a substance loses or emits energy, it will lose mass. So whenever we get energy from a nuclear reaction, say in a power plant, it is because nuclei are losing mass by breaking up into smaller pieces. Sometimes these smaller pieces are nucleons, protons and neutrons, and sometimes they're just smaller, lighter atoms. In either situation, very minute amounts of mass are destroyed and converted into huge amounts of energy. When energy is released in a nuclear reaction, a certain amount of mass is also lost. If we know how much mass is lost, we can use Einstein's equation, E equals mc squared, to calculate the amount of energy in joules produced by multiplying the mass in kilograms that is lost by the speed of light squared. The speed of light squared is equivalent to 9.0 times 10 to the 16th meters squared per second squared. This relationship shows that even a small change in mass results in a large change in energy. That's why if the entire mass of the gallon of gas in your tank was converted into energy via a nuclear reaction, you would be able to travel so far. It takes a large amount of energy to split a nucleus into smaller pieces because there's a very strong force holding the nucleus together. This amount of energy is called the nuclear binding energy. Finally, when a nucleus is split into smaller pieces, those pieces will have more mass than the original nucleus. This difference in mass is called mass defect, and it is this difference that is responsible for nuclear energy.
Nuclear fission is the process in which a large nucleus splits into two smaller nuclei with the release of energy. In other words, fission is the process in which a nucleus is divided into two or more fragments and neutrons and energy are released. The mass changes and associated energy changes in nuclear reactions are significant. For example, the energy released from the nuclear reaction of 1 kilogram of uranium is equivalent to the energy released during the combustion of about 4 billion kilograms of coal. This is Albert Einstein's famous equation relating mass and energy. The change in energy is equal to the change in mass times the square of the speed of light. This means that any reaction produces or consumes energy due to a loss or gain in mass. Energy and mass are equivalent. Note that because c to the second power is large, a small change in mass results in a large change in energy. When nucleons, or particles that comprise atomic nucleus, combine together to form an atom, the energy is released, corresponding to the mass defect. The mass of the nucleus is always less than the sum of the masses of the individual protons and neutrons that comprise it. Conversely, energy is needed to break apart a nucleus into its nucleons. Nuclear binding energy can be defined as the amount of energy needed to break 1 mole of nuclei into individual nucleons. The larger the binding energy per nucleon, the stronger the nucleons are held together and the more stable the nucleus is. Less stable atoms have lower binding energies per nucleon. In other words, it is harder to break apart a nucleus with a high binding energy than a nucleus with a low binding energy. The binding energy per nucleon is a function of the mass number. Light nuclei gain stability by undergoing nuclear fusion. Heavy nuclei gain stability by undergoing nuclear fission. The following figure shows the binding energy as a function of the mass number. Binding energies in this figure indicate that the heavy nuclei tend to be unstable. To gain stability, they can fragment into several smaller nuclei. Because atoms with mass numbers around 60 are the most stable, heavy atoms, those with mass numbers greater than 60, tend to fragment into smaller atoms in order to increase their stability. The splitting of a nucleus into fragments is accompanied by a very large release of energy. Nuclear power plants use nuclear fission to generate power. The nuclei of uranium atoms, as well as the nuclei of other large atoms, can undergo nuclear fission naturally. The first nuclear fission reaction discovered involved uranium-235. Nuclear power plants use uranium-235 nucleus to undergo fission by hitting them with neutrons, as shown by the model in the following diagram. Nuclear power plants use uranium-235 nucleus to undergo fission by hitting them with neutrons, as shown by the model in this diagram. This figure represents the process of nuclear fission when a neutron strikes a uranium-235 nucleus. Barium-141 and krypton-92 are just two of many possible products of this fission reaction. In fact, scientists have identified more than 200 different product isotopes from fission of a uranium-235 nucleus. The elements barium and krypton are typical results of this fission. The energy released by each fission can be found by calculating the masses of the atoms on each side of the equation. In the reaction we just saw, the total mass on the right side of the equation is 0.186 ANU smaller than that on the left. The energy equivalent of this mass is 2.78 times 10 to the negative 11 joules, or 173 mega-electron volts. This energy appears as the kinetic energy of the products of the fission. Each fission of uranium-235 releases additional neutrons, as shown in this figure. If one fission reaction produces 2 neutrons, these 2 neutrons can cause 2 additional fissions. If those 2 fissions release 4 neutrons, those 4 neutrons split other nuclei, and could then produce 4 more fissions, and so on, resulting in a nuclear chain reaction, as shown in this figure. This situation is one type of nuclear chain reaction, a continuous series of nuclear fission reactions, a self-sustaining process in which one reaction initiates the next. The number of fissions and the amount of energy released can increase rapidly. In an uncontrolled chain reaction, huge amounts of energy are released very quickly, as shown here. In fact, the tremendous energy of an atomic bomb is the result of an uncontrolled chain reaction. In contrast, nuclear power plants use controlled chain reactions. The energy released from the nuclei in the uranium fuel is used to generate electrical energy. A common fuel is fissionable uranium, IV oxide UO2, encased in corrosion-resistant rods. U-238 is the most abundant isotope, 99% of uranium. U-235, which makes up 0.7% of the natural uranium, has the rare property of being able to undergo induced fission. U-235 atoms undergo fission when hit by a neutron. The fuel used in nuclear power plants is enriched to contain 3% uranium-235, the amount required to sustain a chain reaction, and is called enriched uranium. Additional rods, often made of cadmium or boron, control the fission process inside the reactor by absorbing neutrons released during the reaction. Keeping the chain reaction going while preventing it from racing out of control requires precise monitoring and continual adjusting of the control rods. Much of the concern about nuclear power plants focuses on the risk of losing control of the nuclear reactor, possibly resulting in the accidental release of harmful levels of radiation. The 3 Mile Island accident in the United States in 1979 and the Chernobyl accident in Ukraine in 1986 prove examples of why controlling the reactor is critical. Let's review. The nuclei of some atoms can break down into 2 smaller, more stable nuclei during a process called nuclear fission. Heavy nuclei with mass numbers greater than 60 tend to be unstable and split into smaller nuclei with a release of energy. Nuclear chain reaction is a continuous series of nuclear fission reactions, a self-sustaining process in which one reaction initiates the next.
Without our sun, life on Earth wouldn't exist. It's the light and heat given off by it that allows us to thrive on our planet. Yet the sun itself, our nearest star, is nearly 93 million miles away from the Earth. To be able to provide light and heat all the way out to our planet and even beyond, it requires a massive amount of energy. The process that fuels our sun and allows it to give off that much energy is called nuclear fusion. Nuclear fusion is a reaction where 2 atomic nuclei fuse together to create a larger nucleus and in the process release energy. You can view a fusion reaction like a car collision you might see in a movie. 2 cars slam into each other and get stuck permanently together while little pieces of them go flying off in every direction. Nuclear fusion is much the same, where the cars are atomic nuclei and the little pieces are various particles and waves given off. The main sources of nuclear fusion in our universe are stars like our sun. Every star in the sky is powered by some form of nuclear fusion, including the carbon fusion cycle, the triple alpha process, and the type of fusion that commonly occurs in our Sun, proton-proton fusion. The various forms of nuclear fusion are differentiated by the initial atoms undergoing the process and the atom resulting from the fusion. Nuclear fusion occurs in stars due to the extremely high pressure and temperature at their cores. At the core of the star, the gas has been heated to the point of it becoming a plasma. In a plasma, electrons may leave their associated atoms, creating a gas filled with positive ions and free electrons. Pressure is needed to bring the atoms close enough together to fuse. High temperature is needed to overcome the Coulomb force between the atomic nuclei. The Coulomb force is the force given off by objects due to electric charge. Objects with the same charge repel, and objects with opposite charges attract. The atomic nuclei being fused consist of protons and neutrons. Since protons are positively charged and neutrons have no charge, atomic nuclei all have a net positive charge. This means they repel each other, and under normal circumstances would not fuse together. Have you ever tried to touch two magnets together with the same poles? They try to push each other apart, much like the two positively charged nuclei want to in atomic fusion. It's extremely high temperatures that give them the energy needed to overcome the Coulomb force and fuse together. The type of nuclear fusion occurring in a star is dependent on its mass and age. The high temperature and pressure in a star are caused by its own gravity pushing inwards on it. The more massive the star, the higher the pressure and temperature inside it. The types of atoms that fuse together in a star can change depending on how high the temperature and pressure are in the star. Regarding age, the atoms in a star being fused together are not infinite. As the star grows older, there will be less and less of these atoms until it can no longer support large-scale fusion of them. The fusion in stars releases a great amount of energy that creates an outwards pushing force which is kept in balance by the star's gravity pushing inwards. When the atoms being fused are running out, fusion slows down. Now the inwards pushing force of gravity will be greater than the lesser outwards force created by fusion, and the star will begin to collapse. When this collapse happens, the environment inside the star can change in such a way that a new type of fusion is ignited, re-expanding the star. The major type of nuclear fusion happening in our Sun is known as proton-proton fusion. In proton-proton fusion, hydrogen atoms are fused together through several steps to eventually become a helium-4 atom. Initially, two hydrogen atoms collide, forming a single deuterium atom, a positron, and a neutrino. Deuterium is an isotope of hydrogen. An isotope has the same number of protons in its nucleus as the standard form of its element, but a different number of neutrons. A positron is a particle with the same mass and magnitude of charge as an electron, but has a positive charge instead of a negative one. A neutrino is a chargeless particle with a mass of nearly zero. In the next step, the deuterium atom fuses with a proton to form a helium-3 atom and gives off a gamma ray as a result. Finally, the helium-3 atom fuses with another helium-3 atom that was created in the same process from another two hydrogen atoms. This creates an end result of a single helium-4 atom and two protons. It should be noted that the single helium-4 atom is lighter than the four hydrogen atoms that started this process to form it. So what happened to all that extra mass from the hydrogen atoms that we started out with? Well, that's where we get the massive amount of energy given off by nuclear fusion. From Einstein's famous formula, we know that E equals mc squared. In this formula, E is energy, m is mass, and c is the speed of light. The speed of light in a vacuum is 3 × 10⁸ meters per second. That's a huge number, and in Einstein's equation for energy, it's squared. Knowing that, and looking at the right side of the equation, we can see that it doesn't take that much mass to produce a lot of energy. This is why nuclear fusion produces such a vast quantity of energy. While stars are still the main source of nuclear fusion, we too on Earth have been able to produce nuclear fusion artificially. The first instance of artificially induced nuclear fusion was in the hydrogen bomb. The hydrogen bomb gets its name from the hydrogen isotopes, deuterium and tritium, it uses in the fusion process. Much like the stars we talked about in the previous section, high pressure and high temperature are required for the nuclear fusion process. In order to get a high enough temperature and pressure inside the bomb, another nuclear fission explosion must be triggered first. Nuclear fission differs from fusion in that it's caused by splitting a single atomic nucleus apart, in contrast to combining two together. The fission explosion is contained within the bomb long enough to raise the temperature and pressure, triggering the fusion process responsible for the bomb's explosion. The future of man-made nuclear fusion might not all be about destruction, though. Nuclear fusion power plants are being looked at for the future. There are a couple of reasons why a nuclear fusion power plant would be superior to the already existing nuclear fission power plants. First, they would be much safer than the nuclear fission reactors, since any radiation leakage from them would not be above the normal levels of radiation people are exposed to by the natural world around them. Second, they would be better for the environment by producing less radioactive waste. The difficulty in getting a working nuclear fusion power plant comes from the high pressure and temperature requirements we already know are needed for fusion. Two possible ways of creating the needed environment for nuclear fusion are magnetic confinement and inertial confinement. With magnetic confinement, hydrogen gas is first heated to the point where it becomes a plasma. Supermagnets are then used to compress the plasma. This compression creates the pressure and temperature needed for nuclear fusion. In inertial confinement, a powerful laser is focused on a small pellet containing the elements needed for nuclear fusion. When the laser comes into contact with the outside of the pellet, that part of the pellet evaporates. Evaporated particles from the pellet are then capable of striking the remaining solid pellet with high-energy collisions. These collisions will compress the pellet, creating the temperature and pressure necessary for nuclear fusion at its core. Nuclear fusion is the process in which two atomic nuclei are fused together into a larger single nucleus, releasing energy in the process. High pressure allows the atomic nuclei to get close enough to one another to fuse. High temperature allows atomic nuclei to overcome the Coulomb force, which is the force given off by objects due to electric charge that would normally keep them apart. In our Sun, the main type of fusion occurring is known as proton-proton fusion. In proton-proton fusion, 4 hydrogen atoms are fused into a single helium-4 atom, releasing a lot of energy in the process. We can see why so much energy is released during nuclear fusion using Einstein's famous formula E equals mc squared. Energy E is equal to mass m times the speed of light c squared, and c is a very large number. Thus, it only requires a little mass to create a lot of energy. Nuclear fusion also has been created on Earth artificially in hydrogen bombs. The high temperature and pressure necessary for fusion in hydrogen bombs is created by a nuclear fission reaction created and confined within the bomb before the fusion explosion occurs. Nuclear fusion is also being looked at as a possibility for power plants since it is a safer and cleaner form of energy than traditional nuclear fission power plants. Two possible types of fusion reactors that might be used for this are magnetic confinement, which uses superheated gas and magnetic compression, and inertial confinement, which uses lasers on required elements.
Colloids are important in both the natural environment and for manufactured products. A colloid is a mixture where at least 2 types of substances are placed together. The substances, also called particles, do not change. Each substance retains its own properties. They do not settle out of the mixture and cannot be seen. To understand more about what colloids are and aren't, it helps to first know a little more about 2 other types of mixtures, solutions and suspensions. A solution is made up of particles or solutes and a solvent. The solvent part of the solution is usually a liquid, but can be a gas. The particles are atoms, ions, or molecules that are very small in diameter. Suspensions are also made up of particles and a solvent. However, its particles are larger than those found in a solution. The particles in a suspension can be distributed throughout the suspension evenly by shaking the mixture. However, the particles in a suspension do not remain distributed throughout the suspension. They will settle out. Have you ever had a recipe that calls for mixing water and oil together? What happens? The water settles to the bottom and the oil rises to the top. You can mix them together, but in a few seconds after you stop mixing, the oil will rise to the top again. This is an example of suspension. A colloid mixture has particles that are not as small as a solution and not as large as a suspension. The particles are intermediate in size. What makes the colloid mixture unique is that the particles are assorted throughout pretty evenly, and they stay that way. Think of a solution as grade school, a colloid mixture as intermediate school, and a suspension as high school. The particles get larger as we move up the list of mixtures, just as students get larger in each school. So how can you tell the difference between a solution, a suspension, and a colloid mixture? It is easy to tell the difference between a suspension and a colloid mixture. As stated earlier, the suspension, when mixed, will combine. But when mixing is stopped, the particles separate out. Remember the oil and water example? So how can you tell if you have a solution or a colloid mixture? You can use the Tyndall effect, a test that can tell if you have a colloid mixture. If you have two glass beakers, you place the solution in one and the colloid mixture in another. Then shine a light through both beakers. The light that passes through the solution will not be visible because the particles are so small. However, the light will be reflected off the larger particles of a colloid mixture, so you will be able to see the light. To picture this more clearly, imagine that you are driving on a foggy night. What happens when you turn your headlights on? The water droplets scatter the light, making the headlight beams visible. That means one example of a colloid mixture is fog. Colloid mixtures can be solid, liquid, or gas. Examples include butter, milk, and fog. There are actually 8 types of colloid mixtures. They are usually described by the original states, solid, liquid, or gas. Let's go over a few types. First will come the name, then the greatest amount of medium in the colloid mixture, followed by the lesser amount of medium, followed by examples of each. For instance, solid sols have solids in the colloid mixture. Examples include pearls and opals. Gels have solids and liquids, and examples are butter and jelly. Solid foams have solids and gases, and examples are marshmallows and styrofoam. Sols have liquids and solids, and examples are paint, ink, and detergent. Emulsions have liquids as the greater amount of medium in the colloid mixture and as the lesser amount, and examples are hand lotion, mayonnaise, and milk. Foams have liquid and gas, and examples are shaving lather and whipped cream. Solid aerosols have gas and solids, and examples are smoke and dust. Aerosols have gas and liquids, and examples are insecticide spray and fog. Have you noticed in the list that there is only one type that does not have a gas as the greatest and lesser medium amount in the type? That is because it is not possible to do either in the natural world or man-made. There are 3 types of mixtures that were described in this lesson, but the focus was on colloid mixtures. A colloid mixture contains at least 2 particles that can be solid, liquid, or gas. The particles of a colloid mixture are intermediate in size when compared to the particles of a solution or a suspension. Remember the example of grade school, intermediate school, and high school students. To identify a colloid mixture from a solution, you can use the Tyndall effect. This is where you pass a light through the mixture. If the light bounces off the particles, you will see the light shine through and you have a colloid mixture.
Did you love playing with building blocks when you were young? Remember how you used the same set of blocks to create different shapes and structures by taking them apart and putting them back together again? Well, molecular formulas are a lot like building blocks, and they can provide us with clues about structural isomers. In theory, molecular formulas tell us how many atoms of each element there are in a molecule. Just like the building blocks, these atoms can bond together in different ways. Structural isomers are molecules with the same molecular formula, but their atoms have different arrangements or bonds. Let's take a look at a molecular formula. C sub 4 H sub 10. While the molecular formula can't tell us how the atoms are arranged, it can help us find some of the possible arrangements. In this case, there are 2 different arrangements for this molecular formula, butane and isobutane. Butane and isobutane have the same number of carbon, C atoms, and hydrogen, H atoms, so their molecular formulas are the same. However, each one has a different structural formula which shows how the atoms are arranged. So we can say that butane and isobutane are structural isomers. Now that we know what structural isomers mean, let's discuss the different types of structural isomers. These include chain isomers, functional group isomers, and positional isomers. Chain isomers are made up of two or more carbon or other compounds with the same molecular formula but different atomic arrangements or branches. Imagine removing one carbon compound and its attachments from a chain and attaching them to another carbon compound within the chain. For example, pentane, which has a molecular formula of C sub 5 H sub 12, has three different chain isomers. In the following illustration, you'll see that pentane and isopentane are chain isomers of each other. When we switch the CH sub 3 group of pentane, which is circled in red, with a hydrogen atom on the carbon chain, we'll have a chain isomer, isopentane. The following is an example of neopentane, another chain isomer of pentane. Neopentane results from exchanging the CH sub 3 on the left with the H atom, which is circled in red, as well as the other CH sub 3 group on the right with the H atom, which is circled in blue. By switching the hydrogen and CH sub 3 groups on the pentane chain, we change the way the atoms bond with each other. Here we can see all three chain isomers of pentane. Chain isomers not only apply to carbon groups on the chain, but also to different atoms that may be present on the chain. Let's take a look at 2-bromobutane, which has a bromine, Br group on the chain. By changing how the carbon, hydrogen, and bromine atoms are attached to the chain, we can come up with the following chain isomers of 1-bromobutane. Molecules are classified according to their functional groups, or groups of atoms or bonds with unique chemical and physical qualities. Let's take a look at some functional groups, where R and R' are side groups that consist of carbon, hydrogen, and/or other elements. For example, if a functional group of CHO, carbonyl, is attached to a molecule, then this molecule is classified as an aldehyde. If a functional group of negative OH, hydroxyl, is attached to a molecule, then this molecule is classified as an alcohol. Functional group isomers have the same molecular formula but different functional groups on the chain. For instance, ethyl alcohol and dimethyl ether have the same chemical formula but different functional groups, which are circled in blue. Ethyl alcohol has a hydroxyl group, ROH, and a dimethyl ether group, ROR'. Other examples of functional group isomers include acetone, which is a ketone, and propanol, an aldehyde. They both have the same chemical formula, but their functional groups are different. Let's go back to one of our building block structures and add a flag. Each time we revisit our structure, we leave the arrangement of the blocks intact and change only the flag. Positional isomers are similar in that everything remains unchanged, except the position of the important functional group, in this case, the flag. Positional isomers have the same carbon skeleton, but only the functional group, or a substitute, which is any atom or group of atoms, changes position. The following image shows the positional isomers of aminophenol. Here, the position of the substituent, negative NH sub 2, changes in the ring. Propyl bromide and isopropyl bromide are also positional isomers with 3 carbon atoms on the carbon chain. Each edge on the chain represents one carbon atom, which remains the same. The only thing that changes is the position of the bromine on the chain. Let's review. Structural isomers have the same molecular formula but different arrangements of atoms. There are 3 types of structural isomers: chain isomers, functional group isomers, and positional isomers. Chain isomers have the same molecular formula but different arrangements or branches. Functional group isomers have the same formula but different functional groups. These functional groups are composed of different groups of atoms that have been arranged a certain way and that provide the molecule with its unique characteristics. Positional isomers have the same number of carbon atoms on the chain, but the location of the substituent, which could be an atom or a functional group, differs on the chain.
Hand two different kids a pile of 8 identical Lego bricks, and chances are they won't build exactly the same thing. Since they are starting with the same materials, the structures they build, assuming they use all the pieces, would count as isomers. In chemistry, 2 molecules are called isomers if they contain the same atoms but are not the same. Geometric isomers are a special case where the atoms in each isomer are all connected in the same order, but the shape of the molecule is different. In the Lego example, if one child connects all 8 in a straight line, we will call A, and the other child connects all 8 in a staircase pattern we will call B, the 2 structures would be geometric isomers. In both cases, the bricks are connected in the same way, red-red, white-white, red-red, white-white, with no branch points. But clearly, the 2 have different overall shapes. Working with the same 8 bricks, many other geometric isomers can be built, like C, D, E, and F. Notice how the order of the connections is always the same, but the 3-dimensional shape varies. In chemistry, the 2 most common types of geometric isomers are those arising from a double bond and those arising from a ring structure. Note that geometric isomers are also called cis-trans isomers, and the terms can be used interchangeably. The Latin prefixes cis and trans indicate how the groups attached to the double bond are arranged in space, with cis meaning same side and trans meaning opposite side. Many molecules containing double bonds between carbon atoms have geometric isomers. The simplest examples are cis-2-butene and trans-2-butene. In each case, the chemical formula is C4H10, and the 4 carbon atoms are connected in a straight chain with no branching. Because the double bond is rigid and cannot rotate, the CH3 groups labeled as carbons 1 and 4 are on the same side in cis-2-butene, and on opposite sides in trans-2-butene. You've probably seen and even used the trans prefix without knowing exactly what it meant. A trans fat is a molecule in the fats category that contains a double bond and has the major groups surrounding the double bond attached opposite one another. Trans fats are not common in nature. They arise during food processing procedures such as partial hydrogenation. Every trans fat has a geometric isomer that is the corresponding cis fat. Cis fats occur naturally in plants and animals, and the human body is well equipped to digest most of them. Oleic acid, shown in the picture in green, occurs naturally in olive oil, canola oil, chicken fat, and lard, among other foods. It is the most abundant fatty acid in the cells that store human body fat. The geometric isomer oleic acid is the major trans fat found in hydrogenated or processed oils. Molecules containing rings can also have cis-trans isomers. Consider 2-methylcyclohexanol as an example. In the cis isomer, the OH and CH3 groups are on the same side of the ring. In the trans isomer, these 2 groups are on opposite sides of the ring. The most significant ringed geometric isomers in biochemistry come from glucose, the familiar sugar molecule. When glucose closes in on itself to form a ring, 2 geometric isomers are possible. They go by the names alpha-D-glucopyranose and beta-D-glucopyranose, and are shown in the top half of the picture seen here. The only difference between the 2 is the orientation of the OH group as up or down on carbon 1. The rest of the ring structure is the same. When hundreds or thousands of glucose units link up using the alpha-down position to link between molecules, the result is starch, the most common carbohydrate in the human diet. Potatoes, wheat, corn, and rice all contain large amounts of starch. When the units connecting the beta-up position, the result is cellulose, the major component of cell walls in plants. Cellulose is a source of dietary fiber for humans. These are just a few examples of geometric isomers that people encounter every day, and which are important in biochemistry and nutrition. Let's review. Geometric isomers, also called cis-trans isomers, are isomers that differ from one another in their geometry, but share the same atoms connected in the same way. The 2 most common sources of geometric isomers are double bonds and ring structures. Geometric isomers often have very different properties and roles.
Take a good look at your two hands. They're very similar. They each have 4 fingers and a thumb. They're each connected to an arm, and there's one on each side of your body. But they're also different, because one is your right hand and the other is your left hand. If you tried to put one on top of the other, or superimpose them, it wouldn't work. Your thumb on one hand would be where your pinky is on the other. And this is because even though they are both hands, they are mirror images of each other. Your hands are very much like a special type of isomer. Isomers are organic molecules that have the same chemical formula but different arrangements of their atoms. And optical isomers are isomers that are mirror images of each other. Like your hands, they come in pairs and are not superimposable. The different forms of optical isomers are called enantiomers. And the central carbon atom that holds each molecule together is referred to as being asymmetric. Also, just like your hand has 4 different fingers, this type of molecule has to have 4 groups in addition to that central carbon atom, and they must be different from each other as well. Okay, so where did the name optical come from? Well, these isomers got their name from how they rotate plane polarized light, or light waves that vibrate in only one direction. One enantiomer rotates it clockwise or to the right, and the other rotates it counterclockwise or to the left. Optical isomers are one of 2 types of stereoisomers. These are molecules that have different spatial arrangements, like we saw in the enantiomers before. They have the same structure and formula, but differ 3-dimensionally. Stereo means 3D. The other kind of stereoisomer is a geometric isomer. These are different versions of organic molecules with a restrictive carbon-carbon double bond. That double bond is called restrictive because it restricts rotation. Basically, if you can rotate the molecule so that it looks different, it's not actually an isomer. But if you have to break the double bond to get the molecule to rotate, then it is in fact an isomer. It's also important that we clarify the difference between stereoisomers, like the optical and geometric ones, from structural isomers. Instead of having a different 3-dimensional arrangement, structural isomers still have the same formula but have different structures. Perhaps a functional group is located in the middle instead of on the end, or the functional group is completely different from one isomer to the other. Or there could even be a difference in the central chain of carbons, which act much like the backbone of the molecule. All of these pentane molecules constitute structural isomers. Even though they might all have the formula C5H12, when you draw them out they will look quite different. Isomers are molecules that have the same chemical formula but have different arrangements of their atoms. One specific type of isomer is the optical isomer. These are isomers that are mirror images of each other. Because the atoms in these molecules differ in their spatial arrangement instead of their structure, they fall into the category of stereoisomers. Geometric isomers are the other type of stereoisomer, but they involve a carbon-carbon double bond. There are also structural isomers which have the same chemical formula but a different structure. This might involve a change in the carbon chain or functional group of the molecule.
Medical physics is the application of physics principles to medicine or health care. It's basically a way of using our physics knowledge to develop tools and treatments that help humans live longer and be healthier. There are many branches of medical physics. The main ones are diagnostic radiology or medical imaging, nuclear medicine, and radiation oncology. But there is a lot of overlap between these categories, as we'll see later. Physics can be found in a variety of other areas of medicine too. For example, many types of ventilators wouldn't be possible without an understanding of fluid pressure and pulse frequency, so that the ventilation rate and amount of pressure applied is appropriate. In fact, you could argue that any advanced or electronic technology used in medicine wouldn't exist without the knowledge of the universe gained through physics. Let's go through the 3 branches of medical physics and look at some examples of what kinds of things are involved. Diagnostic radiology is essentially a form of medical imaging. All the methods of medical imaging we use, including X-rays, mammography, computed tomography, ultrasound, and magnetic resonance imaging, MRI, among other technologies, require the presence of an on-site or consulting physicist. These technologies are complex and can only be repaired by those who understand them. MRI scanners use the principles of magnetism to take high-quality images of the inside of the human body, especially the brain. They basically work by monitoring the nuclear spin and distribution of hydrogen molecules. Since humans are about 70% water, we have plenty of hydrogen molecules to observe. X-rays are a way of taking images of the skeletal structure of the body. Ultrasound uses high-frequency sound waves that humans can tolerate, bouncing them off the inside of the body to create images of soft tissues. These are most notably used to create images of babies inside the womb. Nuclear medicine is a part of medicine that uses radiation to both treat disease and provide imaging and information about what's happening inside someone's body. Radiation can be used to destroy cancer cells and treat diseased organs. But there is some overlap between nuclear medicine and diagnostic radiology because nuclear medicine can also be used to diagnose. Radioactive tracers can be used to create images of body systems by having patients swallow or inject radioactive sources and creating images of where they go. We can even create regular photographs of the inside of the body using radiation through computerized axial tomography, CT, or positron emission tomography, PET, scanners. Radiation oncology is pretty similar to what we've already talked about in nuclear medicine. Radiation oncology is the treatment of diseases, including cancers, using ionizing radiation. So again, this overlaps a lot with nuclear medicine. However, since treating disease with radiation is so complicated, there are many professionals who are solely focused on this part of nuclear medicine. The term medical physics refers to the use of physics principles in healthcare and medicine. These can include the theories associated with amplitudes, fluid pressure, frequencies, and waves. Applications of these principles can be found in diagnostic radiology, nuclear medicine, and radiation oncology. As a form of medical imaging, diagnostic radiology, a form of medical imaging, includes mammograms, MRIs, ultrasounds, and X-rays. MRI scanners use large electromagnets to take interior images of the human body, especially the brain, while ultrasound uses high-frequency sound waves to create images of soft tissues. X-rays image the skeletal structure of the body. Nuclear medicine, which overlaps with diagnostic radiology and radiation oncology, uses radiation to both take images of and treat disease. CT and PET scanners, as well as radioactive tracers, either injected or swallowed, are forms of nuclear medicine. Radiation oncology uses ionizing radiation to treat diseases like cancer.
Humans are all about communication. We communicate with our families. We communicate with our coworkers. We communicate with strangers. The communities we develop could not have been sustained without good communication. And today, where the entire world is connected, communication continues to be vital. But in order to communicate over huge distances at different times of the day and night, we need some tricks up our sleeves. Understanding physics is so integral to those tricks that really there is no example of communication technology that isn't an application of physics. After all, physics is the science concerned with the nature and properties of energy and matter. It attempts to explain everything in the universe. The telephone was an application of physics. Going back further, so was the telegraph. But for this lesson, we'll focus on some modern communications technology and their origins in physics. To send a communication from one place to another, a signal, or data, must pass between the locations. There are two main types of signals, analog and digital. An analog signal in physics is just a wave. There are lots of types of waves, but for communication, most of the important ones are part of the electromagnetic spectrum. The electromagnetic spectrum includes light, radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. An example of sending analog communication would be satellite communication. Satellites are artificial objects in orbit around the planet, like the Earth. We use satellites for many things, but communication is probably the most common. One of the first uses of a satellite was when the President of the United States was able to broadcast a Christmas message in 1958, the first message to be transmitted via space. Today, communication satellites are used to transmit messages across the whole world, for businesses, between world leaders, for news reports, and even phone calls and internet connections. The signals satellites send are radio waves. Those radio waves are used to send our communications into space, and then the satellites transmit them back down to the Earth, again as radio waves. The pattern of the wave represents the exact audio being transmitted. A large peak might be a loud sound, for example, and a small one a quiet sound. But the computers that send and receive those signals are not analog. They're digital, and the physics of digital signals is quite different. The computers used to send and receive the signals work on physics principles. They turn analog radio waves into digital signals represented by electrons whizzing along circuit boards. Digital signals contain a series of ones and zeros, otherwise known as binary. Computers understand this language perfectly. The electric current, or flow of electrons, varies to represent these ones and zeros. But just to confuse things, digital signals can also be sent using electromagnetic radiation. This is usually done through a communication technology called fiber optics. Fiber optic cables are cables containing translucent materials called optical fibers that can carry electromagnetic waves, usually infrared. That infrared light reflects off the sides of the cable to continue down the length until it reaches its destination. These signals are digital, just like the electrons. A pulse of light represents a 1, and the absence of a pulse represents 0. Computers can receive these pulses and make sense of them. Fiber optic cables are often used to send audio signals in home theater systems and for internet connections, but really, fiber optic cables can be used to transmit any kind of information, including telephone calls. They're often used in important connections like expensive business communication links or long-distance links. And then there's the Internet. The Internet is a worldwide system of connected computers allowing the transfer of information and communication, like emails, audio conversations, and video chats. The Internet is probably one of the biggest advances of the last 30 years. It has revolutionized the way we communicate, do business, and learn about our world. The data sent through the Internet passes from place to place, either through electrical signals, which are moving electrons, or light pulses in fiber optic cables. But what really makes the Internet possible is the electronics at each end, the computers. Computers and all electronics are based on electrons. That's why they're called electronics. Electrons move in electrical circuits, powering components. The electrons in computers not only power the components, but transfer data and allow the components to communicate with one another. A thorough understanding of how electrons work and how circuits work is necessary to create a computer. Computers also contain semiconductors, which are materials that conduct electricity, but not as well as metals. This allows us to better control the way electricity flows and produce super fast and super small computers. We're coming to the end of the lesson, but this lesson could practically go on forever. That's because every single technology we use could not have been possible without our physics knowledge. Communication is at the heart of human society. And so, we have developed many ways to communicate with each other, even over great distances. We had telegraphs, followed by telephones, and now we have the Internet. We can send signals over huge distances by beaming electromagnetic radiation to a satellite, which then sends it back to Earth. Fiber optics are translucent cables which allow us to send pulses of light down them to transmit information. And the Internet is a worldwide interconnected network of computers that allows the transmission of data, including communications like emails, voice conversations, and video chats. Physics allows us to understand the electromagnetic radiation we use to transmit data with fiber optics and satellites, and to build computers that interpret those signals and transmit data on the Internet. All electronics, including computers, are based on the movement of electrons in electric circuits, which are designed from our understanding of them using physics. Every technology we have today has physics to thank for its existence.